For this course on NumPy, it is good to be familiar with certain software tools as well as having certain skills in order to understand array operations. For instance, you should be comfortable programming in Python 3, as this is the language which is used throughout this course. You should also have some familiarity with working with Jupyter notebooks, and this is the dev environment which will be used for all the demos. In addition, some demos in this course will involve basic matrix operations, so some amount of familiarity with those will also be useful. Since NumPy provides a framework to express data in the form of arrays and supplies a lot of array-based operations, it becomes the fundamental building block for a number of other Python libraries. All these libraries, which make use of NumPy under the hood, are all referred to collectively as the NumPy ecosystem. Some of these libraries include stats model, which is used extensively in order to perform statistical operations. Scikit-image is another library which makes use of NumPy, and this is used in the world of image processing. Scikit-learn is one more Python library which makes heavy use of NumPy, and this is used for machine learning as well as for data mining and data analysis. Pandas is another tool which is built on top of NumPy, and it supplies a number of easy-to-use data structures which are very helpful in the world of data analysis. And finally, matplotlib, which is a data visualization tool, also makes significant use of NumPy. So by virtue of being a rather fundamental package in order to store and manipulate data, NumPy finds itself being used in several data science libraries and tools. All the demos in this course will be performed in Jupyter Notebooks. Jupyter Notebooks are a browser-based interactive development environment which allows us to execute and view the results of sections of our application code without having to run the entire application. So here we navigate into a workspace directory and then enter the command Jupyter Notebook in order to bring up the application. Depending on your configuration, the Jupyter Notebook web app may come up automatically on your default browser. If not, you may simply copy this URL which comes up on typing the command and then bring up your browser and then paste this URL in the address bar and hit enter. So Jupyter Notebooks is now up, and these are the contents of the workspace directory from which I ran the Jupyter Notebook command. You can see here that I already have a datasets directory, and this contains the ready-made data we will be using just a little later in this course. We can just click on it to view its contents, and you notice that it contains two CSV files and a JPEG file. At this point, we just navigate back to the parent directory of our workspace, and we are now ready to code our first demo for NumPy, for which we will bring up a new Jupyter notebook. So we may go ahead and click New, and then select the backend kernel which will be used for this notebook. Throughout this course, I will be using Python 3 as the backend, so I'm just going to click on that. And this brings up a new Jupyter notebook. And the first thing I'm going to do here is to rename this notebook, which has come up with the default name Untitled, and call it something a little more meaningful. So our first demo is going to be about array creation, and this is what I'll call this notebook. So just click on rename, and the new name has been set for this notebook. So we will run this pip install command, and those familiar with Jupyter notebooks will recall that you can execute shell commands from a notebook cell by preceding it with the exclamation point. So on running this command, I get the message that I already have the latest version of NumPy. But if you don't already have it, then you will see all the installation steps here. Once the install is complete, we are ready to import this NumPy package into our notebook, and we will be referencing this package using the alias np. We now go ahead and create our first NumPy array. We call this array underscore 1, and this array will be initialized with a Python list containing all the one-digit odd numbers. We also make use of the np.array function in order to initialize this array with this Python list. And on running that, we will view the contents of array underscore 1 to see what this numpy array will look like. So when we run this cell, we have successfully created our very first numpy array. As you can see here, it contains the exact same elements as the Python list which we passed to it, except that this is not a list but a numpy array object. We now go ahead and create our second array called array underscore 2. And for that, we will be initializing it with a list which we pass as a variable. This list, which contains the first 7 multiples of 11, is assigned to a variable named num, which we then pass on to this np.array function in order to create our second numpy array. And on running this cell, our second array has also been created. We now move along and explore some of the other numpy functions which are available in order to initialize arrays. And one of these is the np.zeros function. This will create an array whose elements are all zeros, and the size of this array is determined by the argument which is passed to it. In this case, we are creating an array of 2 rows and 3 columns, and for that we pass in a tuple which contains the values 2 and 3. So we just run this cell in order to create our array of zeros, and we see here that the array with 2 rows and 3 columns has been created. Similar to the np.zeros function, there is an np.ones function which will create an array whose elements are all 1. Just like with the zeros function, the argument to np.ones is the size of the array, which is also known as the array shape. And in this case, we create an array with 3 rows and 2 columns. So we just run the cell, and our array of ones has also been generated. Note here that in our array of zeros as well as our array of ones, each of the elements are of type float. This you can tell by the decimal which appears right after the digits. So if you would like to create an array of integers instead, then we simply need to pass the dtype argument when using the np.ones or np.zeros function. So here we simply recreate our array of ones, but this time this is an array of integers rather than floats. NumPy also provides a function called np.empty, which will create a new array of the given shape. However, the elements of this array will not be initialized to any value. As a result, this operation will run quicker than any of the other array initialization functions. However, the elements of the array will need to be explicitly set at a later point. So when we run this function, we notice that each of the elements here is 1, and this is because that value was already present in the memory which was allocated for these elements. We now explore the np.I function, which will create a square identity matrix of the specified size. So this will generate a matrix of 4 rows and 4 columns, where all the diagonal elements are 1, while all the other elements are 0. Another numpy function is the arange operation, which allows us to create an array with a specified range and an interval. So the arguments for this function are the lower bound of the array, the upper bound, and the interval. So in this case, our array will begin with the element 2, and each element will be 2 greater than the previous one until the number 24 is hit. So when we execute this cell, our array of even numbers between 2 and 22 has been created. The arange function does not only take integers as arguments, but can also be used with floating point values. Here, we create an array beginning with 1 and going up to 3, with each of the elements being an increment of 0.3 over the previous one. So on running the cell, our array of floats has been created. We now look at how we can create a two-dimensional array using a list of Python tuples. So we once again use the np.array function and we pass in this list of tuples. And each of the tuples now represents a row in this 2D array. So when we run this command, our array of 2 rows and 3 columns has been created. I had previously mentioned that the size of an array in terms of the number of rows and columns is referred to as the array shape. So if you'd like to view the shape of a numpy array, we can make use of the shape property of the array object. Here we check the shape of this 2D array which we just created. And we can see here that this is an array of 2 rows and 3 columns, which is represented as a tuple. We have previously used the np.arange function in order to create a one-dimensional array with a specified lower bound, upper bound, and interval. If we simply pass in one value to this arange function, this argument is treated as the upper bound, and the lower bound is assumed to be 0, and the interval is assumed to be 1. So when we run np.arange with an argument of 8, it will create an array for us beginning with 0 and going up to 7 with an increment of 1. Now that we have a one-dimensional array of 8 elements, what if we would like to create a two-dimensional array out of this? For that, each numpy array object has a reshape function which will effectively reorder the elements of the array in the desired shape. So our array of 8 elements here can be reshaped into an array of 2 rows and 4 columns. So when we execute this cell, we note that this reshaping has taken place successfully. One caution when using this reshape operation is that an array needs to have the right number of elements in order to be reordered into a specified shape. So in this case, if we try to reshape an array of 6 elements to one containing 2 rows and 4 columns, that is 8 elements, then the operation will result in an error. So this reshape operation needs to be used with caution and ensure that the array being reshaped does have the required number of elements in order to be reordered. The last function we will view in this demo will make use of this array underscore nd array, which we see here has 2 rows and 4 columns. That is, it has a shape of 2, 4. Now, the function which we will explore here is called np.ones_like. This is similar to the np.ones operation in that it creates an array whose elements are all equal to 1. But the argument to this array is not a tuple representing the array shape, but is in fact another numpy array whose shape will simply be taken up. So this operation will create an array of ones whose shape is the same as the array underscore nd array. So on running this cell, we see that this array of ones with 2 rows and 4 columns, just like array underscore nd, has been created. In this demo, we will examine all the options available for us in order to view the contents of a numpy array. We begin by importing the numpy package, and we create our first numpy array, which we will call x, and we do that using the arange function in order to create an array of 8 elements from 0 through 7. The simplest way to view the contents of the array is to use the Python print function. So we just print the contents of x here, and the elements are now visible just as you could see a Python list. We now create a second array called y, And this is going to be a two-dimensional array of 4 rows and 4 columns, which we create using the reshape operation. And once again, we will use the Python print function to view the contents of y. And we see here that our 2D array is essentially a one-dimensional array of one-dimensional arrays. Moving on now to a 3D array, which we once again create using the reshape operation. And do note here that we can pass 3 arguments for the lengths of each of the 3 dimensions in our array. And we once again use the Python print function in order to print out the contents. And this array takes the shape 3, 4, 3 and is essentially an array of two-dimensional arrays. For the arrays we have viewed so far, all the elements have been fully visible. However, what if we go ahead and create a rather large array? This one contains 12,100 elements. And when we print this out, we notice that all the elements are not visible. But in fact, these 3 dots, which are also referred to as an ellipsis, is being used in order to indicate that there are elements between the ones which are visible on screen. The ellipsis also appears when we print out two-dimensional arrays, which we can observe when we simply reshape the previous array to a shape of 110 rows and 110 columns. And we observe from the output that the ellipsis now appears for both the rows as well as the columns. However, if you would like to view the entire contents of the array, irrespective of how large it is, then we need to make use of numpy's set_print options function, which allows us to specify how floating point numbers, arrays, and other numpy objects are displayed. We call this function by passing in a value for the threshold argument, which sets the number of array elements for which ellipsis will begin to be used. In order to eliminate this threshold, we need to set it to a null value, and for that we make use of a special numpy constant called nan, which stands for not a number. So when we set this value for the threshold, we can just go ahead and reprint our array of 110 rows and 110 columns. And on this occasion, the entire contents of this array, which is 12,100 elements, can be viewed. And of course, we'll need to scroll down in the output in order to view the full contents. Note that the default value for the threshold used by NumPy is 1000. We'll now go ahead and print an array of 10 rows and 10 columns. And as expected, the entire contents of this array is visible on screen. Now we can go ahead and set the print options once more, where we set a value of 50 for the threshold. So if we reprint this array of 100 elements, we will now see the ellipsis once more. Do note that once we execute the set_print options function, those options will apply for all the subsequent executions which we perform. And with that, we now come to the end of this demo on printing NumPy arrays. In this demo, we will be exploring some of the basic operations, mostly mathematical ones, which can be performed on NumPy arrays. We begin once more by importing the NumPy package first. And we will first initialize two arrays called P and Q. And you can see each of these are one-dimensional arrays containing 3 elements. The first operation between these two arrays which we will perform is an addition operation. And for that, we simply use the plus sign. So what does P plus Q give us? As you can see here, this operation has effectively performed an element by element addition. So the shape of the resultant array is exactly the same as that of each of the operands. So when performing a plus operation between two arrays of the same shape, then NumPy assumes that we want to perform an element by element addition. The same thing also applies when we perform a subtraction between the two arrays. So P minus Q results in an array containing 6, 6, and 3, which is an element by element subtraction. In fact, even other mathematical operations such as multiplication, division, and the modulus operation work in exactly the same way in NumPy. Now, what if we try to perform an operation between a NumPy array and a scalar quantity? So, what if we perform a modulus operation between the array p and the number 2? Well, in this case, NumPy is smart enough to assume that we wish to perform a modulus of 2 operation on each of the elements in the array p. And in fact, this is exactly the output which is generated. So this output has the shape of the array p. The same thing also applies when we perform Boolean operations. So if you would like to check whether the elements of array p are greater than 8, then we get an array of true or false values which has the same shape as the array p. And the same thing also applies when we perform a less than operation. So far, we have been working with one-dimensional arrays. However, when we switch to two-dimensional arrays, you will notice that the behavior is very similar. So here we recreate x and y to be two-dimensional arrays containing these elements, and we just print out its contents here. We now go ahead and perform an addition operation, and once more an element by element addition has been performed. The same thing also happens when we perform x minus y, where each element of y is subtracted from the corresponding element of x. And even the multiplication operation happens on an element by element basis. Another numpy operation which we can perform is a dot product between two arrays. And for that, we can call the dot function, which belongs to an array object. So this will generate the dot product between x and y. And there is another way in which we can perform a dot product, and that is by calling the np.dot function. So the dot function belongs to an array object, but is also part of the standard numpy library. While the dot function belonging to an array object takes in one argument, the np.dot function takes in two arguments. However, as we can see here, the outputs are identical. So each of the array operations we have performed so far have created a new array containing a result. However, we can also use these mathematical operators in order to modify the contents of an array. Here, we make use of the multiplication operation in order to multiply each of the array elements by 4. So when we execute this cell, we see here that the element by element operation has been performed. We now move ahead to aggregate operations which can be performed on numpy arrays. And for that, we create an array containing the mileage of several cars in a fleet. So imagine here that we are part of a car rental company which has various vehicles in its inventory, and this list represents the mileage for each of the vehicles in the fleet. Now, what if we want to sum up the mileage of all the vehicles in our inventory? For that, numpy conveniently provides us with a sum function which belongs to every numpy array object. So when we just call that, we get the sum of all the elements in our numpy array. There is also a min function which will return the minimum value in our numpy array, and correspondingly there is a max function as well. So this returns the highest value in our array. Now, what if we wish to calculate the average mileage of all the vehicles in our fleet? For that, there is the mean function which we can make use of, and we're just going to use this as part of the print statement. So the mean mileage of all the vehicles in our fleet is about 20,000 miles. So these were aggregate operations performed on a one-dimensional array. How exactly would they work in 2 dimensions though? For that, we create a 2-dimensional array with 4 rows and 4 columns. And when we run the sum function on this array, It simply sums up the values of each of the elements and returns us a single value. So this may be of use, but when we are working with 2 dimensions, we would also like to sum up values across the individual dimensions. To do that, when we call the sum function, we simply pass along a value for the axis argument. Here we specify that we would like all the values to be summed up for each of the columns, and the result is a one-dimensional array whose size corresponds to the number of rows in this array, and simply sums up the values in each of the columns. If we would like to sum up the values in each of the rows in the array, we simply call the sum function and set the value of the axis argument to 1, and this will return an array with the sum of each row, and the size will correspond to the number of columns. We can perform aggregations for individual dimensions even using the other aggregate functions. So here we get the minimum value in each row of our array, and the size once more corresponds to the number of columns. And finally, we confirm that we can also perform the mean operation for each of the rows in our 2-dimensional array. And once more, this returns the expected output. And with that, we have covered a number of the basic operations which can be performed on both 1-dimensional as well as 2-dimensional numpy arrays. We have previously seen how certain operations can be performed on numpy arrays on an element-by-element basis. In this demo, we will be covering universal functions, which are numpy library functions which operate on an element-by-element basis on numpy arrays. In this notebook, we once again begin by importing the numpy package, and we will first create a numpy array containing the radius values for a number of circles. And once we have this array of radii, we perform a mathematical operation which will apply to each of the individual elements in this array. So here, we obtain an array of diameters by multiplying each of the elements in this array of radii by 2. So executing this cell will produce an array of diameters for the circle whose radii have been defined previously. And similarly, we can also perform mathematical operations to get the areas of the circle using the circle_radii array. So here we are making use of the constant np.py, which is provided by numpy. We are also making use of Python's power operator in order to get the square of the radii from the elements in the radii array. So we have just covered once more how we can use mathematical operators in order to perform operations on an element-by-element basis on numpy arrays. However, we can also make use of numpy functions which work on an element-by-element basis. And to demonstrate that, we first define an array which contains a set of angles expressed in degrees. In order to express each of these angles in the unit of radians, we once more perform a mathematical operation on each of the individual elements of our angle_degrees array. And this operation will result in an array containing those same angles expressed in radians. Now, the first universal function which we will make use of is the np.sign function. It requires at least one argument, which is a numpy array, and this will calculate the sign value for each of the elements in that numpy array. That is, it performs an element-by-element operation. So when we execute this cell, we are presented with the sign values for each of the angles expressed as radians in our array. Similar to the sign function, numpy also provides a cos function in order to calculate the cosine values for each element in a numpy array. And correspondingly, there is also an np.tan function available in the numpy library. As you will have noticed, each of these functions requires the angles to be expressed in radians by default. Now that we have covered the basic trigonometric functions which are available, we can also go ahead and check for the inverse trigonometric functions. To do that, we first create an array which contains all of the sine values, and for that we once again use the np.sine function. And with these sine values, we pass it as an argument to the np.arcsine function, which will calculate the arcsine or the sine inverse of each of these sine values. So when we execute this cell, we note here that each of the angles have been recovered from all the sine values, but once again these are expressed in the form of radians. We can view the values in degrees for each of these angles by multiplying each of these arcsine values by 180 and then dividing by pi. And from the output here, we notice that all the original angles between 0 and 90 have been recovered. But since the sine of 120 degrees is the same as sine of 60 and the sine of 150 is equal to the sine of 30, we see those values listed in this array. We now move on to some other universal functions for which we will create a new array X using the np.arange function. So this contains an array of these 6 elements, and the universal function we explore right now is the exponential or exp function. When we apply this exponential function to the array X, the output will result in an array containing the values of e to the power x. That is, each of the elements in the array X will be applied as an exponent to the Euler's constant or Euler's constant e. The value of e is about 2.718, and as you can see here, this array contains a number of rather large values. Another universal function which numpy provides us is the square root function, which is sqrt, and this will calculate the square root for each of the elements in a numpy array. There is also the median function, which will calculate the median value in an array. So this will sort the array and pick the middle value if the number of elements is odd, or will calculate the average of the middle 2 elements if the array has an even length. In our case, our array contains 6 elements and the middle 2 elements are 14 and 19, which is why the median is calculated as 16.5. Finally, we will perform a number of aggregate operations on a rather large array. For that, we load a bunch of float values from a data set, and to do that, we make use of the gen from text function. So this will generate a numpy array from a text file. The arguments we pass to it include the location of the file, which is in our datasets directory and is called float_values.csv. And we can also specify what the delimiter is between each of the values in that file. In our case, it's a comma. So once we run this cell, we can take a look at the contents of this float_values array. And we notice here that this contains a number of elements, which is indicated by the ellipsis. We can then take a look at the shape of this array, and we observe here that it contains almost 6,000 elements. So we now have a rather large one-dimensional array, and we will use it in order to perform a number of aggregate operations. These include the calculations for the mean, median, variance, and standard deviation for all the values in our array. And the aggregate functions we have not come across earlier include the var function for variance and the std function for the standard deviation. So on running this cell, we are able to get these aggregate values for this rather large one-dimensional array. In this demo, we will be performing indexing and slicing operations on numpy arrays, which are not very different from the indexing and slicing operations on Python lists. We begin as usual by importing the numpy package, and we start off by initializing an array X, which contains the cubes of numbers from 0 through 9. So this powers of 3 array is now ready for us. And the first operation we will perform is to access an element of this array by the index. So just like with Python lists, we use the square bracket notation, and the element at index 3 is the cube of 3, that is 27. Now, just like with Python, we can also access elements from the end of the array. So using an index of -4, we get the fourth from last element of our array, which is 216. So that covers the basic indexing of numpy arrays. We now perform a slice of this array. So here we get the slice of elements from index 1 through to index 7. So these should return the cubes of all the numbers from 1 through 7. We can also use negative indexing while slicing the array. So this will give us all the values from index 3 until the fourth from last index of the array. If we do not specify a starting index for our slice, then numpy will assume that the starting index is 0. So this returns the first 7 elements in our array. And similarly, if we do not explicitly set the end index, it is assumed to be the last element in the array. So this will give us the slice of the array beginning from index 3 through to the end of the array. NumPy also allows the use of the start, stop, and step notation in order to get a slice of the array. So the indexes of this slice of the array will include the start of the array and will go on until the index of 9 in increments of 2. So the slice contains the elements of our array at index locations 0, 2, 4, 6, and 8. When using this notation, we can also specify a negative step value, and this particular slice will contain the elements of the original array only in reverse order. We now move along to a two-dimensional array containing some more meaningful information. This has 3 rows and 5 columns and contains data representing 5 companies along with the year of their founding and the number of employees on their payroll. So once we initialize this array, we can just view its contents. And we see here from the D type of U9 that all of these values have been converted to string. In order to access the first row of the array, we can use a single index. That is, we access the element at index 0, and this returns the row containing all the company names. If we would like to get the data from a specific column, we need to specify a multi-dimensional slice. So for the first dimension, we just say that we would like all of the rows to be picked up. But for the column dimension, we say that we only want the column at index 2. Running this will return the details of IBM, which is at column number 3, or the column at index 2 of our array. If we would like to retrieve the values within a particular cell of our array, rather than get a whole row or column, we can specify the location of that cell in terms of its row and column index. So here, the cell which is at row 0 and column number 2 contains the text IBM. So far, when using this two-dimensional array, we had retrieved either a complete row or a complete column. However, if we would only like a subset of rows and columns to be returned, then we can use this notation where we specify a range of row indices followed by a range of column indices. So running this will return a slice of the array which includes the data in the rows corresponding to index 0 and 1 and the columns 2 and 3. We now take a look at another slice of this array which includes all of the rows and columns 2 and 3. So this returns all the details of IBM and Spotify. Negative indexing can also be used with two-dimensional arrays. So here we return all the columns corresponding to the last row of our array. So this returns the entire row containing the employee count for the companies. And lastly, we explore the use of the ellipsis when it comes to indexing and slicing. So the ellipsis in numpy is used to denote the rest of the array. So in this case, we are getting the elements at row 0, and we specify all the columns by using the ellipsis symbol. So this returns all the company names. And similarly, we can also use the ellipsis in order to denote all the rows in the array. So this will return all the rows corresponding to column with the index 2, that is the details of the company IBM. In this demo, we will explore various options which are available in order to iterate through arrays in NumPy. As always, we will import the NumPy package first, and the array we will first work with contains the cubes of all numbers beginning from 0 through to 9. So for that, we use the np.arange function. And once we have this array, we will iterate through this array first by using the for loop. So we will capture in the variable I the element which is returned in each iteration of the for loop and then print it out. As anyone familiar with Python lists would expect, each of the elements of our array is what is assigned to the variable I at each iteration. We will now make things a little more complex, where we will create a two-dimensional array. This contains 3 rows and 5 columns and contains information about 5 different companies, including their names, the year of their founding, and the number of people they employ. So when we try to iterate over this 2D array, each iteration will return a row of the array. We create a variable I, which we initialize to 0, and this will denote each iteration of the array. So once we execute this for loop, we get the confirmation that each iteration returns one row of this 2D array. We will now perform a flatten operation on our 2D array. So the flatten function is something which will reduce our 2D array into a single dimension, and this will be done row-wise. To understand what that means, we can just execute this cell. We observe that the initial elements of our flattened 1D array is the first row of the original 2D array, followed by the second row, and then succeeded by the third row. Now, if we would like to perform a flattening of the array, but we would like to do that in a column-wise manner, we can make use of the flatten function once again, but this time we specify the value of the order argument to be f. F here stands for Fortran style ordering, that is the Fortran programming language. The previous row-wise order was C style ordering, that also denotes the C programming language. So when we perform our Fortran style ordering, we see here that the original two-dimensional array has been flattened column-wise. Before we perform some more iterations, we create one more array. So this is a two-dimensional array with 4 rows and 4 columns. And once our array has been created, we will iterate through this using the numpy.nditer function. nditer accepts a multi-dimensional array as argument and returns a very efficient iterator for this array. So if we use this iterator for the for loop, we are now iterating through each of the individual elements of this array rather than through each of the rows. You will notice from the ordering of these elements that nditer by default performs a row-wise or C-style ordering. If you would like to perform a column-wise ordering, then we simply call the nditer function by passing the array and then specify the value of the order argument to be f for Fortran style. And as you can see from the output, this does traverse through the array in a column-wise manner. Rather than iterating through the individual elements or zero-dimensional arrays, we can iterate through the rows or columns by making use of the flags parameter for the nditer function. So if we pass in a value of external loop to the flags parameter, and we specify the ordering to be Fortran style, then we will be iterating through each of the columns of this array. Note that the flags parameter accepts a list of flags. So we can specify a number of different flags in order to define the behavior of our nd_iter object. Also, had we performed a C-style ordering, we would have been iterating through the rows of our 2D array. One thing to keep in mind when using the nd_iter object is that the array which is returned by it is by default read-only. This is because it points to the array which is passed as argument to nd_iter, and any changes which will be performed will not be on a copy of the array but will in fact be to the array itself. In this for loop, we calculate the square for each of the elements in our 2D array by multiplying each element with itself. However, when we execute this cell, we get an error, and this is because the array is read-only for us. However, if we would like to update our array, then we can call the nd_iter function by passing it the array and by setting the ops flag argument to be equal to read_write. Note here that the ops flag is also a list, but we are only setting one of the ops flags here. So when we execute this for loop, we get no errors this time, and we can confirm what our num array looks like. And we see here that the square of each of the elements is now available. So we were successfully able to write to our array using the nd_iter object. We have already come across a few operations which reshape an array, such as the reshape function as well as the flatten function. We will now explore some of the other operations which are available in order to change the shape of an array. So once we have imported the numpy package, we define a 2D array using np.array once more, and this time our array will contain 2 rows and 5 columns. This includes data for 5 different companies based in the United States, along with the states in which they are headquartered. So once this array has been created, we can examine the shape of this array using the shape property of the array object. So our array contains 2 rows and 5 columns, which is denoted in this tuple. And the first operation which we will perform on this array is to use the ravel function. So the ravel function is similar to the flatten function, which reduces a multi-dimensional array to a single-dimensional array, except the difference between ravel and flatten is that flatten belongs to an array object and can only be used by numpy arrays. On the other hand, the ravel function belongs to the numpy library and can be applied to any object which can be successfully parsed. The next thing we do with our array is to get its transpose. That is a form of the array where the rows are the columns of the original and the columns are the rows of the original. So the transpose for an array can in fact be obtained from the uppercase t property. So we do not need to call a function, but we can simply access this t property. And we see here that the transpose of the array is available through it. And we can also perform a raveling or flattening of this transpose. And we do that by calling the ravel function, because the transpose of an array is also an array object. So we see from the output that we have obtained the flattened form of the array transpose. So let us just revise the shape of our original array. So it contains 2 rows and 5 columns. And now we can simply perform a reshape function on it in order to reshape it to an array containing 5 rows and 2 columns. So from the output, we gather that the elements have been processed in a C order. That is, they have been processed row-wise. So here, we reshape an array of 18 elements to one containing 3 rows and 6 columns. And this operation is successful because the product of the arguments passed to reshape is equal to the number of elements in the array which is being reshaped. So if we try to reshape this array of 18 elements to an array containing 3 rows and 5 columns, that is an array which has 15 elements, then the reshape operation will fail. We now define one more array containing the names of 8 different companies. So this is a one-dimensional array containing 8 elements. So once this companies array has been created, we are going to perform a reshape operation on it, but this time we're going to specify a negative value for one of the dimension lengths. So when you specify a negative value here, it means that that particular dimension will be inferred by the reshape function. So here we set the number of rows to be -1, which means that the number of rows of the reshaped array will be inferred using the number of elements available and the number of columns which have been specified. So since the number of elements is 8 and the number of columns is 4, the reshape function has inferred that the number of rows in this array should be 2. Similarly, we can perform the reshape operation by specifying a negative value for the number of columns and set the number of rows as 4. And the reshape function is able to infer that the number of columns in this array needs to be 2. However, as always when using the reshape function, one needs to be careful that the number of rows and columns to which the array needs to be reshaped are in fact compatible with the dimensions of the original array. So here, if we try to reshape an array of 8 elements into 5 rows and that the number of columns should be inferred, then this operation results in an error. In this exercise, you will create an array X which has the same shape as another array Y, and all the elements of the array X should be set to 1. This can be accomplished writing one line of code using numpy. You will then write one more line of code, and this will be in order to retrieve a part of an array. So this code should be able to return the last 20 rows and columns 2 through 5, both included, from a two-dimensional array. You will then recall the two primary ways in which a two-dimensional array can be flattened using numpy. And finally, you will imagine that you have made a call to a function which has returned a numpy array. You're not exactly sure what the dimensions of this array are, but you need to reshape it into one which contains exactly 4 columns, and you leave it up to numpy in order to infer how many rows this reshaped array should contain. Tasks 1, 2, and 4 can be performed using exactly one line of code. Do try and perform these tasks all on your own. The first task in the exercise was to create one array X in the shape of another array Y, where all the elements of X are initialized to 1. The way to do that in numpy is to make use of the ones_like function and then pass to it as an argument the array whose shape you would like to mimic. Of course, there are other more indirect ways in which you could have performed the same task, but the use of the ones_like function is the most straightforward and the cleanest way to do it. The next task involved getting a slice of a two-dimensional array, and we do this by specifying a range of rows and columns. The range of rows begins from the 20th to last row and goes on until the end, which is why we specify a start index of -20 and leave the ending index for the rows as blank. And then in order to retrieve columns 2 through 5, we specify a range of 2 through 6. The next task was to list the two main ways in which we can flatten a two-dimensional array. These include the row major or C-style ordering, or the column major or F-style ordering. F-style here references Fortran-style ordering. The last task in this exercise involved reshaping an array where one of the dimensions is not known in advance. In order to get numpy to infer the dimension, we can call the reshape function and then pass in a value of -1 or any negative number for the dimension which needs to be inferred. Since we know that our reshaped array will contain 4 columns, we pass that dimension along to reshape, and then we set the row value to -1 so that numpy can deduce what that value should be. You will know by now, of course, that this reshape operation will only work if the number of elements in the returned array is divisible by the number of columns in the reshaped array. That is, if that is divisible by 4. This dimension inference feature in NumPy is very helpful when you do not know the dimensions of an array which you are getting. However, if you know that the array which you will receive will be of a certain format or will meet certain conditions, then this dimension inference can be used. In this demo, we will be exploring various options which are available in NumPy in order to split the NumPy arrays. So once we import the NumPy package, we will create an array called P, which will contain all the elements starting from 0 through to 11. So this is an array of 12 elements. And the first thing we're going to do in order to split this array is to use the np.split function. And this takes in at least 2 arguments. One is an array, and then it takes in the number of equal parts into which the array needs to be split. So here we try to split our array P of 12 elements into 4 equal parts. And on running this cell, we see that this array has indeed been split into 4 equal subarrays of 3 elements each. Also note that the array has not been split randomly, but has in fact been traversed in order while doing the split. So when we try to split an array of 12 elements into 5 equal parts, we do not end up with 5 arrays containing 2.4 elements, but in fact this operation will throw an error because an even split is not possible. So when we pass in a single numeric value along with an array to the split function, then it returns an equal split of that array. However, if we pass in a list of integers rather than a single one, then the split function will split the array at the index corresponding to the numbers which have been passed in the list. So this operation will split the array into 3 parts. The first part will contain values from index 0 through 2, the second one from index 3 through 7, and the third one from index 8 right up to the end of the array. So if we pass in n index values in the list to the split function, it will result in n plus 1 subarrays. We now move along to a 2-dimensional array, and this array contains a set of US-based companies along with the state in which they are headquartered. So once this array has been created, we are going to perform an H-split or horizontal split operation on it. So a horizontal split will do a column-wise split of the array. The H-split function takes in at least 2 arguments, the first of which is the array which needs to be split, along with an integer or a list of integers. Here we pass in an integer of 2 to specify that we would like this array to be split into 2 equal sections. The H-split function returns each of the subarrays which are created from the split, and these we assign to the variables x1 and x2. Once we run this horizontal split, we will print out our subarrays, and we see here that a horizontal or a column-wise split has occurred. If we now try to perform a horizontal split on our array containing 6 columns, and we try to split this into 6 equal parts, then we are returned an array of 6 arrays, each of these arrays corresponding to 1 column in our original array. If we now try to split our array of 6 columns into 4 equal horizontal divisions, then this operation fails because the number 6 could not be divided by 4. Similar to a horizontal split, numpy also provides a vertical split or vsplit function. This performs a row-wise split of the array which is passed as argument. So if we try to vsplit our array containing two rows into two equal subarrays, then the results are captured in these variables y1 and y2. And then when we print it out, we see here that each of these subarrays corresponds to one row of our original array. We will now cover how numpy can be used in order to work with digital images. So one thing to understand is that digital images are merely multi-dimensional arrays. So how exactly is that the case? Well, you will be familiar with the notion that an image is made up of a number of pixels. The size of the image determines how many pixels it has, and each pixel in an image is shaded in a single color, and this color can be represented in the form of a number. So a combination of all of these pixels, each with their own individual colors, will together make up the image. So when I say that the color of a pixel is represented by a number, it is actually a bit of a simplification. In fact, for a color image, each pixel is represented by three colors. That is, there is a red component, a green component, as well as a blue component. Each of these color components are the ones which are actually represented by a number, typically in the range of 0 to 255. These three values for R, G, and B collectively represent the pixel of an image. So these are the RGB values for a pixel. So what exactly might a pixel look like? Well, if it's a purely red pixel, then the R value for that pixel will be 255, whereas the green and blue values will be 0, as you can see here represented in this tuple. Similarly, a green image will have 255 for the green value and 0 for the remaining two colors. And a blue pixel will simply have the blue component set at 255 while the others are 0. So this is how one represents the pixels in a color image. When it comes to grayscale images, on the other hand, things are a bit simpler, where you have a single number which represents a pixel. So this number is typically in the range 0 to 1, and this value represents the brightness or intensity of the pixel. So a value of 0 corresponds to black, whereas a value of 1 corresponds to white. Very often, a pixel is represented by one byte of data, where its intensity is set to a value between 0 and 255. And once again, 0 corresponds to black, while 255 corresponds to white. All values in between are various shades of gray. So, grayscale images, which have a single number representing each pixel, are referred to as single channel images, and color images are typically multi-channel. An image where each pixel is represented by RGB values qualifies as a three-channel image, since there are three values representing each pixel. So now that we have explained what pixels in images look like, we go back to seeing how images can be represented as multi-dimensional arrays. Since pixels in an image are arranged in the form of a grid, we can quite easily use a two-dimensional array or matrix in order to represent the pixels of an image. Each pixel belongs to a specific row and a specific column, and each pixel can be uniquely identified by a combination of the row and column. Now, for individual pixels, we may either represent them by a single value in the case of grayscale images, or by three values in the case of color images. In any case, we can represent any image in the form of a 3D array or matrix. The number of elements in the third dimension of such an array is in fact determined by the number of channels for the image. In the case of a grayscale image, the length of this third dimension is simply 1, as you only need one value to represent a pixel, while color images have a third dimension with a length of 3, to represent the R, G, and B values. In this demo, we will be using numpy in order to manipulate a color image. Since a color image is simply a three-dimensional array, we can use numpy in order to represent such an image. We will then perform slicing operations using numpy in order to view sections of the image. The first thing we will do though is to install the SciPy package, which is used for image manipulation, and we do that using the pip install SciPy command. In order to execute this from a Jupyter Notebook cell, we need to precede it with the exclamation point. So when I execute this cell, I get this message that the requirement is already satisfied. However, if you don't have SciPy already, you will view some installation steps instead. At this point, we can import our numpy library as well as the ndImage object from the SciPy library. So once that is done, we can use ndImage in order to load a JPEG image into a numpy array. And we do this using the imread function of the ndImage object. So this particular JPEG file is available in the datasets directory. So once you execute the cell, you may see a warning message depending on which version of SciPy you have installed. So although I do see such a warning message, I will ignore it since I'm not using any of the advanced features of imread, which is available in the matplotlib library. So we can now go ahead and take a look at the shape of the array which has been created from our JPEG file. And from the output, we can see that the first two dimensions correspond to the size of the image in terms of the number of pixels. And the third dimension simply represents the R, G, and B values of each pixel. We can quickly confirm the type of this image array object. And we see here that it is simply a numpy array or ND array. So what can we do with this image array? Well, first we examine its contents, and we see here that it looks no different than any three-dimensional array. Now, in order to view an image represented as a numpy array in a Jupyter notebook, we will make use of the matplotlib library and specifically the pyplot object within it. So once this has been imported, we will use the imshow function of this pyplot object in order to view the array within our notebook. So we pass in our numpy array as an argument to this function, and note that you may need to execute plt.show in order to render the plot which has been generated by matplotlib. So when we execute this cell, we can view this rather cute image of a koala within our Jupyter notebook. You can also view from the axes that the size of this koala image corresponds to two of the dimensions of our numpy array. Okay, now that we have an image which can be represented as a numpy array, we can treat it as any other array and perform a slice operation. So our sliced image will contain all the rows starting from row with the index 300. It will also contain all the columns beginning from the one at index 250. And as for the third dimension, which represents the R, G, and B values, we simply retrieve everything so that our slice is a full color image. So running this cell will create a slice of our image, which is also a numpy array. And in order to view it as an image within our Jupyter notebook, we once again use the plt.imshow function. And we can gather from the output that this image is quite literally a slice of the original image. We can now perform a split operation on our original array, and we will be creating two equal splits which will be assigned to the variables x1 and x2. So once we pass in the image to the split function, we will simply view the first subarray which was created, that is x1, and for that we once again use the imshow function. And we see here that this contains the top half of the image. So the split has been performed along the y-axis. And we can now view the second half of our image. So we use imshow to render x2, and this renders the bottom half of the koala image. Now that we have cut the image along the y-axis, we can perform a split along the x-axis, for which we once again make use of the split function, but this time we're going to split it into two halves along the x-axis, and for that we specify the axis argument to be equal to 1. This returns two subarrays y1 and y2, and we render y1 using the imshow function, and we see here that this is the left half of our original image. We can simply confirm that y2 contains the right half of the image by once again using the imshow function, and this confirmation is obtained here. Now that we have split our image, we can also combine the images by using numpy's concatenate function. So this function takes in a number of numpy arrays and it will concatenate them by adding them one below the other. So when we use it with our images x1 and x2, which was split along the y-axis if you remember, then we see here that a whole image has been obtained. However, if we use the concatenate function in order to concatenate y1 and y2, which were effectively split by a vertical line, then the concatenate operation doesn't quite produce the original image. However, we can specify the axis along which to concatenate, and if we set the value of the axis parameter to 1 when calling the concatenate function, then we can reproduce this image of this rather adorable looking koala. In this demo, we will be exploring the concept of views or shallow copies in NumPy. We begin by importing the NumPy library, and we will first create an array into which we will later create a view. So this is an array of 6 countries, and once this has been created, we will go ahead and create views into this array by using the view function of an array object. So we have two views here, which we shall call location 1 and location 2, or loc1 and loc2. And we can view the contents of loc1 here by using the print function. And we see that this displays the exact same elements as in the countries array. When we print out loc2, we see that the output is identical. So are all three of these objects, that is countries, loc1 and loc2, exactly the same? Well, the answer is no, and we can confirm that by printing out their IDs using the ID function. So in this cell, we print out the IDs for each of these three objects, and from the output, we get the confirmation that each of them is different, since the identifiers are all different. Next, we use the is operator to check if the loc1 view points to the same object as the countries array. And running this gives us the value false, which shows us that it is in fact a different object. However, the loc1 object has a base object as well, and we use the is operator to check if this base for loc1 is the same as the countries array. And from the output, we gather that it is in fact the case. The base for the loc2 view is also the same as for loc1, that is the countries array. Now, what will happen if we modify one of the elements in our view? Specifically, in the loc2 view, we replace the country of Nigeria with Ghana. So when we run this, we get the confirmation that in loc2, the element at index 3 is now Ghana and not Nigeria. And what effect does this have on the original countries array? So we just run this cell in order to view the value of countries. And we see here that the countries array has also been modified. So it looks like loc2 is simply a view into the countries array and is not an independent copy. Since loc1 was also a view into countries, we expect that when we view its contents, that Nigeria will have been replaced by Ghana over here as well. And in fact, we get the confirmation that is exactly what has happened. So views in NumPy are clearly connected directly with the arrays out of which they were created. So if we were now to reassign the lock1 variable to an entirely new array, and this is an array containing 6 entirely different countries, what exactly would happen? So once lock1 has been reassigned, we examine the contents of the countries array, and we see that this has not been affected at all. So reassigning the variable for a view into an array has no effect on the original array. Now, what would happen if you happen to change the shape of a view? So here, we change the shape of the log2 view to contain 2 rows and 3 columns. And when we print out its shape and contents, we see that this reshaping has indeed taken place. Now, does this reshaping of a view affect the shape and contents of the original array at all? In this cell, we check exactly that by printing out the shape of the countries array along with its contents. And we see here that the original array has not been affected at all by the change in the shape of the view. So the view can modify the contents of the original array, but we cannot really modify the shape of the original by modifying the shape of the view. Now that we have seen what views or shallow copies of arrays are like, we will explore deep copies in this particular demo. So once we have imported the numpy library, we create the same array as we used in the view demo, and this contains a list of 6 countries. And this time we create a variable called lock, which is created out of a copy of this countries array. And for that, we make use of the copy function. Once this copy has been created, we first check whether it is pointing to the same object as the original countries array by using the if operator once more. And we get the message here that it is not pointing to the same object. We check if the base of this particular deep copy is the same as the countries array. And this time we see that this is not the case. So what exactly will happen then if we modify the contents of this deep copy? So we change the first element in this particular array from India to Turkey. And when we print out the contents of this lock array, we see that India has indeed been replaced by Turkey in this copy of the array. Does that affect the countries array at all? In fact, the answer is no. So it looks like the lock array is independent of the countries array. Now, let us see if modifying the shape of this lock array has any effect on the original. So we set the value of the shape for this lock array to be 2 rows and 3 columns. And then when we print out the contents of lock, we see that this reshaping has indeed taken place. But if we print out the countries array here, we see that this has not been affected at all. So the copy function of an array object simply creates an independent copy of the array, and beyond that, there is no link between the original and the copy. This is what constitutes a deep copy of an array. We have seen previously how we can access subsets of an array by using slices, or how we can access individual elements by using an index value. So rather than using a single index, we can use an array of index values called masks in order to access multiple elements of an array at the same time. This is referred to as fancy indexing, and that is what we will be covering in this demo. We start off by importing the numpy and CSV libraries, and the array we will first create is going to be called X, and this will contain the squares of all the numbers from 0 through 13. Once we have this array of 14 elements, let us use simple indexing, that is single index values, in order to access 4 different elements from our array. So here we print out the contents of our array at index locations 3, 7, 9, and 13. And in the output, we get the squares of the corresponding index numbers. Now, Rather than access these 4 elements individually as we have done here, we can instead use an array containing those index positions. So here, we create an array containing 3, 7, 9, and 13, which is referred to as a mask. So once this mask has been created, we can use that as an index with our original array X. And when we do that, we see that the output which it produces is exactly the same as accessing each of those elements individually. So rather than using single index values, we have specified a list of index values in order to access multiple elements from an array. And this is exactly what fancy indexing is. So now that we have used a one-dimensional list as a mask, what if we create a two-dimensional mask? So for that, we create a two-dimensional numpy array containing the elements 3, 5, 2, and 8. And once this mask has been created, we use that with our original one-dimensional array X. So when this operation is performed, the resultant array will have the same shape as the mask, but it is populated with the elements from the one-dimensional array X corresponding to the index values which were passed in the mask. Moving along, we define a two-dimensional array containing a number of cities. So here we have a set of 9 cities which are arranged in a 3 by 3 array. To access elements from a 2D array, we define two masks, one containing the coordinates of the rows from which we wish to extract the elements, and the other containing the coordinates of the columns. Between these two, we will be able to extract elements from 3 of the corners of our cities array. So we use the cities array and we use these two 2D arrays as indexes. And what we get is elements from 3 of the corners. So how exactly did this work? Well, the element Sydney was available in row 0 and column 0 of the cities array. The value of Vancouver was obtained from row 0 and column 2. The value of Istanbul was in row 2 and column 0. So the shape of this resultant array is the same shape as each of the masks. Just to confirm, when we are using these two-dimensional arrays, we can access the individual elements even using regular index values. So here we get the value at row 1 and index 2 of our cities array, and that is Lisbon. Now, we can also use fancy indexing to modify the contents of our array, that is to set values, not just to read them. So here, we use the fancy indexing with our two masks for the rows and columns in order to overwrite the values in these 3 corners to the string of 4 A's. So once we run this cell, we see that our cities array has now been modified with these new values. Now that we have used a mask in order to modify our 2D array, let us confirm that we can use a mask in order to modify a one-dimensional array as well. So this mask underscore 1, which we had created earlier, contained the values 3, 7, 9, and 13. And we now use this in order to modify our X array, and we set the value of 999 in each of these positions in the mask. And once we execute this cell, we get the confirmation that our one-dimensional array has also been modified with the mask. In this demo, we will be applying a lot of what we learned about indexing with numpy arrays on a real data set. To begin, we will import the numpy library and will also use the Pandas library in order to import and play with a two-dimensional data set. We will also make use of matplotlib in order to visualize the data. So once we have imported these libraries, we can go ahead and read in this data set. This countries of the world dataset provides plenty of information about all the countries of the world, and we will soon see all the information which it contains. So we use the read underscore CSV function of the pandas library in order to read the CSV file and load it into something called a Pandas data frame. The argument to this function includes the location of the CSV file, which is there in our datasets folder. And one thing about this dataset is that for all the numerical fields, it uses a comma instead of a decimal point rather than a period. This notation is standard in many European countries, but it is not the case with Pandas, which is why we need to explicitly ask Pandas to use a comma as a decimal separator. The read underscore CSV function will return something called a Pandas data frame, which is a two-dimensional or even tabular representation of the CSV file. We will use the head function of this data frame object in order to view the first 5 rows of data. So once the data frame has been loaded, we can see from this preview of the first 5 rows that Pandas has effectively rendered this file in the form of a table. There is a lot of data available for each of the countries here, including its population, its area, the coastline it has, and so on. But the data we are interested in for now is the one at the extreme right on your screen, which is the birth rate per 100,000 people in a country. So in order to access this one column of data from a Pandas data frame, we can treat it similar to a two-dimensional numpy array and then reference this particular column by its column header. So the column headers of a Pandas data frame can be treated the same way as we would the index label of a numpy array. This is because Pandas is actually built on top of numpy, and a Pandas data frame is merely an abstraction on top of numpy arrays. So in order to access the birth rates column from our Pandas data frame, we reference the column by its column header, and we use the .values property in order to access the individual values in that column. So once the values from the birth rates column has been assigned to this birth rates variable, we can go ahead and check what the type is for this object. And as it turns out, this is actually a numpy array. And this confirms the fact that Pandas is built on top of numpy. We can check the shape for this array, and this array contains 227 values, which corresponds to the number of countries represented in this dataset. We will now make use of matplotlib in order to view the distribution for this data, and we can see from the plot that the value of birth rates ranges from a little under 10 to about 50. So just to clarify, the value of birth rates is equal to the number of new births in that country per 100,000 people in its population. We can check what the median value is for the birth rates for the countries in our dataset, and for that we make use of the np.median function. And we get a warning over here, and the returned median for the birth rates is calculated as nan. That is, it's not a real number. So what exactly is going on here? For that, let us take a closer look at our birth rates numpy array. And we can observe here that it contains a handful of nan values. So these were instances where the birth rate data was not available for the country, and the corresponding entry in our dataset was either blank or was a value which could not be parsed. So how exactly do we handle this situation? For one, we can eliminate the rows in our dataset where the value for the birth rates is null or nan. The way we do that is by making use of the numpy isNan function. So this will check whether a particular value is null, and we make use of the negation sign, that is the tilde character, in order to include only those values in our numpy array where the value is not a nan. So we update the birth rates array by eliminating all the nan values, and then we can inspect its contents, and we can visually get the confirmation that there are no nan values here. To get a real confirmation, we examine its shape, and we see here that it contains 3 fewer elements than it did previously. So now that the nan values have been removed from this numpy array, will we be able to calculate the median for the birth rates? So we make use of the median function once more, and this time we get the value of 18.79 as the median value for the birth rates. So handling NaN values is a crucial part when working with any real data sets. Here we eliminated the NaN values entirely, but it's also possible to substitute the NaN values with any value you see fit. Now that we have calculated the median, let us see if we can get the mean value for the birth rates. And this is a little higher than the median, which is 22.11. Since we are treating this birth rates array as any other numpy array, we can also calculate the number of countries where the birth rate is less than 20 per 100,000. And we do that by applying a condition. So here we make use of the count underscore non-zero function in the numpy library, which counts the number of non-zero elements in a numpy array. The numpy array we use here is one which only contains all the birth rate values less than 20. So there are 117 countries in our dataset where the birth rate is less than 20. And at this point, we can examine the birth rate values which are the lowest in our dataset. In order to do that, we make use of numpy's sort function, and we specify that once the birth rates array has been sorted, we only wish to view the top 20 elements. Since the default sort is in ascending order, we will see the 20 lowest birth rate values here. So when we execute this cell, we see that the lowest birth rate value is 7.29, and that there are at least 20 countries where the birth rate is less than 10. We now create a numpy array which contains all the birth rate values greater than 40. And from the result, we get all those values in the array which are higher than 40. We then make use of the count non-zero function once more. And this time, we just wish to count how many countries there are where the birth rate is between 30 and 40. And we get the result that there are 32 countries where the birth rate per 100,000 people falls within this range. So when working with any real data set, even in the form of a CSV file, we can simply extract individual columns from the dataset in the form of a numpy array, and then make use of the numpy library functions and other operators in order to examine that data. Previously, we have covered the concept of fancy indexing in NumPy with masks. In this particular demo, we will be focusing on Boolean masks, that is, masks which are Boolean arrays. We begin as usual by importing the NumPy library, and then we create an array containing 12 elements in the shape of 3 rows and 4 columns. Let us examine what this array looks like now. And we can see here that it contains the numbers 0 through 11 spaced out in 3 rows and 4 columns. Now, we can create a Boolean array in the same shape as the X array. And for that, we just put in the condition X is greater than 6. When we examine index underscore bool, we notice that it has the exact same shape as X, but it contains true or false values depending on whether the element in the corresponding position in X satisfied the condition of being greater than 6. Now we can make use of this particular Boolean array and use it as a mask with our original array. And what this does is it returns a one-dimensional array which contains all the elements in the target array which correspond to the positions of the true values in the mask. What this boils down to for us is that we end up with a one-dimensional array which contains all the elements of our target array X which satisfy the condition which we had applied of being greater than 6. We can obtain the same array by using a more direct route where we simply apply the condition of X is greater than 6 and use that as an index with our array X. So this will automatically apply the Boolean mask to the array. Now, Let us see what happens when we apply the condition x is less than 7. And then this returns an array of the same shape as x, and it contains the corresponding true or false values depending on whether the element is less than 7. With this array, we can perform a few operations. So here, we check the number of non-zero elements in this array, and we see that this Boolean array contains 7 non-zero elements. So all the true values are calculated as 1, and the false values are calculated as 0. To confirm that the true values are computed as 1, we can just sum up all the values in this particular array, and we get the number 7. That is 1 for each true value in the Boolean array. Now, rather than calculating the sum across the entire array, let us count how many true values there are in each row of the Boolean array. So we pass the Boolean array x is less than 7 as an argument to np.sum once more. But this time we also pass in the axis parameter and set it to 1 so that this operation is performed on each row. And this returns not a single number but an array corresponding to the number of rows in our dataset along with the number of true values in that row. We now make use of another numpy library function, which is the any function, which returns a true or false value and is used to check whether there is any element in the given array or the given axis of an array which evaluates to true. In this case, we pass an entire Boolean array as an argument to numpy.any, and this will tell us whether there is a single true value in the array. In effect, it will tell us whether there is any value in the array which is greater than 8. And running this cell does give the confirmation that the array X does contain at least one value greater than 8. Complementing the any function is numpy's all function, which checks whether all the elements in a given array are evaluated as true. So here we check whether all elements in X are less than 11, and we get the answer as false. So you can think of the any function as being the equivalent of an OR operator, while the all function is the equivalent of the AND operator. Now let us check whether all the elements in X are less than 50, and we get the answer as true, as we would expect. Both the any and all functions can be performed for individual axes as well. So here we check whether all the elements in each row of X is less than 10. And to perform a row-wise operation, we set the axis is equal to 1. And we get the result that the first two rows contain all elements which are less than 10, whereas that is not the case with the third row. In this demo, we will be making use of structured arrays in NumPy, which are very useful when one wants to store heterogeneous data. We begin as usual by importing the NumPy library, and then we will go ahead and create 3 lists, which we will use in order to create a 2-dimensional NumPy array. Each of these lists corresponds to what will become a column in our 2D NumPy array. The first column contains the names of some employees in a fictitious company. The second one contains their employee IDs. And the third one contains their scores in some test. Note that there are 6 employees for whom we are storing this data. The next thing we will do is to initialize our structured array, and we do that by making use of the numpy zeros function. Here we say that our structured array will contain 6 rows of data, and then we define the number of columns as well as the format of the data within those columns within the dtype parameter. This dtype is a dictionary, and it contains 2 keys, the names and the formats. The value of names is a tuple corresponding to the names of the columns, and the formats is also a tuple which corresponds to the types for each of the columns. The name column is going to be a 16-character Unicode string. The ID column is going to be a 4-byte integer. while the score column is going to be an 8-byte floating point value. So running this cell creates our mdata array, and we can see here that it is in fact a list of tuples, and they're all initialized to 0, or in the case of the string, it is a blank string. Now that we have an empty structured array, we can populate it with all the data which we had defined earlier in the Python lists. So we reference each of the columns by their names, and then we set their values to each of those lists which we had created. And then when we view this mdata array, we can see that it is still a list of tuples, but the tuples have now been populated with all the data from our list. To view the contents of each column, we can simply reference them by their column headers. So here we check the contents of the name column, and all the names are now visible to us. Similarly, let us confirm the contents of the ID column, and we see the employee IDs have been populated here. And finally, let us examine the scores in the test for each of these employees. And these numbers are also available from our structured array. Now that we have accessed the columns of our array, how exactly do we access the rows? Well, we just use the row index over here. And when we examine the row with index 2, we get the details for the employee Manuel. We can also use negative indexing, and we will do that along with the column header in order to get the data from a particular cell. So here we get the name of the employee in the second to last row of our structured array, and this turns out to be Teresa. To get Teresa's score in the test, we simply reference the score column in her row, and we get the value of 96.2. We can also get information from structured array based on specific conditions. So here, we would like to get the names of all employees where their score is greater than 85. So we first retrieve the full rows for all the employees whose score is greater than 85 in the test. And then from the return rows, we only get the name column. So these are the 3 employees who scored greater than 85 in the test. We'll then retrieve the names of all the employees who scored less than 75. And this returns just the single employee name of Lorena. So we have now seen how we can work with structured arrays in NumPy. We have covered how a lot of operations on NumPy arrays take place on an element by element basis. This works quite seamlessly when the two arrays being operated upon have the same dimensions. However, there will be occasions when we need to perform operations between two arrays which do not share the same shape. This is where we need to use the concept of broadcasting in order to perform operations between mismatched arrays. So broadcasting is a technique where we can perform arithmetic or other operations between two arrays where the shapes are different, and this works in effect by broadcasting the smaller array until it matches the size of the larger array. Do note that broadcasting will not work with every single array, and that there are certain restrictions on the shapes of the arrays. However, the two arrays which are being operated upon need not be of exactly the same shape. So, what types of broadcasting is possible in NumPy? Well, if we are performing an operation between a NumPy array and a scalar quantity, then broadcasting will always work, and this is because the scalar will simply be broadcast across the entire array it is being operated with. We will see exactly how that works in just a little bit. When we are performing an operation between two arrays of different shapes, then the smaller array is effectively broadcast across the entire larger array. However, this only works under specific conditions of the shapes of the two arrays, which we will cover just a little later. So how exactly does broadcasting of scalars work? For that, consider a multiplication operation which we perform between this one-dimensional array of 8 elements with this scalar quantity of 20. So in this case, we have some array which has 8 elements. And in order to perform an element by element multiplication, it needs 8 other elements. And in the case with this scalar, we only have 1. So this is where the scalar needs to be broadcast across the entire array it is being operated with. You can think of this as numpy creating an array which has the same shape as the array being operated with, and each element of this array will have the same value as the scalar quantity. So in this case, we end up with two arrays of compatible shapes, and we can perform an element by element multiplication in order to give such a result. So when some array is multiplied with some scalar, then the result is an array which has the same shape as some array. Operations with scalars also work with multidimensional arrays, where the scalar is simply broadcast to the shape of the array it is being operated with. So this is how broadcasting works between arrays and scalars. To understand how broadcasting works when the two operands are arrays of different shapes, let us revisit the definition. So broadcasting essentially describes how numpy handles arrays of different shapes during arithmetic operations. Operations, as we have seen, are performed between pairs of arrays with the same shape on an element by element basis. While there are no restrictions when it comes to broadcasting scalars, broadcasting of arrays only takes place under certain constraints. To be precise, two arrays are said to be compatible for broadcasting after the shapes of these two arrays are compared on an element by element basis. What exactly does that mean? Well, consider one array on the left here which has 3 rows and 8 columns, while the array on the right has 3 rows and a single column. We see here that the single column of the array on the right can be broadcast 8 times in order to match the shape of the array on the left. So when we compare the last dimensions of these two arrays, that is 8 and 1, we say that these dimensions are compatible. Also, the second dimensions are both exactly the same, so those are compatible as well. As a result, these two arrays with 3 rows and 8 columns and 3 rows and 1 column are said to be compatible for broadcasting. On the other hand, if you were to replace the array on the right with one which has the shape 3, 3, then these two arrays are not compatible. That is, 3 is not compatible with 8. If we replace this array on the right with 1, where the shape is 4, 1, then the last dimensions match, that is 8 and 1 are a match. However, the second dimension is not a match, which is why these two arrays are not compatible for broadcasting. So just to revise broadcasting, we saw that the constraints when it comes to broadcasting of arrays is that when the shapes of each of the arrays are compared element-wise, then the individual dimensions must be a match. The dimensions are considered in reverse order, starting with the last dimension and working their way towards the first dimension. And when the arrays are compatible and the smaller array is broadcast, this does not involve the making of any copies of the array. As a result, this is very efficient from the point of view of computation as well as memory. Broadcasting of the smaller array only works when the corresponding dimensions of the two arrays being operated upon are compatible. That is, these arrays have compatible shapes. Now, two dimensions are said to be compatible when they are either identical or when one of those two dimensions is equal to 1. So broadcasting provides a lot of flexibility when working with numpy arrays, since operations can be performed between arrays of different shapes. By not creating multiple copies of the smaller array, broadcasting is also very memory efficient. And under the hood, a lot of the broadcasting operations are implemented in C rather than in Python, which makes it very computationally efficient as well. And just to summarize the different types of broadcasting, we saw that scalars are in fact very easy to broadcast. Simply need to replicate one element across the array it is being operated with. There are no constraints when broadcasting with scalars, and they will work with arrays of any size. However, when we are broadcasting arrays, then the shapes of the two arrays being operated with need to be compatible. In order to check for compatibility, the dimensions of the two arrays being operated upon are compared starting from the last dimension and moving towards the first one. In this demo, we will cover the concept of broadcasting in NumPy. So broadcasting is something which allows arithmetic operations between arrays which have different shapes. And it allows this by effectively replicating the smaller array to fit the shape of the larger array. In other words, the smaller array is broadcast until it matches the shape of the larger one. So let us explore how that works by first importing the NumPy library. And then we create two arrays, which are one-dimensional arrays of identical size. So each of these contain 5 elements. And then let us go ahead and perform an arithmetic operation, that is a multiplication between these two arrays x and y. As we know already, this results in an element by element multiplication of the contents of each of these arrays, and we end up with an array of the same shape as x and y. Next, we create a scalar value z, which is also a zero-dimensional array. If we go ahead and multiply the array x with z, we then end up with an array which contains the same number of elements as x. So what has happened over here is that the scalar value z has been broadcast to match the shape of the array x, and then an element by element multiplication was performed. So this is what broadcasting is. To see further examples of how this works, we can create a two-dimensional array containing only ones, and this has 3 rows and 4 columns. If we multiply this array by the scalar quantity z, we end up with an array with the same shape as our array of ones, and each of the elements have been multiplied by z. So broadcasting does work with both one-dimensional as well as two-dimensional arrays, and will work with arrays of any dimension. However, there are certain restrictions which we will cover just a little later. We move along now and create some more data which we will use to populate a two-dimensional NumPy array. So we create two lists over here, one containing the top speeds of some cars in kilometers per hour, and the other containing the weights of these cars in kilograms. We will then go ahead and create our array car info, which is a 2D array containing both the top speeds as well as the weights in metric units. So we just confirm here that this is a 2D array containing 2 rows and 6 columns. And then we will go ahead and create one more array called conversion factors. And this contains the values which we can use to convert the metric units in the 2D array into imperial units. So once this array has been created, let us go ahead and examine its shape. And we see here that this is a one-dimensional array containing 1 row and 2 columns. So let us see how this compares with our car info array, and this has 2 rows and 6 columns. To convert the values in our car info array into miles per hour and pounds, we can just try to multiply the car info array by this conversion factors array and see if conversion factors is broadcast to assume the shape of car info. And when we try that, we get this value error, which says that the shapes of these two arrays are not compatible. This is because when broadcasting, NumPy will check the dimensions for each of these arrays, beginning with the last dimension, and the dimensions are said to be compatible if they are both exactly the same value, or if one of them is 1. The last dimensions in our arrays represent the number of columns, which is 6 in the case of car info and just 2 in the case of conversion factors. So they are neither equal nor is one of them 1. So in order to make these arrays compatible for broadcasting, we can just go ahead and reshape the conversion factors array and then make it one which contains 2 rows and 1 column rather than 1 row and 2 columns. So we create a new factors array, which is going to be a reshaped version of the conversion factors array. And once we have this in place, we just go ahead and confirm its shape. And this one now contains 1 column, which is compatible with the 6 columns for our car info. And both of these arrays contain exactly the same number of rows, which is 2. So we can now go ahead and perform the multiplication, as these two arrays should be compatible. And in fact, we now get the values in imperial units when we perform the multiplication. So broadcasting is a very useful feature in NumPy, but as with some of the other operations, we need to be careful with the shape of the array which we are using. In this exercise, you will take in an array X, and then from it, you will create a new array which contains all the elements of X which happen to be greater than 100. There are many ways to do this, but you should try to use the most simple and straightforward technique in order to get this result. Next, you will take in another array X which contains exactly 20 elements, and using these, you will create 3 other arrays. These will effectively be subarrays of X, and the first subarray will contain the elements of X which begin from index 0 right up to index 6. The second subarray will contain the elements from index 7 through to index 16, and the final subarray will contain the remaining elements of X, that is from index 17 through 19. There are many different ways to solve this problem, but there is a simple, straightforward, single line solution as well. And that is what you should be aiming for. And finally, you will need to recall the different conditions under which an operation can be performed using NumPy arrays of different shapes. While there are no restrictions when applying some mathematical operation between an array and a scalar quantity, when an array is being operated with another array of a different shape, there are specific conditions which need to be met, and I would like you to think of what those are. Do try to perform each of these tasks on your own. The first task involved retrieving all the elements from an array X whose value was greater than 100. The simple way to do this is to make use of a Boolean mask, and that Boolean mask can be applied as an index to the array. So in this case, we use the array X, and then within the square brackets, we apply a Boolean mask. This Boolean mask is an array which has the same shape as X and which contains true values for the elements which we would like to retrieve and false everywhere else. The simplest way to do that is to simply apply the condition X greater than 100. This is an example of fancy indexing in NumPy. The next task involved creating 3 subarrays out of another array X which contained 20 elements. The simple way to create such a subarray is to make use of NumPy's split function. The arguments we pass to the split function include the array which we need to be split, along with a list which specifies the points at which the split should occur. The first subarray will always begin at index 0 of the array to be split, while the other subarrays will start at the split points which are given in the list. So the code which you see on screen will create 3 subarrays A, B, and C. A will contain elements from index 0 through 6 of X, B will contain elements from 7 through 16, and C will contain the remaining elements of X. The final task was to recall the conditions in which 2 arrays of different shapes can be operated upon. So this is where we need to apply the broadcasting rule so that the smaller array can be broadcast to fit the shape of the larger array. The way to do this is to compare each of the dimensions of the two arrays being operated upon, and we begin from the last dimension and move one by one until the first dimension. Two arrays are said to be compatible for broadcasting if the corresponding dimensions are either exactly the same or if one of those dimensions is 1. Hello, and welcome to this course on Pandas for working with tabular data. We begin by taking a look at some of the software one needs to be familiar with in order to do this course, along with the skills which one may require. First of all of the demos in this course will be coded using Python 3. So it helps if you are comfortable programming in this language. The dev environment we will be using is Jupyter Notebooks, and familiarity with that interface will also be helpful. In addition, if you have used a library such as numpy or matplotlib before, this will greatly ease your understanding of pandas. Since pandas provide some very fundamental data structures and the tools in order to manipulate them, it has become an essential building block for a lot of the data science and data visualization libraries available. For example, Seaborn is a data visualization library which makes significant use of pandas. Bokeh is one more visualization tool which is specifically meant for large data set, and this also uses pandas under the hood. Plotly is a very useful tool in order to create interactive figures which can be easily shared over the web, and this also makes heavy use of pandas. Stats model is also a popular library for performing statistical operations, and this also makes use of pandas. And then there is scikit-learn, which is specifically meant for machine learning and also for data mining and data analysis. This also provides integration with pandas. These libraries and many others which make heavy use of pandas or provide integration with it all make up part of the pandas ecosystem. We'll now quickly summarize some of the features of pandas. So the pandas package in Python is a very popular package in the world of data science. This is because it provides a very convenient data structure of a data frame which effectively models the rows and columns in a table of a relational database. Pandas is also specifically designed to make it easy to work with relational data, and it does this by providing an array of helper methods which can be used for common operations on tabular data structures. And Pandas is also built on top of the numpy package, which works with data in the form of arrays. And there are also a number of visualization libraries which make use of pandas. Throughout this course, we will be using Python 3 in order to develop our applications, and we will be using Jupyter Notebooks as a development environment. Jupyter Notebooks are an interactive web-based dev environment which is very popular among Python developers. It allows us to execute sections of code in our applications and immediately view the results of their execution, rather than having to write the entire code for an app before being able to execute and view the results. So here we bring up our Jupyter Notebook application by typing Jupyter Notebook on the terminal. And we do this from the root directory of the workspace we want to use for this course. And depending on your configuration, the Jupyter Notebook app should pop up in your default web browser. But if it does not, you can simply copy this URL which comes up in the terminal and then open up your browser and then paste that URL in the address bar. You should then be able to view the contents of your workspace directory in the browser. And you see here that I already have a datasets directory created here. Navigating into it, there are a number of CSV files which we will be using as datasets for some of the demos later on in the course. So navigating back up to the root of the workspace, we can just go ahead and create a new notebook. So I'm going to create Python 3 notebook over here. And once the notebook is up, the first thing I'm going to do is to rename this to something more meaningful. So I'm just going to call this Introduction to Pandas. And with that done, the first thing we need to do is to install Pandas. So we do that by running a pip install command. And when executing any shell commands from a Jupyter notebook cell, we need to precede it with an exclamation point. Executing the cell shows me that I already have Pandas installed. So if you do not already have it, you will see the installation steps here. Once Pandas has been set up, you can import the Pandas library, and we can also import the sys library in order to view some of the system information. So in the off chance that you run into some kind of compatibility issues between Pandas and Python, you can just ensure that you have the same versions of both as I do. So in a Jupyter notebook, we can look at the version of Python by checking the value of sys.version. And printing this out shows that I currently have Python version 3.7.0. We can now check the version of Pandas, and for that, we can check the pd.version field. And I currently have 0.23.4 of Pandas. So once that is done, we can go ahead and start creating data to use in Pandas. The first bit of data we create is a Python list called data, which contains all the days of the week. So these are strings. And once we create this list of strings, we can create our first Pandas object. This will be a Pandas series object. And this is not that different from a Python list. The main difference being that a Pandas series index can be a label. That is, it can also be a string and not just a number representing the position of the data in the series. So once this series object called week has been created, we can examine its contents. And you see here that an index has automatically been created for us, which represents the position for each of the data points in our series. And the data in our list has now become the data for this Pandas series object. So we have now successfully built a Pandas series object out of a Python list. We can also create a Pandas series object from a numpy array. And this is fairly straightforward because Pandas is actually built on top of numpy. That is, it is an abstraction on top of numpy arrays. So in order to first create a numpy array with which to create a series object, we import the numpy library, and then we create a numpy array containing a set of square numbers. So we use the np.array function in order to initialize a numpy array from a list of data. And once our array has been created, we can create a Pandas series object by calling the pd.series constructor and then passing as argument our square numbers numpy array. And just like when we created a Pandas series from a Python list, the series object automatically has an index created for it, and then it is populated with the data which we supplied. We'll now move along to defining our own index for a Pandas series object, and this is where it differs from a Python list. In our Pandas series object, we're going to store the information about certain employees, and these are the fields for each of the employees which we will store the data for. These will become the values for the index in our series. So we first initialize a list containing these employee fields. So once we have created these fields, we specify the data which will be in our series object. And this is also going to be a Python list for now. So we store the data for an employee, Susie Schneider. We then go ahead and create a series object. And this time when we call the series constructor, we specify that the index for the series is going to be our employee fields. And then the data for the series is going to be our employee data. And on creating the series, we see here that the index is no longer numeric, but in fact contains the fields which we had initialized it with. As we have seen previously, the data for the series is the contents of the list we had loaded it with. Now there is another way in which we can specify the index and data when creating a Pandas series object. So far we have used two lists in order to denote the index and the data values, but we can also use a Python dictionary in order to do so. In this dictionary, the keys become the index values and the values become the data points within this series. We once more called pd.series in order to create a Pandas series, and we just pass in the dictionary of country capitals. And when we run this, our series has been created once more, and as mentioned, the keys become the index values and the values in the dictionary correspond to the data in the series. Now that we have created Pandas series objects, how do we access the data they have been loaded with? One way to access the entire data in the form of an array is by accessing the values property of the series object. So when we do that with our country capital series, we get an array of each of the country capitals we had loaded the series with. And we can see here that the type is an array. But exactly what type of array is it? For that, we use the type function in Python to check the type for this particular array. And the output confirms for us that Pandas is indeed built on top of numpy, since the data in this Pandas series is a numpy nd array object. We will now access the index for our Pandas series by using the index property of the series object. And running this returns to us each of the fields in our index in the form of an index object of Pandas. This index is simply an immutable ND array object. So we have now successfully made use of the values and index properties of a series object in order to access the entire data and index values of a Pandas series. What if we simply want to access one data point from our series object? Well, just like with any list or array, we can access a particular data value by using its corresponding index position. So in our particular series, we try to get the data value in the index position of 0, and this returns to us the data point in the first position in our series, which is Kabul. Just like with Python lists or numpy arrays, we can also get a slice of a Pandas series object, and for that we once more use the numerical positions of each of the fields. So here we create a slice beginning with the index position of 1 right up to the index position of 4, and when we run this cell, we see that this returns not just the data but also the index corresponding to the positions in our slice. Now that we have accessed data in our series object using their numerical positions, let us see if we can use the actual index values as well. So here, we want to get the data corresponding to the index position China. That is, we want to access the capital of China from our series. And this returns to us the answer we were looking for, which is Beijing. So we have managed to extract data from individual cells in our series using the index labels. But if we would like to retrieve multiple data points from our series using the index labels, for that we simply pass in a list of the index labels for which we would like to retrieve the corresponding data. Here, we wish to see the capitals for the countries of Afghanistan, France, India, and the United States. And what Pandas returns to us is in fact the full series, including the index and the data at these points. So with that, we have now covered how we can create and then work with Pandas series objects, how we can access elements by their positions using the position indexes, as well as specifying our own custom index and then accessing the elements using that. we now explore the fundamental data structure in Pandas, namely the data frame. So a Pandas data frame is essentially a two-dimensional data structure and contains a number of rows as well as a number of columns. For a lot of people, it is convenient to think of data frames as a type of table. Now, each data frame has an index which mostly serves as a unique identifier for each row in the Pandas data frame. So, what exactly does a Pandas data frame consist of? Well, the components include the data which populates each cell in the data frame. There is the index which is used to identify each row. And then we have the columns which are identified by the column headers. So while the data within a particular column in a Pandas data frame must be of the same type, we can have different types of data in different columns. The headers of a data frame column can be thought of as index labels, which is why columns are often referred to as the labeled axes of the data frame, while the rows are the numbered axes. However, it is also possible to have index labels for each row of a data frame. In Pandas, it is possible to add new columns to a data frame after it has been created, and we can perform arithmetic operations by referencing entire rows as well as entire columns. As touched upon previously, the data within a particular column must be of the same type, though different columns can have different types of data. And these are just some of the data types which we can have in Pandas. In addition to a lot of the standard data types such as int or float, we can also have composite data types such as lists, dictionaries, and Pandas series within the individual data frame cells. And in fact, we can even have an entire Pandas data frame within the cell of one data frame. Now that we have covered what Pandas series objects are, specifically one-dimensional representations of data, we move along to Pandas data frames, which are a representation of data in the form of a rectangular grid and can also be thought of as a tabular representation of data. To begin this demo, we create a new Jupyter notebook, and I have named it pandas_dataframe. And we start off by importing the pandas library into our code. After that, we can create our first data frame, which will in fact be an empty data frame. And we do that by making use of the data frame constructor. So this is going to create an empty data frame for us. And when we print it out, we see here that the columns of this data frame are empty, and even the index is empty. So when we initialize a data frame using its constructor, we need to initialize it with certain values if we want our data frame to be populated. So to do that, we first create some data which we can load into our data frame. And for that, we create this particular list containing a number of prominent 20th century political figures. So once we have our list of political figures, the next thing we do is to once again call the pd.dataframe constructor, but this time we pass along our list as an argument to this. When we view our data frame this time, we can see here that it contains all the data we loaded it with, and there is also an index for each of the rows beginning from 0 and going on until 6, and there is also an index for the single column. That is, there is a column with an index of 0 as well. So we have now successfully created our first data frame and populated it with data, and the data was loaded in the form of a Python list. The next thing we will do is to create a data frame from a list of tuples. For that, we will create another Python list called countries, which will be populated with a list of 7 countries. These nations, in fact, correspond to the countries of origin for each of the political figures we had defined just previously. And we can create a tuple for each of these countries and political figures by using the zip function. So the zip function takes in 2 lists as argument, and it will map the values in the corresponding positions of each list into a single tuple. We then call the list function in order to convert this data into a list of tuples. So what does this data now look like? Well, as you can see here, each tuple contains the name of the political figure along with the country of origin, and then we have a list of such tuples. Now, we once again make use of the data frame constructor, and this time we pass in our list of tuples as an argument. And when we view this particular data frame, we see here that it contains two columns this time, one for the political figure and the other for the country. And as before, we also have 7 rows of data. The index for both the rows and the columns are by default numeric and represent the positions of each of the rows and columns. Now, we will reload the same data into a data frame, but this time we will specify names for each of the columns in our data frame. So our first column is going to be called politician name, and the second one will be called country. And when we create the data frame this way, we see here that our numeric index for the column has been replaced with the column headers which we have specified. So we have now successfully created a Pandas data frame by using a list of tuples where each tuple corresponds to one row and each value in the tuple corresponds to a column. Let us now revise what each of our lists look like. So there is a political figures list and the countries list which we have created. So we just recreate them here. And then we will create a new data frame, but this time by using Pandas series objects. And to do that, we will make use of a Python dictionary where the keys of the dictionary will correspond to the column names and the values will correspond to the series objects which contain the data for those columns. So here, the keys in our dictionary are politician name and country, and the values are the Pandas series objects created from the lists corresponding to the political figures and countries. So with this dictionary created, we will once again create a new data frame using the data frame constructor and pass it our dictionary, which contains the column headers as keys and the series objects as values. And we have recreated the same data frame which we did previously using the list of tuples. So at this point, we have covered multiple ways in which we can create Pandas data frames. We can create them from lists of tuples and also from Python dictionaries. Another way to create a Pandas data frame is to load data into it from a CSV file. However, we will first examine how we can export data in a Pandas data frame which we have created into a CSV file. And for that, we simply make use of the to_CSV function, which is available for each Pandas data frame object. So here, we need to specify at least one argument, which is the location of the output file. So we will create a file called politicians.csv within the datasets folder of our workspace. And the index argument is used to specify whether we want the index to be exported into the file as well. Here, we do not want the row index to be exported into the file, so we set this value to false. However, the column index or the headers will be exported in this case. That is referenced by a separate argument called headers. Okay, so we just run this cell and our data has been exported into a CSV file. To view it, we simply navigate into the datasets directory, and we can do that from the Jupyter Notebook interface. And we see here that this politicians.csv has been created here. We can now navigate back to the root of our workspace and then head back into our Jupyter Notebook. And this time, we will create a new data frame called politicians.df from file, and we will load it with the data from our recently exported CSV file. So for that, we make use of the pandas read_csv function, and we specify the location of the file from which we would like to load the data. So if we simply run this cell, we have recovered the data which we had exported into the CSV file. We can now demonstrate the use of the read_CSV function to read in an entirely new set of data, one which wasn't exported by us. And the dataset we will load here is the avocado prices dataset, which is available within the datasets directory. So we execute this cell in order to populate our avocado data frame, and then we view its data. And we see here that this contains over 18,000 rows and 14 columns worth of information. And with that, we have now covered many of the ways in which we can load data into a Pandas data frame. So far, we have covered how we can create Pandas data frames and then load data into it. We will now explore how we can add and remove data from a data frame which has already been created. For that, we create a new Jupyter notebook, which I have named Add and Delete. And then we can begin by importing the Pandas library. Once that is done, we create a data frame which we can play with. And for that, we simply make use of the Pandas read CSV function and create a data frame out of the politicians CSV file which we had created previously by exporting data. So once we have created this data frame, we can just view its contents. So it contains 7 rows and 2 columns, and it contains the names of prominent politicians from the 20th century, along with the country they're associated with. Now, if you would like to add a new column to this data frame, we can simply make use of the notation similar to adding a new key and value pair to a Python dictionary. Here, we wish to add a column called year of birth to our data frame, and we can simply reference this column by the column header. If this column does not already exist, it will simply create this column as a new one. We can also initialize the values of this column either by passing a list of values, or in this case, we set every cell in that column to the same value by passing in this scalar value of 1900. So when we execute this cell, we see that a new column has been added to our data frame, and all the cells in this column contain the same value of 1900. Now, rather than using a scalar quantity in order to populate the cells of a column, we can simply use a list which contains the actual years of birth for the politicians. We are once again referencing this column by the column header, and since the column already exists, this operation will simply overwrite the values of all the cells corresponding to that column. So when we execute this particular Jupyter Notebook cell and view the contents of our data frame, we see that this third column for the year of birth has been overwritten with the values we have supplied in the list. So we have now successfully been able to add a new column to our data frame and then populate its cells with data. Now, if you would like to delete the column which we just created, we can simply make use of the Python del command. So we specify that we would like to delete the year of birth column from our data frame, and by executing this code, we get the confirmation that the year of birth column has indeed been removed from the data frame. Moving along, we will see how we can add a new row to the data frame. To do that, we make use of the lock indexer, which allows us to access specific rows or columns of a data frame by their corresponding indexes. In this case, we wish to set the value of the row corresponding to index location -1 to Otto von Bismarck and Germany. Similar to our use of column headers just a little earlier in this demo, if the row with index -1 does not already exist, then it will be created for us. If it does, then the value in that row will simply be overwritten with these new values we are providing. So when we execute this cell, the resultant data frame contains this new row of data right at the bottom with the index of -1. So now that we have covered how we can add and remove rows and columns to our data frame, let us see how we can modify the index of the data frames as well. For that, we simply access the index property of the data frame. And in this case, we will simply be incrementing the value of each row index by 1. Upon running this cell, we see that each row index label has indeed been incremented by 1. But you may also notice that the row with the lowest index of 0 is right at the bottom of this data frame. Now we can adjust that by sorting the data frame rows by the index values. And for that, we make use of the sort_index function of the data frame. So we update our data frame by sorting it with the index. And upon examining this resultant data frame, we see that it has indeed been sorted by the index of the row. So now that we have added a new row to the data frame, let us go ahead and drop one. For that, we make use of the drop function of a Pandas data frame object. And here we can specify using the index which row we need to drop. So here we are going to drop the row with the index of 7, which corresponds to the entry for Deng Xiaoping. On running the cell, we can confirm that the particular row has indeed been dropped from our data frame. At this point, let us see how we can set our own custom index for the rows in the data frame. And for that, we will use a list which is similar to the year of birth list which we had used previously. So this index_values list contains the year of birth for each of the politicians in our data frame currently. And then we simply set the value of the index property of our data frame to this new index values list. We then examine the contents of our data frame, and we see here that each of the rows has this new index corresponding to the year of birth for each of these politicians. So if you were to set the row index for your data frame, and you find that you're not happy with what you had just set and you'd like to undo the operation, well, for that, Pandas provides the reset_index function, which is associated with the data frame. So if we simply update our politician's data frame with one where its index has been reset, we see here that this has in fact added a new column to the data frame containing the old index. This column is called index, and the actual index for this data frame now simply contains the positional index values. Now, let us just go ahead and delete this index column, which we no longer need. And rather than using the del function to delete a column, which we had done previously, we are going to make use of the drop function. So previously we had used drop in order to remove a row from our data frame, but this time we're going to use it to drop a column. To do that, we make use of the columns parameter, and we can pass it the list of columns which we would like to delete. In our case, this list contains just a single element because we only want to delete one column. And when we execute this Jupyter Notebook cell, we see that the index column has now disappeared. So we have now covered how we can add and remove columns and rows from a data frame. In this demo, we will cover how one can just view a part of the Pandas data frame which they wish to analyze depending on various conditions. So we create a brand new Jupyter notebook once more, and this one I have called selection. And we begin as usual by importing the Pandas library. We will then load our data frame with data from this towedcars.csv file. So this dataset contains information about vehicles which have been towed in the United States, and we have trimmed this dataset to only include 15 rows of information. That is more than enough for the purposes of this demo, and anything more would simply slow down a lot of the operations. So once we have loaded the data into the CSV file, we are making use of the head function of a data frame in order to preview the data. That is, to view only the first 5 rows of the data frame. So the output of the head function returns the first 5 rows of the data frame along with all its columns. So this is a very good way to quickly preview the contents of your data frame. And we can see here that this contains data such as the firm which did the towing of the vehicle, the make, model, color, and license plate of the vehicle as well. Now, if we simply wish to access one column from the data frame, that is the color column, then as we have seen previously, we can simply reference the column by its column header. This syntax is similar to accessing the value of a Python dictionary using its key. And once we execute this, we see that the entire contents of the color column is now available to us. If we wish to view multiple columns from the data frame, then we can pass in a list of the column headers whose column contents we wish to see. So here we wish to view the contents of the make and color columns in our data frame, and we pass this along as a list. And now we can view both of these columns in their entirety. So when we access the columns of a data frame in this manner, the object which gets returned is also a data frame, which is why we can apply the head function in order to preview the contents of this particular return data frame. So in this case, the two columns along with the first 5 rows are returned. Now, the head function also accepts arguments. If no argument is specified, then by default it will return 5 rows of data, but we can also pass along an integer argument which will specify how many rows of data we wish for the head function to return to us. Here, we wish to view the first 9 rows of this data frame, and this is exactly what we get. Similar to the head function, there is also a tail function which returns the last few rows of the data frame. Just as with the head function, by default, this will return the last 5 rows of data, but we can also pass in an integer value in order to return a specific number of rows from the end of the data frame. If we wish to access a particular row of data from the data frame, then we can use the lock indexer and specify the row index for the row whose contents we wish to view. Here we say that we wish to view the contents of the row with the index 6, and this is exactly the data which is returned. We can also use the slice notation in order to retrieve a slice of the Pandas data frame, and this once more we can pass to the lock indexer. Here we wish to get all the rows starting from index 3 right up to index 7, and on running the cell, these are the exact 5 rows of data which are returned. Moving along, we make use of the lock indexer once more, but this time we get all the rows beginning from the index of 9, and we specify the column indexes as well. So here we wish to get all the columns beginning from the toenum column right up to the vehicle year column. And this is exactly the slice of the data frame which is returned. So now we have performed indexing of rows using a numerical index and the indexing of columns using the index labels, that is the column headers. So far we have seen how we can get a range of rows and columns, but in this case we specify the exact rows which we wish to retrieve, that is the rows with the indexes of 1, 6, and 13, and then we leave the column values blank to say that we wish to retrieve all the columns. And this is the data frame which is returned to us. Moving along, we now make use of the ilock indexer. So the ilock indexer is similar to lock, except that we can only use integers with ilock. So we have used the column headers with lock just a little earlier in this demo, but we cannot do the same with ilock because it only accepts integers and will not accept a column header in the form of a string. In the case of the rows in our data frame, the rows are already indexed by numerals, so we can simply get rows 2 through 5 using this ilock indexer. For that, we specify the range of 2 to 6. And this returns 4 rows of data beginning from index 2 right up to index 5. Note that had we specified the exact same range using lock, it would have also returned the row with the index of 6. We now try to make use of our string column headers in the iloc indexer. Here we wish to get the rows 2 through 5 and then the columns from vehicle plate right up to the color column. But when we run this, we get the error because iloc does not accept string column headers. So we can only use numerical values. And we can confirm that by getting the same range of columns, but this time we specify the numerical index values. So we get columns 3 through 6. And this time the operation is successful. So iloc only works with integer values. Just as with the loc indexer, we can also specify multiple index values in order to retrieve multiple rows using iloc. And here we get the rows with index values 3, 7, and 10, along with all the columns. And that is what is returned to us. We now move along to selecting specific parts of a Pandas data frame based on a certain condition. Here, we wish to retrieve all the rows where the value of the vehicle year column is greater than 2005. Those familiar with the concept of fancy indexing in numpy will know that this particular syntax will create a Boolean mask where the particular condition is met, and we will use that mask in order to retrieve the specific rows where the vehicle year is greater than 2005. From the output, we observe that 8 of the 15 rows of data in our data frame have been returned. Moving along, we now apply another condition where we wish to retrieve all the vehicles where the registration state is Connecticut. And when we run this returns the first 7 rows of data in our data frame. So we have now seen how we can apply a certain condition in the data frame, and we've used that to retrieve vehicles where the vehicle year is greater than 2005 and the registration state is Connecticut. Now, what if we want to apply both of these conditions so that we retrieve vehicles which are registered in Connecticut and also have a vehicle year greater than 2005? For that, we simply make use of the ampersand operator, which is the AND operator, which can be used with Pandas. We simply supply both of the conditions which we have used previously, and note that we have included them within parentheses. And running this cell gives us the results we are looking for, that is, vehicles which match both of the conditions which we have set. Similar to the AND operator, we can also make use of the OR operator. So this is going to be a single pipe character. So in order to view vehicles where the registration state is either Alabama or the color of the car is gray, we can simply use this syntax, and once more note that the individual conditions are specified within parentheses. So the returned rows over here match at least one of the specified conditions. Now that we have covered the and the or operators, let us examine the negation or not operator. So this is the tilde character. And here we wish to view all the vehicles which were towed and were not blue in color. So in our condition, we specify that the color of the vehicle should be blue, and then we include this within parentheses, and outside the parentheses, we include the tilde character to say that we wish to view the towed vehicles which are not blue in color. And this is exactly what we get when we execute this cell. And with that, we have now covered many different ways in which we can select part of a Pandas data frame. So far in this course, all the data frames we have come across have had a single index. The index has either been numeric or has been a string. We now explore the concept of a multi-index. So a multi-index is also known as a hierarchical index. So when we use this, our index is not just a single value, but is a combination of values in a specific hierarchy. The reason we may use this is because it effectively allows us to work with data in more than 2 dimensions within a 2-dimensional Pandas data frame. So how exactly does that work? Well, let us consider the fact that the index of a Pandas data frame is meant to uniquely identify a row. That is, it effectively works like the primary key in a database table. There will be occasions where a single value is unable to uniquely identify the row, in which case you need a composite key which is made up of data from more than one column. So this is what a multi-index effectively accomplishes. Let me explain with an example. Assume that you work in an auto dealership and you have a number of cars in your inventory. If this is the data of all the cars, then you see that the index, which is used by default, is not of much use. This is because referencing each type of car by a number is not quite intuitive. So we now decide that we would like to reference each car by its make. Well, this is a little more intuitive. However, the make of a car does not uniquely identify each row in our table. On the other hand, if we were to combine the make and the type of car, then what we have is a composite key which uniquely identifies each row in our data frame. So the index in this data frame is made up of two columns, which is why it is a multi-index. It is also a hierarchical index because there are two levels in this index. Each level of this multi-index is referenced by its header, which is why this is the level type, and the first level of this index is the level make. We can use each of these index levels individually in order to reference rows in our data frame. For example, we can use the make level in order to retrieve all the Toyota cars in our data frame, and we can use the level of type in order to return all the sedans. In this demo, we will cover how we can reshape or reorient the data within a Pandas data frame in order to analyze the data in a more meaningful manner. So we start off as usual by importing the Pandas library, and then we will create an avocados data frame, and we do so by importing this data set which contains the price information for avocados in the United States over a number of years. And when we view the contents of the data set in our data frame, we can see that it contains information on a weekly basis for various regions in the United States and also for both organic as well as regular avocados. Since this contains about 4 years worth of data for multiple regions and for both conventional and organic avocados, this data set is rather large and contains about 18,000 rows. Now, we wish to analyze how many unique regions are covered in this data set. And for that, we first access the region column. And from the return data frame, we call the unique function. So this function will return the number of unique values in that particular column. And from the return value, we can see that this list is also rather large. So these are too many data points for us to work with. So let us trim this data set so that it's of a more manageable size in order for us to perform our analysis. Here, we specify that we want to limit the data frame to just the total US region. So this is an aggregation of all the regions in the United States. And we only wish to view the latest information in this data set, that is the data points from January 2018. Now that we have a trimmed data set, we will go ahead and sort the data by the date column. In order to do that, we can make use of the sort_values function of a data frame. And here we can specify a list of columns by which to sort the data. Since we only wish to sort by the date column, that is the only value we pass in the list. Once we get the output from the sort operation, we notice that there are duplicates in this data frame. That is, there are duplicate values of date, and this is because this information covers both organic as well as conventional avocados. At this point, let us say that you wish to analyze the average price for each of these dates of both organic as well as conventional avocados. Sure, you can get that information from this particular data frame, but you would like to reorient the data so that you can perform a quicker analysis. One way to do that is to create a pivot table. So Pandas allows us to create pivots by making use of the pivot function of a data frame, and this will allow us to orient our data in such a way that each row corresponds to a date and each column corresponds to the type of avocado. The individual cells will then contain the average price of an avocado of a particular type represented by its column and on a particular date represented by the row index. We can simply run this cell to see what that looks like, and we see here that there is one row entry for each date and then there is one column for each type of avocado. Note here that the combination of the row index and the column header must be unique in order to generate a pivot table. So by reshaping the data in our data frame to create such a pivot, we can very quickly compare both conventional and organic avocado prices over a range of dates. Now that we have seen how we can create a pivot table from a Pandas data frame, we will examine the concept of using multi-indexes. These are also known as hierarchical indexes in Pandas, and these are very useful in order to represent multi-dimensional data in a two-dimensional Pandas data frame. We can illustrate what that looks like by reloading the avocados dataset in a new data frame, but this time we will make use of the index underscore call parameter of the read CSV function in order to specify that a combination of the region and date columns of the dataset needs to be used as the index for the data frame. We will then sort the contents of the data frame based on the index columns using the sort underscore index function. And then when we view the contents of our data frame, we will see exactly what this hierarchical index or multi-index looks like. So we have the first level of our index, which is the region, and this contains a number of date values which correspond to the second level of the index. There are duplicate values for the date for each region in this data set, and that is because there is information for both conventional as well as organic avocados in this data set. If we wish to ensure that the combination of both the index columns uniquely identifies a row in the data set, then we can simply trim it so that it only contains information for organic avocados. So once we do this filtering, we are now left with a combination of index fields which will uniquely identify each row in this data frame. Now, if you would like to apply a filter on our data frame based on the value in one of the index fields, we can make use of the dataframe.index.getLevelValues function. We use this along with the lock indexer in order to return those rows in our data frame where the value of the date index is greater than the 1st of March 2018. And now when we view the contents of our data frame, there are 4 rows of data corresponding to each region in our data frame. So what does the index of this data frame look like? For that, we access the index property, and from the output here, you can see that it is a multi-index and that each of the levels for the index have been defined here. We will now explore the stack operation on a Pandas data frame, and for that we will be using the pivot table which we had created just a little earlier in this demo. So each row in this particular pivot table corresponds to a date and each column corresponds to a type of avocado. The cells contain the average price for a particular type of avocado on a given date. So in this case, there are 2 columns for each row in the data frame. When we perform the stack operation, we'll create a new data frame which contains a single row of data for each row index and column index combination. So when we call our data frame with the stack function, what we end up with 2 rows of data in the new data frame corresponding to each row of data in the original. And this is because there were 2 columns for each row in the original data frame. This is referred to as a stacked format because there are multiple rows stacked one on top of the other. Complementing the stack function is the unstack function on a Pandas data frame. So we can take our stacked data frame, and then when we run the unstack function, we end up recovering the original data frame. Let us now see what happens when we stack a multi-index data frame. So this time we perform a stack operation on our avocados data frame and see what the output looks like. And we gather from the output that each column in our data frame, which is not an index, gets stacked as a new row in the resultant data frame. Having covered the stack function, we will now move along to the melt function. And to demonstrate that, we will reload the avocados dataset into a data frame. And this time we will not specify any multi-index, but what we will do is to filter the data frame so that it only contains data for March 1st, 2018 onwards. With this filtered data frame, we can now demonstrate the melt function. So this melt function is used to convert a data frame into such a format where one or more of its columns are set as identifiers, and some of the other columns can be set to be the measured variables. In our example, we would like the region, type, and date columns of our data frame to uniquely identify a row in the melted data frame. And for each combination of these ID variables, we would like to view the average price and total volume information. So these are the value variables for this melted data frame. So what exactly does this look like? From the resultant data frame, we can see that there is one row for each combination of the ID variables and the measured variable. So this is similar to stacking a data frame which contained the ID variables as an index, and each of the measured variables were columns. So we have now covered several ways in which one can reshape or reorient a Pandas data frame. In this exercise, you will write a single line of code in order to retrieve specific elements from within a Pandas series. The elements which need to be retrieved are the ones which are located at index locations 0, 3, 7, and 10. And of course, do assume that the Pandas series is long enough to accommodate all of these elements. Next, you will retrieve a subset of a Pandas data frame, and this subset will include the first 15 rows and 2 columns which may not be contiguous. The headers of these columns are name and join date. The hint which I can give you is that this can be accomplished by simply writing one line of code. And finally, you will once again write a single line of code, and this time it is to get all the distinct values in the department column of a data frame. So the column header here is department. There are many roundabout ways to accomplish each of these tasks, but each of them also has a single line solution, and that is the one you should strive to get. Do try to get these answers on your own. The first task was to get the elements located at specific index locations from within a Pandas series. In order to access a single element from a Pandas series, we can simply make use of a single numeric index. However, if we wish to access multiple elements which are all located in different locations, then our index will not be a single numeric value, but in fact a list or array of values. This is the array which we use as an index here. So we pass along a list containing the values 0, 3, 7, and 10. And this will return to us the subset of the Pandas series corresponding to those index values. From the return Pandas series, we access the values property by using dot values here, and this will return to us an array of all the elements in the corresponding location of the Pandas series X. In order to retrieve a subset of a data frame, which included the first 15 rows and 2 specific columns, this is the notation which we use. And do note that we make use of the lock indexer. So the lock indexer is able to work with both numeric as well as non-numeric or string values. So to retrieve the first 15 rows, we specify a range of index values for the rows. We leave the start index as blank so that it knows it can retrieve from the beginning of the data frame. And then we specify the end index of 14. In order to retrieve the name and join date columns, we pass along these column headers in the form of a list to the lock indexer. Do remember that the lock indexer is different from the ilock indexer, where ilock only accepts integer index values. The final task was to retrieve all the distinct values in the departments column of a data frame. And the way to do that is by using the unique function. So we reference the departments column here by using the departments column header as the index. This will return a data frame which contains only the departments column. And then to that, we apply the unique function in order to retrieve all the unique values in that particular data frame. The return data structure here will be a numpy array. In this demo, we will be looking at different ways in which we can iterate over the data in a Pandas data frame. Once we have created a new Jupyter notebook and then renamed it, we can first import the Pandas library, and then we can define the data which we will use for this demo. The data concerns 6 US-based companies. So we have the name of each company, along with the state in the United States where it is headquartered, and the name of its CEO. So those 3 fields will become the columns of our Pandas data frame, and the content of these lists, that is the values in these dictionary, will populate the cells of the data frame. We then make use of the data frame constructor in order to build a new Pandas data frame out of this dictionary. We then confirm that our data frame looks exactly as we expect it to, and following that, we can iterate through each row of this data frame by making use of the iter_tuples function. Iter_tuples will return a list of named tuples, each of which represents one row in the data frame. So when we run this and we examine each row, we see that it is in fact a named tuple, where each member of this tuple is assigned a name which corresponds to the column header. So how do we access the individual fields of a name tuple? For that, we can just make use of the dot notation. And for each name tuple, which is the row object here, we will access the individual fields of company and headquarters and then print them out. So we are now iterating through each row of the data frame, and we are accessing each row in the form of a named tuple. Another way to iterate through the rows of a data frame is by using the iter_rows function. This will return both a row index as well as the row contents in the form of a Pandas series object. So here we will print out both the row index and the Pandas series with each iteration, and we see here exactly what that looks like. Rather than getting the entire row contents, if you would like to access the individual fields, then we can simply make use of the positional index for each field in the Pandas series object. So the data at index positions 0 and 2 correspond to the company name and the company CEO. And when we run this, we have performed one more iteration over the rows of our Pandas data frame. If we would like to iterate over the columns of our data frame, then we make use of the iter_items function. This will return a key and value pair where the key corresponds to the column header and the value is a Pandas series object which corresponds to the column's data contents. So when we iterate over the columns and print out its contents, this is what the output is like. So we have now covered how we can iterate over the contents of a Pandas data frame both row-wise as well as column-wise. We will now cover the various ways in which we can export the data in our Pandas data frame to different types of files. These include Excel files, JSON files, CSV, and so on. So once we have created a new Jupyter notebook and set it a name, we will import the Pandas library, and then we will create the data which we will populate a data frame with. So this data contains 3 columns: the name of a company, where its headquarters are in the United States, and the name of its CEO. So once we have loaded this data into a Pandas data frame, we will now explore how these can be exported into different file formats. First, we will export this data into an Excel file, and for that we make use of the to_Excel function of a Pandas data frame. Here we need to specify the location of the output file, and then we can set whether we want the index for each row to be represented in the file. So we set that value to false. And once we have run this cell and the export has taken place successfully, let us go ahead and confirm that this file has indeed been created. So within our Jupyter Notebook interface, we navigate to the datasets directory where the file was exported, and we can see here that this Excel file has indeed been created. Heading back into our notebook, we will now export this file into a text file, and for that we'll simply use the to_CSV function. So this will actually create a CSV file, but we want to demonstrate that you can also name it as a text file, and this function will still run successfully. So once this text file has been generated, we will just go ahead and create a real CSV file, once again using the to_CSV function, and this time we will call our file techcompany.csv. Once the CSV file has been created, the next thing we will do is to create a JSON data structure from our data frame. So for that, we'll make use of the to_JSON function, and we will write this JSON output to a techcompany.json file. After that, we will create an HTML file in which our data frame is output, and there is a to_HTML function available for that. So now we have exported our data frame in multiple data formats. Let us go ahead and examine some of these. So we once more navigate into the datasets directory, and then clicking on the HTML file, you can see here that this has formatted the contents of our data frame into a nice little HTML table. The column headers are all bold, and because we had specified that the row index should not be included, that is not present in this HTML output. We'll now examine the JSON file which has been created, and we can see over here what that output looks like. So these are all the different types of export files which we have created, which contain the data from our Pandas data frame. In this demo, we will examine different ways in which we can sort the contents of a Pandas data frame. Once we have created a new Jupyter notebook and set it a name, we'll then import the Pandas library, and we will load the data frame which we will need in order to demonstrate sorting in this demo. So for that, we will be making use of this echocardiogram dataset, and we will load it into a data frame called unsorted data. Once this data has been loaded, we will trim the dataset so that we are only working with the first 15 rows. This is more than enough to demonstrate the various types of sorting available in Pandas. Once the data has been loaded into our data frame, we can take a quick look at it, and we see here that it contains mostly numeric values. So the first thing we will do is to specify our own index values. For that, we access the index field of a Pandas data frame and then set it to this list of values. Note that this contains all the numbers from 1 through 14, but in fact contains 15 values because the number 9 is duplicated. This is to demonstrate that the index of a Pandas data frame need not be unique. So when we run this cell, the previous index has simply been overwritten with these new values. The remainder of the data frame's contents have not been altered in any way. Now, Let us go ahead and use the sort underscore index function in order to sort the data in this data frame by their index values. So this is a function we have seen previously, and when we execute it, we can confirm that the rows of the data frame have now been reordered in order to order the contents by the index value. So the sort underscore index function by default sorts the contents of the data frame by the row index. If you would like to sort the data frame by the column index, we simply call the function, but we also pass in the access argument and set it to a value of 1. When doing that, the columns have now been sorted in alphabetical order. If we wish to retrieve the contents of only one column after the data frame has been sorted by the index, we can simply reference a single column by its column header and then apply the sort index function on this reduced data frame. And this simply returns the contents of that column when it has been sorted by its row index. Thus far, we have been sorting the contents of the data frame according to the row or column index. We will now cover how the data frame can be sorted by the contents of individual columns. Before we do that, let us quickly remind ourselves what our unsorted data frame looks like. And we can see here that this is the version where the index has not been sorted either. What we will do now is to sort our data frame depending on the contents of the age column. For that, we need to make use of the sort underscore values function of the data frame. And in order to specify which column it needs to be sorted by, we make use of the by argument and we set it to the name of the column by which the data needs to be sorted. So now our pandas data frame should be sorted by the age column, and we can confirm that when we execute this cell. To further illustrate how sorting can be performed, we will select just a few of the columns from our pandas data frame, specifically the survival, age, EPSS, LVDD, and wall motion score columns, and then we will sort not by a single column but by two columns. The resultant data frame will first be sorted by the value of the survival column, and for those rows which contain the same value for survival, they will be sorted by the value of the age column. And this is what our resultant data frame looks like. You will notice that there are 3 rows which have the same value for survival, specifically 19, but those have been sorted according to the value of their age column, which contains 46, 57, and 72. So we have now covered different ways in which a pandas data frame can be sorted by using both the index for the rows and columns as well as the data within the individual columns. We now explore an occasionally annoying but rather crucial task of handling missing data in datasets. Large datasets do not always have every single cell populated with information, and there are different techniques to handling this missing information in order to perform any kind of statistical analysis. We will explore some of them in this demo. So we start off by creating a new notebook, and then we will import the pandas library into it. We will then load the echocardiogram data using the read underscore CSV function, and then we will preview the first 5 rows using the head function. So we see here that there are a handful of missing values or NaN values in this data frame. We will now explore one of these columns containing a few NaN values, and this is the age column. We will make use of the isNull function, which will look for these NaN values. So you see here in this row with the index of 2, there are a handful of NaN values, including in the age column as well as in the last column. This isNull function will return a Boolean array containing true or false values, and it's going to be the same size as this age column. However, we will use the sum function in order to sum up the number of true values in that Boolean array, and this will have the effect of returning the number of NaN values or null values in the age column of our data frame. So we observe that there are 7 null or NaN values in this age column, and then we can use the not null function in order to calculate the number of non-null values in this column. So there are 126 such values. So the total number of values in this column is 133. Now, there are different ways in which we can handle these null values, and one of those is to substitute the null or nan values with another number. The way to do that is by calling the fill_na function, and this will replace all nan values in the data frame with the value which is passed to it as an argument. So in our case, we are simply replacing all the nan values with 0. Once we run this cell, we can once again preview our data frame, and we see here that in the row with index of 2, the nan values have indeed been replaced with 0. Now this is a trivial way of substituting a nan value. More sophisticated techniques include calculating the mean or median of the non-null values in a column and substituting the nan values in the column with that value. Now that we have filled the nan values in our data frame with 0, let us calculate the number of null values in the age column, and this turns out to be 0 because all the nan values have been replaced with a valid 0 value. When we sum up the number of non-null values in this age column of our data frame, we see that all 133 values are now valid. We now move along to a rather harsh but effective technique of handling missing data in a data set, and this is to simply drop each and every row in the data set which contains any missing value in even a single column. To do that, we make use of the drop_na function. So when we call that function and preview the resultant data frame, we can see that the row with an index of 2, which contained a handful of nan values, has now disappeared. So after having dropped all the null rows, how many null values do we have in the age column? Unsurprisingly, the answer is 0. We now examine how many non-null values are present in the age column, and the answer is now 61. This is because even though there were only 7 null values in the age column, the drop_na function discards an entire row if even a single column in it contains a null or nan value. So there were 72 rows in our data set of 133 rows, which contained at least one null value. The next thing we will do is not exactly handle missing data, but see how we can substitute specific values in our data frame. For that, we examine the first 10 rows of our original data frame, and we observe that in the name column, only the first names of patients have been listed. Now, if we would like to substitute full names of the individuals rather than the first names, we could either alter the contents of the cells individually, or we can simply make use of the replace function of a pandas data frame. The argument to a replace function can be a pandas dictionary where we specify a set of key value pairs, and the keys correspond to the string which needs to be replaced, and the value represents the data which the string will be replaced with. Note that every single occurrence of the key will be replaced with the value. So if we execute this cell and view the first 10 rows of our data frame, we can see that the name substitution has indeed taken place successfully. In this demo, we will explore in more detail the grouping of data in a pandas data frame by using a multi-index. So once our new notebook has been created and then assigned a name, we will go ahead and import not just the pandas library, but a few others as well. This includes the matplotlib pyplot object as well as the Seaborn library. We then configure both Seaborn and matplotlib for our notebooks by running the sns.set function and running the matplotlib inline directive. With those taken care of, we will initialize the data set which we will use for this demo. And for this, we need to assume that we are an automobile dealership and we're storing details about various cars in our inventory. So we have the make and model of the vehicle along with its color, the quantity of each vehicle we have in stock, along with the price of each individual vehicle. Once we have loaded this data into a pandas data frame, let us quickly examine what this looks like. And we can see here that this contains a total of 13 vehicles. We will now check out the index which has been created by default for this data frame. And for that, we access the index property, and we can see that this is a range index type, which is denoted by a start, stop, and step notation. We would now like to group cars of the same make together using the index of the data frame. And for that, we call the setIndex function, to which we need to pass as an argument the list of columns which will be used as an index. For now, we only want to create an index out of the make column. So this is not going to be multi-index yet. And when we execute this cell, we see that the index of our data frame has now been updated. Ideally, the index in a Pandas data frame should be able to uniquely identify the row. In order to do that, we will reset the index, and this time we will call the setIndex function in order to define a multi-index. So our multi-index or hierarchical index contains two levels, the first one being the make of the vehicle and then the model of the vehicle. And when we run this cell, we can now see that all the cars here now seem to be grouped together by their make. Previously in this course, we have seen how we can access rows of data in a Pandas data frame using the index. But when it comes to using a multi-index, we need to make use of the access function, which will return a cross-section of rows or even columns. So the access function will return a set of values corresponding to the index key. In our case, we want this to return all the rows in our data frame where the index corresponds to BMW. That is, we wish to view all the BMW vehicles in our inventory. So when we run this, what is returned is in fact a data frame which contains the second level index, which is the model, along with all the other columns in the data frame. All of these rows are ones where the first level index value was BMW. Moving along, we now try to make use of the access function in order to return rows where the second index value is x4. That is, we want to view the rows of data where the car model is x4. So what we're trying to do here is to get the access function to access a value from the second level index. And when we run this cell, we end up with an error, and this is because the access function by default only looks at values in the first level index. If we would like to view the rows where the model is x4, then we need to explicitly set the level at which the access function needs to look for that value. So here we pass the level argument and we tell the access function that it needs to look for the x4 key in the model level index. And when we do that, we are returned a data frame which contains the first level index, which is BMW, along with all the other columns corresponding to the row where the model is equal to x4. So we have now retrieved the data of the BMW X4s in our inventory. Even when using a hierarchical or multi-index, we can get a slice of the Pandas data frame by using the lock indexer. Here, we wish to retrieve all the rows where the value of our first level index is between Audi and Chevrolet. So this is not that different from using a numerical index. And when we execute this cell, this is exactly the range of data which we wish to retrieve. So the data for Audi, BMW, and Chevrolet has been returned, and we have confirmed that we can use the lock indexer even with a multi-level index. When working with a large amount of data, one often ends up in a situation where they need to combine data which resides in different data sets and happens to be in different data frames. In this demo, we will explore how we can merge or join data which lies in different data frames into a single one. So we begin by creating a new Jupyter notebook, and once this has been named, and then we import the Pandas library, we create the first data frame we will work with during this demo, and this contains information about certain cars. Imagine you work in an auto dealership and you'd like to store information about the various types of cars in your inventory. So here we create a data frame which contains three columns. One is for the make and model of the car, the other is for the car's color, and finally there is a car ID to identify a car of a particular color. So once we have created this data frame with 8 vehicles, we create one more similar data frame So this contains the same columns and the type of data in each column. That is, it has the same schema. However, it only contains 2 rows for 2 types of vehicles. So we now have 2 data frames, each of them containing data about certain vehicles. Now let's just say each of these data frames represent the inventory of 2 different divisions or 2 different franchises of an automobile dealership. Then if you happen to work in the head office of this auto dealership, then you may want to view the total inventory of vehicles across all the franchises. For that, you may want to combine the data frames coming in from each individual franchise into a single one. One way to do that is to use the concat function, which will concatenate 2 data frames. Let's see how this works. So here we pass in an argument containing a list of data frames which need to be concatenated. So once we combine our cars and more cars, we can see that the result contains all the rows from the 2 combined data frames. So it now contains 10 rows of data. The first 8 rows are the rows from the cars data frame, and the next 2 rows are from the more cars data frame. So each of the data frames passed in the list to the concat function are processed in the order in which they appear in the list. You will notice that the row indexes for the rows from the more cars data frame are 0 and 1. That is, they have been imported as is from the more cars data frame without any modification. As you can imagine, this could be problematic because you want the combined data frame to have its own unique index. To do that, when we call the concat function and we pass in our list of data frames as argument, we can also specify the ignore index argument and set it to true. This will ignore the index from the source data frames which are being concatenated and will create a new index for the resultant data frame. And when we do this, we can see here that the index values from 0 to 9 have been created this time. So with that, we have covered the situation where we can concatenate 2 data frames which contain the exact same schema. So we have been able to combine 2 data frames which contain the exact same schema. That is, 2 data frames which contain information about cars in our inventory. Now, we can consider the case where we have another data frame which contains a set of orders for the various vehicles in our inventory. So here we have a data frame containing an order ID, the quantity of vehicles in the order, as well as the ID for the car which is associated with the order. So we just go ahead and create this data frame which contains an order for 8 of the cars in the inventory of 10 cars. So if you are analyzing the data for all the sales made for each of the vehicles in your inventory, it will be useful to combine both the cars data frame as well as this orders data frame so that you can see exactly how many vehicles of each type have been sold. So let us try to combine the cars and the car orders data frame using the concat function and see what the result looks like. And we not only get a warning message that this operation seems incompatible, we also see that the concat function simply appends the rows of one data frame below the other. Since the car ID column is the only one which is common to both the data frames, this is the only column which has all the values populated in this combined data frame. So this concatenation of the rows of the data frames does not really provide anything meaningful for us in this situation. However, the concat function does allow us to perform a concatenation along the columns of the data frame. And for that, we simply need to pass in the axis argument and set it to a value of 1. So this time when we perform the concatenation, the result looks a lot cleaner. There are no nan values here. However, what you see here is that the orders have not been matched up with the corresponding cars, and this is because the order of the rows in the individual data frames have been maintained in this concatenated data frame. That is, a SQL-like join operation has not been performed. In order to do exactly that, we can make use of the merge function in Pandas. The arguments to merge include the 2 data frames which we wish to join along the columns, and the resultant data frame gives us exactly what we are looking for. In fact, Pandas has been smart enough to detect that the car ID column is common between these 2 data frames, and it has performed a join operation using that column. So on this occasion, each of the cars have been matched up properly with their corresponding orders. So this merge operation worked successfully between the two data frames because each of them had the exact same name for the car ID column. It is possible that when you're using different data frames, there will be a matching column, but they may not have the exact same column header. For occasions like that, we can specify the on argument when calling the merge function, and the value for this can be a list of columns on which to perform the join. In our case, there is just a single column which is common to both, so we just pass in a single value. But when there are different column names in each of the data frames, then you would need to pass in the list of those column headers. So when we run this merge function, it gives us the same result as we did previously. So in the case of this merge operation, all of the 8 cars in the cars data frame were matched up with each of the 8 car orders. What if we had some rows in one of the data frames which did not have a corresponding match in the other? To simulate that situation, we are going to recreate our extended cars data frame by combining the cars and more cars data frames, and then we specify the ignore index argument. And once we have our data frame containing 10 cars, we try to merge this with the data frame containing the 8 car orders on the car ID column. So this gives us the exact same data frame as we saw previously. That is, the cars which did not have a corresponding order are not present in the combined data frame. Those of you familiar with SQL will notice that this is similar to an inner join operation in SQL. So what if you would like the combined data frame to show even those cars which are not matched up with an order? What we need for that is a way to perform a left join. So the merge function does allow us to specify a how argument, and here we can mention what type of join we wish to perform. The valid values are left, right, outer, and inner. So in our case, we wish to perform a left join, and when we run this, we get the data frame which we are looking for. That is, every single entry from the extended cars data frame is present here, as well as the matched orders from the orders data frame. If you have worked with relational databases, you will notice that there are a few similarities between relational databases and pandas. The fact that pandas data frames can be viewed as tabular data structures does lend itself to a lot of SQL-like operations. In fact, that is exactly what we will be covering in this demo, where we will integrate SQL as well as pandas. We create a new Jupyter notebook as we have done with the previous demos, and this time we will import not only the pandas library, but also the sys library in order to connect to our file system, and the SQL-like 3 library. This will allow us to create databases on our local file system. Next, we will go ahead and create a connection object, and this will be used to connect to a local database, which is in fact a file on our local file system. This database is going to be in the datasets folder and will be in a file called empdata.db. We use the SQL-like 3's connect function in order to connect to this particular file, and if it does not already exist, a new file will be created in this case. Note that if the file already exists, it means that we are connecting to an existing database. So once we have established our connection object, we will need to create a cursor before we can execute any queries against this database. So we simply call the cursor function from our connection object. And following that, we are now ready to create a table in this local database. To do that, we will construct a create table query, and we will be creating a new table called employees, which will store the details for a number of employees in a fictitious company. So the details include the ID, first name, last name, department, gender, and the city where the employee is working. So just think of it as a global company with offices in multiple cities. Also take note that the employee's ID is the primary key for this table. So once our create table query has been constructed, we make use of the cursor object in order to run this query against our database. So we call the cursor.execute function and pass in our create table query to it. And then when we execute this, we see no errors, which means that our create table query has executed successfully. At this point, let us try to execute this query once more. Let us try to recreate the same table with the same table name and see what happens. And on this occasion, an error is thrown because the table already exists in that database. We move along now and try to insert data into our newly created table. And for that, we make use of an insert into statement. So we will be inserting the details of one employee called Xuan Ping, who works in Beijing, into our employees table. And as we did previously, we will be using the cursor.execute function in order to execute this query. So this operation has also performed successfully. And just to confirm that our table will not allow the insertion of duplicate values, that is, the primary key constraint is being enforced, we try to insert the details of one more employee with the same ID as the previous employee. So Susie Schneider is being created with the employee ID of ID_1, which is the same as the previous employee Xuanpeng. When we execute this statement, we end up with an error because the primary key constraint is being violated. So we try again now to insert the data for Susie Schneider, and this time we specify a different ID of ID_2, and executing this insert statement is successful. We'll now go ahead and insert the details for a third employee, David Lennon, who works out of Austin, and this insert statement is also a success. And we'll just go ahead and create two more employee records for two persons working out of the Cape Town office. So with these statements executed, we now have the details of 5 employees in our database. To save all these changes which we have made, we execute the connection.commit function in order to commit our changes. At this point, let us perform a select query in order to view the contents of our employees table. So we simply do a select star from employees using the cursor.execute function. And now the query has been performed, but in order to retrieve the rows which have been returned from it, we need to use the cursor.fetchAll command. So the cursor has the query results, but we need to fetch them using this function, and we gather them into this employee_data variable. And when we view its contents, all the data from our employee table is now available here. So far in this demo, we have performed all the operation using SQL-like 3. So where exactly does the Pandas integration fit in? Well, that is exactly what we're going to do now, where we're going to create a data frame from all this employee data which has been returned from the table. To do that, we make use of the Pandas data frame constructor, and the data which this data frame will be loaded with will be the rows which were returned from the select statement. Do note here that we have explicitly converted the employee_data variable to a list when passing it as the data for the data frame constructor. And then we also specify a list of column headers using the columns argument. Once that is done, we see that our database table information now is loaded into this data frame. So while we have loaded CSV files and our own custom data from dictionaries, lists, and so on into a data frame, we have now seen how we can load data from SQL table into a Pandas data frame. When we are done working with the database, we can simply close the connection by running the connection.close function. Once that is done, if you try to use the cursor object in order to execute any query, it will result in an error because that cursor is linked to the connection object and the connection has been closed. In this exercise, you will write some code in order to sort the rows of a data frame by the contents of one of its columns. So make an assumption here that you have a data frame which has information about some employees in a fictitious company, and one of the columns in this data frame contains the salary of these employees. You will need to perform a descending order sort based on the values of the salaries. Next, assume that you have two data frames X and Y which contains data which is related to each other. The relationship between these two data frames is established by the ID column. What you need to do is to write one line of code which will effectively perform a left join between these two data frames. That is, it will combine these two data frames into a single data frame which contains all the rows of X, but only those rows of Y which have a corresponding ID in X. The final task in this exercise involves cleaning up a data frame. To be specific, You'll implement two techniques to handle missing values in data frames. One of these is to remove all the rows in a data frame which contains even a single missing value. The other technique is to substitute all missing values in a particular data frame with a specific number. Do try to perform these tasks on your own. In order to sort the rows of a data frame by the contents of one or more of its columns, we make use of the sort_values function. The arguments to this function include the headers of all the columns whose data needs to be considered when performing this sort. So in our case, we call the sort_values function and we specify using the by argument that the data frame needs to be sorted by the contents of the salary column. If we needed multiple columns to be considered in the sort, then the value of the by argument would be a list containing those column headers. By default, any sort operation which is performed in a data frame is by ascending order. So in order to perform a descending order sort, we can simply set the value of the ascending argument to false. Next, in order to perform a left join between two data frames, we make use of the merge function in the Pandas library. The arguments to the merge function include the two data frames which need to be joined, and the ordering of these two arguments does matter here. We then make use of the on argument to specify the columns of these data frames on which the join needs to be performed. In our case, each of the data frames X and Y have an ID column, so the value of our on argument is a single string. However, if the matching columns in the two data frames have different column headers, then the value of the on argument would be a list. And finally, in order to perform a left join, we can make use of the how argument and we set it to a value of left. And finally, in order to clean up a data frame which contains a number of missing values, there are different approaches which can be applied. Making use of the drop NA function will remove every single row in the data frame which contains even a single missing value. This is often the simplest solution. However, it does have the drawback of potentially drastically reducing the size of your dataset. Another option is to substitute the missing values with some other value. For that, we make use of the fill_na function, and there are different ways in which this can be applied. In this case, we are simply hard-coding a value of 100. However, there are more sophisticated ways to deal with missing values by using the fill_na function. These may include calculating the mean or median of all the existing values in a particular column, and then filling in all the missing values in that column with that mean or median. For this course on visualizing data using Seaborn, there are a few prerequisites. For one, you should be comfortable programming in Python 3 since all of the demos in this course will be coded in that language. You should also have some degree of fluency using Jupyter notebooks, as that is the IDE which we will use during the demos. And though it is not a requirement by any means, understanding this course will be far easier if you have some experience with some of the other Python libraries which Seaborn is integrated with. This includes Pandas, numpy, and also matplotlib. So what exactly is Seaborn? Well, you can think of it as a data visualization library, which is built on top of matplotlib and integrates with a lot of other data science as well as statistical libraries. So while matplotlib is a visualization framework which provides a lot of fine-grained control over the plots one can create, and it is also part of the PyData stack, Seaborn is something which provides higher-level abstractions over matplotlib and is tightly integrated with the PyData stack. Seaborn also integrates with other data structure libraries such as numpy and pandas. In addition, Seaborn also provides support for other statistical and data analysis libraries such as SciPy and stats models. So how exactly can we compare and contrast both matplotlib and Seaborn? Well, matplotlib is part of the PyData stack, which is the open data science stack available in Python. On the other hand, Seaborn is built on top of matplotlib and is tightly integrated with PyData. Matplotlib allows you to very finely control every detail of your plot, and it allows you to do a lot of complex things with it. On the other hand, Seaborn works with plots at a much higher level, which makes it very easy to use for a lot of data scientists. On the other hand, it does take away some degree of control from the user. So Matplotlib, as we have discussed, provides a very low-level API to control your plots, while the PyPlot library of Matplotlib works at a slightly higher level. Seaborn, on the other hand, works at an even higher level than PyPlot. So if you'd like to define plots for production use, such as a production website, or if you'd like to make some important presentations to higher ups in your company, then it's certainly possible to use Matplotlib. However, the task becomes a little more complicated because of the need to use the low-level Matplotlib API. On the other hand, some degree of fine-grained control is possible in Seaborn without having to access the low-level APIs. Now, let us try to understand where Seaborn fits in with all the other data science libraries. So, Seaborn is a package which you can install using pip install, and it is very closely integrated with the PyData stack. In fact, Seaborn represents a number of high-level APIs which provide a layer of abstraction over some of the other libraries within the PyData stack. So what exactly is included within PyData? So the one package which Seaborn works directly with is Matplotlib. In fact, it is built right on top of Matplotlib. Matplotlib itself is integrated with some of the other libraries within the PyData stack. This includes the numpy and pandas packages, which individually can be installed using pip install, but these provide essential data structures such as arrays and data frames, which are used to represent data. Now, within Matplotlib itself, there are a number of different modules which serve their own purposes. For one, the low-level APIs for Matplotlib provides a lot of fine-grained control over your plots. PyPlot, on the other hand, works at a slightly higher level, as does the PyLab module, and both PyLab and PyPlot work on top of the Matplotlib API. And Seaborn sits on top of all of these. So with all this talk of high level and low level, it makes sense to clarify what exactly is meant by those terms. For example, at the low level, your instructions may be of the form, draw this curve, and the curve will be part of a much bigger plot. But when you're working at the higher level, you simply provide the data and then give an instruction such as use this data to plot a histogram. So low-level operations work with specific elements of the plot, whereas with high-level operations, you simply define the type of plot you want and then supply the data. In fact, this high-level and low-level hierarchy is defined within the Matplotlib codebase itself. So let us examine the hierarchy of various elements within Matplotlib. So right at the top sits the figure object, and a figure consists of a canvas and axes. Your axes could be the X and Y axis, or maybe even a Z axis or others. And within these axes, there will be ticks. These could be minor and major ticks. And there are, of course, several other elements. In Matplotlib, each of these components are of type artist, and there is a hierarchy defined for the various artists. So right at the top here, the figure is in fact a container class, while the other artists are more granular elements. Since the figure, along with the canvas and axes, are the top level containers, the higher level APIs such as PyPlot and even Seaborn work at this level. On the other hand, if you would like to control some of the more minor artists, then you would need to use the Matplotlib API. This demo and all the others in this course will be developed in Python 3 using Jupyter Notebooks. A Jupyter Notebook is a web-based interactive development environment which is very popular among Python developers. It allows you to execute just a section of your application's code and then quickly view its results. For the demos of this course, I have created my own workspace, which is under my home directory /projects/Skillsoft. Once you have done something similar, you can start up your Jupyter Notebook session by typing Jupyter Notebook on the terminal. This should automatically bring up the Jupyter Notebook web app in your default browser. In case it does not, you can simply copy this link which appears on your terminal window and then paste it into your browser's address bar. This will bring up the workspace directory in the Jupyter Notebook interface. And as you can see here, I already have a datasets directory. So just clicking into that, you can see a number of CSV files. And these are the datasets which we will be using during this course. So at this point, we can navigate back to the root of the workspace. And then from there, we can just pop up a new Jupyter Notebook. For that, click on New. And this new Jupyter Notebook is going to have a Python 3 kernel. And once the notebook has come up, the first thing I'm going to do is to just rename this notebook to something more meaningful than untitled. So just click on the title and then give it a name which represents what you're going to do in this demo. Once that is complete, the first thing for us to do is to install Seaborn, and we will be doing that by executing a pip install command from the cell of our notebook. So whenever we execute a shell command from a notebook cell, we need to precede it with the exclamation point. Note here that I'm also making use of the upgrade flag. This will mean that if I already have an installation of Seaborn, that can be upgraded if a newer version exists. Since I already have the latest version of Seaborn, there is no installation which occurs here. But if you don't have the latest Seaborn already, you will see some installation steps over here. Alright, so we are now ready to start coding. The first thing we do is to import the Seaborn library, and we reference it by the alias SNS. With that, let us check which version of Seaborn we have currently. And to do that, we make use of the Seaborn dunder version dunder property. And this shows that I have the version 0.9.0. The next thing we do is to import the Pandas library. So Pandas is a Python library which is capable of representing data in the form of a tabular data frame. The datasets which we will use in this course are in the form of CSV files, and we will be loading those CSV files into Pandas data frames before we can use those data frames with Seaborn in order to analyze the data. We go along now and check the version of Pandas which we have currently. And in my case, I have version 0.23.0. This version check is just to ensure that the versions of Pandas and Seaborn are indeed compatible. We now move along and then load the data set which we will be using for the initial demos. And for that, we make use of the read_CSV function of the Pandas library. And the argument we pass to it is the location of the dataset file. The read_CSV function will return a Pandas data frame object, which we load into this pollution data variable. We then make use of the head function of a data frame in order to preview the first 5 rows of the dataset. Alright, so this is the data which we will be using for the initial demo. And as you can see here, it contains data from a number of cities in the United States, and it has entries for the recorded pollution levels for various polluting gases across a number of dates. So this is called the UFO pollution dataset because it also has an entry for whether there were any UFO sightings on the particular day. It is meant for us to see if there is any correlation between pollution levels and UFO sightings. But in this course, we will only be analyzing the pollution levels using Seaborn. We then make use of the data frame's tail function in order to preview the last 5 rows of our data frame. And you can see here that this contains some more pollutant information. We then examine the number of rows in our data frame by checking out the length of the index field. And this shows us that we have over 63,000 records in this data frame. So in order to perform our analysis, we will be considering just the first 1,000 rows of this dataset, This is so that there is not too much data in all our graphs, and we are able to make observations visually, which allows us to understand our data. So we make use of the head function once more, and this time we pass in an argument of 1000 in order to load the first 1000 rows of our data frame. So once we have updated our pollution data frame, let us once again check the number of records, and this shows us that our data frame now has just 1000 rows. We can also make use of the describe function of a data frame, which will give us a summary of all of its numeric columns. The summary includes the count, the mean, the standard deviation, the minimum and maximum values in the column, as well as the values at the various quartiles of the distribution. So that brings us to the end of the overview of our pollution dataset, and we are now ready to use Seaborn in order to perform some analysis. In this demo, we will be using the Seaborn library in order to analyze the data within some of the columns in the air pollution dataset which we had previewed previously. To do that, we can bring up a new Jupyter notebook, and after it has been renamed, the first thing I'm going to do here is to disable warnings. Now, this is because the Seaborn library has a number of dependencies, and those dependencies may issue some warnings, which will be a little distracting during this demo. So I make use of the warnings library and set the filter warnings value to ignore so that the warnings do not appear. After that, we will import all of the libraries which we need for this demo, and this of course includes the Seaborn library. We will also be making use of numpy, pandas, as well as the matplotlib library, which is integrated with Seaborn. Following that, we load the UFO pollutants dataset into our pollution data frame, and we'll only be loading the first 1000 rows of the dataset. Once that is complete, let us take a quick look at what this pollution dataset looks like. So we use the head function of the data frame for that. And here we see that this contains the data about various pollutants, which includes the nitrogen dioxide levels, as well as the carbon monoxide, sulfur dioxide, and ozone levels. All right, so we are now ready to begin using Seaborn in order to analyze our data. And the first kind of plot which we will use is the distribution plot. So a distribution plot or dist plot is useful when we want to plot a univariate distribution. That is, we want to visualize the distribution of a single column of data. In our case, we wish to examine the distribution of the nitrogen dioxide air quality index levels. So the air quality index, or AQI, is a number which represents how polluted the air is. So the NO2 AQI levels will indicate how bad the pollution caused by nitrogen dioxide is. The higher the number, the worse the pollution levels. We analyze this by making a call to the distplot function of the Seaborn library, and we pass along the column of our pandas data frame, which corresponds to the NO2 AQI levels. So this will plot the univariate distribution of the NO2 AQI levels. We then make use of the matplotlib pyplot.show function in order to display the plot within our notebook. This function call will be used throughout this course for every single plot. However, it is only required if you are running in non-interactive mode for matplotlib. Alright, let us now just execute this cell, and this gives us our Seaborn distribution plot for the NO2 AQI levels. So you can see here that the x-axis has automatically been adjusted to represent the range of values in our NO2 AQI distribution. Seaborn has automatically created a number of bins for us, and we can see the frequency of distribution of values in each of these bins. The heights of the bars for each of these bins shows us that a lot of the values for this NO2 AQI distribution is around the 20 mark. By default, the Seaborn distribution plot also draws the kernel density estimation curve or KDE. So a KDE is a more smooth representation of the distribution of data across a range of values. The values on the y-axis of this distribution plot corresponds to the kernel density estimation. The bin in our distribution, which has the highest density of data points, is the one corresponding approximately to the value 20. Alright, with that we have created our first distribution plot, but this time we will redraw that plot but will apply a few customizations to its appearance. We once again make use of the Seaborn distplot function and pass in the pollution data's no2.aqi column, but this time the color of our plot is going to be green rather than the default blue which was selected last time. We do that by passing in a value of green for the color argument of the distplot function. We also set a title for the plot, which is going to be pollution statistics, and then set labels for both the x-axis and the y-axis. Note here that we are making use of the distributions set title, set x label, and set y label functions, and the arguments we pass to it are the strings representing the corresponding values. We once again make use of the plt.show function in order to render the plot. And this time the plot which is displayed is in fact green in color. In addition, this plot has the title which we had set for it, and there is also the X label, and then the Y label at the Y-axis is also visible. Do note here that the green color applies not just to the histogram but also to the KDE curve. Also, the green of the histogram is a little transparent. That is, it has an alpha value less than 1. One more thing about dist plots is that we can also adjust its orientation. So this time, we plot the exact same distribution plot as previously, but we pass along the value of the vertical argument to denote that the range of values should be plotted along the y-axis. The resultant plot has effectively been flipped 90 degrees. That is, the bars of the histogram are now horizontal rather than vertical. Note that we have also flipped the X label and Y labels. And here is a quick comparison with what the previous plot looked like. We now add further customizations to our Seaborn distribution plot, and we do so by passing along specific parameters to the underlying plot functions for both the KDE estimate as well as the histogram. We pass along these parameters in the form of a dictionary. So for our KDE curve, we specify a blue color as well as the line width of 2 and set a label of KDE for that curve so that it appears in a legend. We also configure the histogram by making use of the hist_kws argument. But before we do that, why don't we simply plot this graph and understand how our configurations have affected its appearance. So you can see here that the KDE curve has been plotted in a blue color, and it is thicker than it was previously because the default line width is 1 and we have set it to 2 this time. By setting a label for our curve, it has now appeared in the legend as well towards the top right of the plot. Now we can also understand how the histogram configurations work here. So setting the hist type to step instead of the default bar will create what looks like a hollow plot. That is, it is not shaded in its entirety. The line which outlines this histogram has a width of 2, and we also set an alpha value so that it's not entirely opaque. The color of this line is green, and we also set a label so that the histogram also appears in the legend. Okay, so we move back now to a more regular distribution plot, but this time we set the value of the KDE argument to false so that it only plots the histogram and does not include the kernel density estimate curve as well. So when we plot this graph, the distribution plot only contains the histogram as we expect, but do notice here along the y-axis that this graph has the frequency of the data points in each of the bins of the histogram rather than the kernel density estimate as in the previous plot, which I have just displayed here towards the right for comparison. Moving along to some more configurations for a distribution plot. This time, we set the number of bins which will be used to represent the entire range of values along the x-axis, and we set it to a value of 40. Now this is greater than the default number of bins which Seaborn had chosen for us, which is why you see that the bars are much thinner this time. In fact, if we go along and increase the number of bins to 85, the bars pretty much seem like lines in our plot. Moving along, we have seen how we can eliminate the kernel density estimate curve from a distribution plot. This time, we get rid of the histogram and plot only the KDE curve. So for that, we just set the hist value to false, and the resultant plot just contains the KDE curve. We move along now from distribution plots to a Seaborn ruck plot. So a ruck plot can be thought of as a rather compact way to visualize the density of a set of data points across a range of values. So we make use of the Seaborn ruck plot function in order to create a ruck plot, and the arguments include the data which we wish to analyze on this ruck plot, and then we pass along the height of each of the lines in the ruck plot. We would like these lines to be displayed along the x-axis, so we pass that along as the axis argument. So once this ruck plot has been rendered, you can see here that this almost resembles a barcode, but you can see that the lines here in fact represent the density of the values across the entire range. So the lines are very densely packed just above the 20 mark and around the 50 mark as well, but they are very sparsely distributed in the range 75 and above. The height of the ruck plot which we had set is 0.7, which represents 70% of the total height of the plot. So a ruck plot, much like a histogram, does allow us to visualize the distribution of data across a range of values, but we can also use them in conjunction in the same plot. To see how that can be done, we will create one more distribution plot, but this time we will adjust its size, and for that we make use of the matplotlib pyplot subplots function and set the figure size argument for it. So we set a value of 20, 5, which represents the width and the height of the plot respectively. We then call our distribution plot function, and then we set the number of bins to 95 and also set the ruck plot argument to true, so that a ruck plot is also included in this distribution plot. So what exactly will this look like? Well, as you can see, this is a rather wide plot, but the ruck plot is also included along with the histogram and the KDE curve. Finally, we will replot a distribution plot, but this time we use the default figure size, so we don't specify a figure size at all. And we also disable the histogram in our plot, but include a ruck plot. So this should plot both the ruck plot and the KDE curve. And that is exactly what we get here. So we have covered how we can plot a univariate distribution using the distplot function, which can render histograms, KDE curves, as well as a ruck plot. We have understood how we can use Seaborn in order to configure these plots in terms of its color, the line width, and so on. We now continue to explore how we can customize the aesthetics of our plots, and this time we make use of Seaborn's set function in order to set some default aesthetic parameters in a single step. We will see exactly what that does when we visualize our first plot. So this time we will make use of the KDE plot function in order to plot a single KDE curve. Again, we use the NO2 air quality index data for it. And rather than have a simple line in our plot as we did previously, this time we set the shade argument to true so that the entire area under the curve will be shaded. The color for the shaded curve will be blue as defined by the color argument. And this is what the KDE plot looks like when it has been shaded. You will notice that this time the background is not a clear white, but a gray grid with white lines. So this is known as the dark grid style in Seaborn, and this is the default style which is used when we use the Seaborn set function. Do keep in mind that by calling the Seaborn set function as we did, we'll apply the default aesthetic parameters to all the subsequent plots, unless we explicitly call the set function again and change the parameters. Also, the line of the KDE curve is an opaque blue, while the shaded area is a translucent blue. We move along now, and this time we will create a number of KDE plots, and each of these will have their own unique bandwidth and color. So the bandwidth of a KDE curve in effect determines how smooth the curve appears. The higher the bandwidth, the smoother the curve. The bandwidth value effectively determines what portion of the entire range of values will be considered in order to plot the KDE estimate for a given point. We will see exactly how this affects the curve by plotting these 5 different KDE plots, starting with a default KDE plot where we don't specify a bandwidth, and the color of that will be black. The next KDE curve has a bandwidth of 0.3 and will be in the blue color. The next one has a bandwidth of 8 and will be green, a bandwidth of 30 in yellow, and the red curve will represent a bandwidth of 80. And when we plot each of these curves, you can see that the one with the lowest bandwidth, that is 0.3, is in fact the squiggliest of these curves, and the one with a bandwidth of 80 is the smoothest of them all. The black curve is the one with the default bandwidth, and it almost overlaps with the green curve, which has a bandwidth of 8. We now move along to plotting bivariate distributions. That is, we examine two variables together in the same plot. One way to do that in Seaborn is to make use of the joint plot. So we make use of the joint plot function here in order to understand the relationship between the mean nitrogen dioxide levels and the mean carbon monoxide levels in the atmosphere at any given point in time in a particular city. Here we pass along 3 arguments to the joint plot function. This includes the data argument, which is the data frame from which the information can be obtained. The first argument to joint plot is the column of the data frame, which contains the value to be plotted along the x-axis, and the second argument is the column from the data frame, whose values will appear along the y-axis. So let us now render this plot to see what it looks like. And you can see here that it includes 2 plots, which is why it's called a joint plot. One of these is a scatter plot, which shows the relationship between the mean NO2 levels and the mean CO levels. And there is also a histogram plot, which shows the individual distributions for each of these columns. So a joint plot allows us to analyze 2 variables, both individually with the histogram, as well as collectively with the scatter plot. One little point here on terminology. The little dots you see in a scatter plot are called markers, and they represent one combination of x and y values. We now customize our joint plot, and this time we specify the kind argument and set it to reg so that it will plot a regression line for the scatter plot, and this will also include a KDE curve for the histograms. So when we plot this graph, we see that the regression line is in fact visible, and it shows a clear relationship between the mean NO2 and CO levels. And along the histograms, the KDE curve has now appeared. All of these are now in the green color as well. Moving along, we consider those occasions where you do not want to examine the entire plot, but only a portion of it. That is, you would like to limit your visualization to a specific range of x and y values. To do that, we can make use of the xlim and ylim arguments when we plot our joint plot. And when we do that, you can see here that the x-axis is now restricted to a range of 0 to 60 as we had specified in the xlim argument, and the y-axis is also restricted to a range of 0 to 3. The next thing we explore is replacing the scatter plot in our joint plot to a hex bin plot. So while a histogram can be used to represent a univariate distribution, a hex bin plot can be used for a bivariate distribution. We can create a hex bin plot by specifying the kind argument in the joint plot to be hex. And do note here that we are also setting the axis style over here to dark grid to better visualize the data. And when we render our joint plot, we see exactly what this hexagonal bin or hex bin looks like. So the grid has now been divided into a number of hexagons, and the shade of these hexagons represents the density of the bivariate distribution. In fact, you can clearly see the relationship between the univariate and bivariate distributions here, where the hexagons are darkest, where the values of the NO2 and CO2 levels are also individually the highest. The lighter hexagons represent points where the density is not as high. So this hex bin plot allows us to very clearly visualize where the values of the mean NO2 and CO levels converge. Another way to visualize the bivariate distribution is by using a KDE plot in a joint plot. But before we do that, we will set the axis style to ticks this time, and we will soon see exactly what that looks like. By using the with keyword in order to set the style, we ensure that the style is set only for this particular plot and not for all the subsequent plots in this notebook. Do note a couple of the arguments we use here. We set the value of kind to KDE so that it plots a KDE plot. And then we set the space argument to 0 so that there is no space between the axis and the plot itself. So what exactly will this joint plot look like? Well, first of all, you will notice that the univariate distribution now has a familiar KDE curve. But for the bivariate distribution, you will notice that this is kind of similar to the previous hex bin plot, but rather than very clearly defined hexagons, we have some very smooth contours which define the various density regions here. So once again, the really dark green region represents the points at which the combined density is the highest. We now redefine this plot, but this time we set a value of the space argument to be 1. And when this plot is rendered, you will see that this actually creates a space between the bivariate distribution and the univariate distributions. Moving along now, this time we don't plot a joint plot, but just a KDE plot. The variation this time being that the KDE plot will render the bivariate distribution of NO2 and CO mean levels. So this will be similar to our previous joint plot, but without the univariate distributions. Another change we introduce here is to use a color map rather than a single color for the curve. And this color map will include purples for the lower values and greens for the higher values. We also set the C bar argument to true so that a color bar will appear along with our plot. Let us see exactly what that looks like. So this two-dimensional KDE plot includes a number of 2D curves, and the colors of these curves represent the density of data points. So this PRGN color map is one of the inbuilt color maps which is available in Seaborn. And since Seaborn actually uses matplotlib, you can find the entire list of inbuilt color maps available by searching for matplotlib color maps reference. In order to map the colors of these KDE curves to actual values, we merely refer to the color bar which now appears along the right of this plot. Next, we create one more KDE plot, but this time we specify the clip argument, and by doing so, we set the lower and upper bounds of the data which is used to fit the KDE curve. And when we plot this, we see that the range of the x-axis has now been limited by the values we set to the clip argument. The next thing we do is to include RUC plots for each of the NO2 and CO distributions along with the KDE plot. Note here that because we want the carbon monoxide RUC plot to appear along the y-axis, we set the vertical argument for that rug plot to true. And we now have all three of these plots rendered in the same plot. We have covered so far how we can use a joint plot in Seaborn in order to plot a bivariate distribution. So with that, we were able to plot a relationship between two of the variables in our dataset. Now, consider the case where we have a number of columns in our dataset and we wish to study the bivariate relationship between every combination of pairs from those columns. One way to do that is to plot a joint plot for every combination of pairs. As you can imagine, this could be a rather tedious process if you have a large number of columns to analyze. However, Seaborn provides something called a pair plot, and to this we only need to pass in a list of columns, and then Seaborn will generate a graph for every combination of pairs in that list of columns, and will plot these all in a grid. So let us see exactly what that looks like. We make use of the Seaborn pair plot function. We pass in the data frame as an argument and set a height for the plot. And then, using the vars argument, we specify all the columns for which we need to plot a pairwise relationship. In our case, we would like to see if there's any relationship between each pair of pollutants in a particular town at a particular point in time. So here we specify a list containing the mean values of all the 4 pollutants in our data frame. And this generates a 4x4 grid which shows the relationship between every pair of pollutants. Each plot in this grid represents a particular combination of pollutants, while the diagonal elements represent the univariate distributions of the corresponding pollutant. So we examine this graph in greater detail, and we can see here that nitrogen dioxide is represented in the first column and the topmost row of this grid. And this is where we can see the relationship between NO2 and the other pollutants. So the use of a single pair plot function has saved us a lot of trouble of generating each of these plots individually. So the scatter plot which was generated in the pair plot allows us to examine the relationship between any two variables at the same time. However, if we wish to add more detail to the scatter plots, we can do so by specifying a value for the hue argument. So over here, we recreate the same pair plot, but on this occasion, we use the hue argument so that a different color is used for the markers to denote the year in which that particular data point was recorded. So when we plot this pair plot, what we see is that the individual markers are now shaded in different colors in order to represent the year in which that data point was noted. Also notice that along the diagonals, we no longer have histograms, but different KDE plots for each year. So by making use of colors, we can always represent an additional dimension of data in our plots. We now move along and generate one more pair plot, but this time a scatter plot is going to include a regression line. And we do that by specifying the kind attribute to be equal to reg. This allows us to confirm that there is a direct relationship between the NO2 and CO levels, while there appears to be an inverse relationship between the NO2 and O3 levels. If you would like to configure the diagonal plots in our pair plot, we simply make use of the diag kind argument, and we can set it to KDE over here. So while the previous pair plot had histograms along the diagonals, this one has the KDE curve. Since we did not specify the kind to be regression, all the other plots in this grid are simple scatter plots. Now, the pair plot is a great way to examine and visualize a pairwise relationship between columns. However, if you would like to quantify those relationships and express them in a grid similar to a pair plot, then Seaborn allows us to create something called a heat map. The input to a heat map will be a correlation matrix, which we will now create from our Pandas data frame. But first, Let us create a data frame which only contains the 4 columns containing the mean values of the 4 pollutants in our dataset. And with that data frame, we create a correlation matrix by calling the core function of a pandas data frame. So while this will allow us to view the numbers representing the correlations between those columns, we would like to visualize it in a more meaningful way using Seaborn. And for that, we will input our correlation matrix to a Seaborn heat map. We set the square argument to true so that the heat map is generated as a square. The anot argument specifies whether the correlation values will be visible in the heat map. The format argument sets the format of the correlation value. So we would like it to have 2 decimal points. And the C map or color map used by this heat map will range from yellows to greens to blues, yellows representing the lower range of values. And once this heat map is generated, we can view the correlations for every pair of elements. So the nitrogen dioxide and carbon monoxide levels are strongly positively correlated, while the ozone levels are strongly negatively correlated with both nitrogen dioxide and carbon monoxide levels. This can be visualized by both using the colors of the grid elements as well as the numbers. Previously, we have seen that when we plot a bivariate distribution, we can draw a regression line in order to show the linear relationship between two variables. That is in fact going to be the focus of this particular demo, where we will delve into linear relationships between two variables in greater detail. We begin once again by importing all the libraries which we need during the demo, starting with Seaborn, and also includes numpy, pandas, and the pyplot object of matplotlib. Following that, we will disable warnings for this notebook as well. And following that, we will once more load the UFO pollutants dataset into a data frame and limit ourselves to only the first 1001 rows of that dataset. The next thing we will do is to make use of an LM plot in Seaborn. So an LM plot will render a regression plot or reg plot on a facet grid. So this will effectively allow us to generate a grid of regression plots. However, in this case, we only generate a single regression plot, and the arguments to this include the data frame which needs to be used in order to source the data for the plot, along with the column headers of the columns which are to be analyzed. Here along the x-axis, we will plot the highest recorded level of carbon monoxide on a particular day, and then along the y-axis is the highest recorded level of NO2 on that same day. When the plot is rendered, we can see that it includes a scatter plot as well as a regression line. The direction of the regression line suggests that there is a clear relationship between the highest recorded levels of CO and NO2. We move along now and try to plot a relationship between two other pairs of variables. And this time, we wish to analyze whether there is any relationship between the ozone air quality index and the time of the day when these highest O3 levels were recorded. In other words, does it matter when O3 levels were highest in the atmosphere, or is that time irrelevant? And when we plot the graph, we can see that the O3 AQI is highest, that is, the air quality was the worst, when the O3 levels were very high between 8 am and 12 pm. However, the relationship between these two is not linear. You will also notice that the max R value almost appears discrete over here. This is because it can only take 24 possible values corresponding to the 24 hours of the day. A consequence of this is that the markers appear to be crowded along specific points on the x-axis. If you would like the markers to be a little more evenly distributed, then we can add something known as a jitter. So we once again plot the same LM plot, but this time we introduce an X jitter and a Y jitter. The jitter will add a little bit of noise along the corresponding axes, And now when we plot this graph again, we see that there is a little more distribution for all the markers. Note here that the regression line is not at all affected by adding jitters. We also set a higher jitter value, that is, we added more noise along the x-axis, since that is the axis along which a lot of the markers seem to be clustering. Moving along with the customizations of the plot, we render the same LM plot, but this time we specify some dimension information. We say here that the height of this plot should be 5 units, and we specify an aspect ratio of 2.5. This means that the width of this plot will be 2.5 times the height. And when we plot this graph, we can see that it does indeed appear to be about 2.5 times wider than it is high. Now, since our x variable appears to take discrete values and all the markers in our scatter plot appear to be crowded around specific values of x, one thing we can do is to make use of an estimator. When we set an x estimator for an LM plot, it will use just a single marker for every value of x. And as for the y value of that marker, we make use of numpy's mean operation so that the average value of y is used for all the markers corresponding to that x value. To see what that looks like, we can simply plot this graph, and you can see here that there is just a single marker for every value of x, and its y value represents the average y of all the markers corresponding to that value of x. The lines from these markers represent the confidence intervals for all the points corresponding to the x value. At the beginning of this demo, we had discussed that an LM plot is capable of rendering multiple regression plots along a facet grid. To understand what that looks like, we first generate a single regression plot which plots the relationship between the mean NO2 and the mean CO levels. So we have already seen such a plot earlier. Now we extend this LM plot just a little bit, and this time we specify the row argument and set it to year. This will have the effect of generating a new plot for CO mean versus NO2 mean levels for each unique year in the dataset. Each of these plots will be rendered in different rows in the grid. Let us see exactly what that looks like. When the plot is rendered, we can see here that the first plot only contains the data from the year 2000 and plots the CO mean versus NO2 mean levels for that. The next row contains a similar plot for the year 2001, and then for 2002, and so on. So there is a separate plot for each year on each row of this particular grid. If you would like the regression plots to be rendered along the columns of this LM plot grid, then we just specify the column argument and set it to year. This will generate the exact same set of plots, but they will all appear in different columns rather than different rows. We have already seen a few instances of how we can control the aesthetics of a figure in Seaborn. In this demo, we will focus more on that. That is, we will explore the different themes and figure styles which are available in order to configure the appearance of our plots. As usual, we import all the libraries which we require for this demo, and then we filter out the warnings. Following that, we will import our UFO pollutants dataset. So we load this into a data frame, and as we did previously, we only consider the first 1000 rows of this dataset. We can quickly preview the dataset to remind ourselves what it looks like. And it contains a record for multiple days in which the level of 4 different pollutants was recorded. The focus of this demo is not to perform data analysis with this information, but just to explore some of the aesthetic configurations. So for that, we will just use a simple distribution plot, which we did previously, and we will render the distribution for the NO2 air quality index column. So once we have rendered this distribution plot, we see that it renders a histogram as well as a KDE curve in the blue color. There is a box within which this plot is drawn, and we have our X and Y axes, and the X axis is labeled as well. Note that the background over here is a plain white. Now, these are some of the aspects which we will be changing during the course of this demo. The first thing we will do is to call the set function in the Seaborn library, and this will set some of the default Seaborn aesthetic parameters. Once this function has been invoked, those default aesthetic parameters will apply to every subsequent plot in this notebook, unless of course we explicitly set it to something else. So what exactly are these aesthetic parameters which change? Well, for that, let us redraw our distribution plot, but this time we will explicitly define the size of our figure. For that, we make use of the pyplot subplots function, and here we pass in a figure size of 10, 5, and this will generate a figure which is 10 units wide and 5 units high. It will also return a figure and an axis object which we can individually configure if we need to. So as we did before, we render the same distribution plot for the NO2 AQI column. And this time we notice that there are a few differences from the previous plot. Most visibly, the background is not a plain white as it was before, but in fact has this grid. The font for all the text is also a little different. And this is all because of the aesthetic parameter set once we call the sns.set function. Here is a quick look at the previous chart in order for you to just compare exactly what the differences are. So while the call to the set function did configure some of the aesthetics, we can also control them individually on our own. So this time, we shall call the set_style function, and we set the style for our next plot to be dark. The style for our previous plot was a dark grid, so this time we expect that the grid lines should disappear from the plot. In fact, that is exactly the case. So the background is still a little dark when compared to our first plot in this demo. So while the call to the Seaborn set function did set a lot of parameters and also set the style to a dark grid, if you would like to configure only the style attribute, then we can once more call set style and this time specify it to be a dark grid. So the grid is back in the background and the color of the background is also darker than the default white. Moving along, we can configure the gray color which appears in the background of our dark grid, and we can do that by passing a dictionary of attributes to the setStyle function. Here, we set the axis.faceColor property, and since this can be represented in grayscale, we can specify any value between 0 and 1. And when we set it to 0.8, we get a grid which is now darker than the default dark grid color. One of the other styles which we can set for our plot is a simple plain white. And the rendered plot in this case is exactly what you would expect. Rather than a dark grid, we can also have a white grid. And in this case, the background is white and the grid lines are gray in color. There is also a style called ticks, which is in fact similar to the white style, but the axes now have ticks displayed on them. As mentioned previously, the call to the SNS set function, as well as some of the other styling functions which we have called, apply to all the subsequent plots in the notebook. Those are very useful if you'd like to apply a default style for everything in your application. However, there may be occasions when you need to make an exception. For such occasions, there is the with keyword which you can use in order to set a style or theme which will only apply to plots which are defined within the with block. So over here, we set a white grid style and then we plot our distribution plot on it. And that is exactly the style which is applied here. So all of the plots we have explored so far have been encompassed within a box. Now we apply the despine function on a white grid plot and see exactly what that does. So this plot is no longer in a box, but it just contains the single x and y axes. So the call to the despine function had the effect of removing the lines from the top and the right. We once again plot the disk plot, but this time we can configure the despining in a much more detailed way. So we want the despining to remove not just the lines from the top and the right, but also from the left and the bottom. And once this is rendered, we can compare what our spineless plot looks like with regards to the regular white grid plot. And finally, we look at one more configuration option for the despining. That is, we introduce an offset between the axes and the plot itself. And when this is rendered, we can see that this time there is some space between the axes and the plot itself. By setting the trim argument to false, we have ensured that this offset plot has not been truncated in any way. In this exercise, you will recall some of the data science libraries which Seaborn is integrated with. This is to fully understand the type of data structures which Seaborn works with, as well as some of the statistical libraries which you could use in conjunction with your Seaborn plots. In addition, assume that you have been given a data set which contains a number of columns of data, and for some of those columns, you need to get all combination of pairs for those columns, and then plot bivariate distributions for each of those pairs. Think of a few lines of code which you may be able to write using Seaborn in order to plot those distributions. The next task in this exercise involves styling your Seaborn plots. So you will need to come up with a line of code which will set a figure style for all the subsequent plots in your Jupyter notebook. Following that, you will write a line or a block of code in order to create a style as a one-off. That is, the style will only apply for a single plot and not for all the subsequent plots in the notebook. And finally, you will come up with a way in which you can generate multiple regression plots where you will plot values from column Y against the values in column X for each different category in another column Z. You don't need to write code which will compile and execute here, but mainly recall the kinds of functions and objects which you may use in order to perform these tasks. Do try to solve them all on your own. The first task was to recollect some of the libraries which Seaborn integrates with. The biggest one here being matplotlib, which in fact Seaborn is built on top of. While matplotlib provides a lot of fine-grained control over elements of your plot, Seaborn works at a much higher level. The data structures you end up working with when using Seaborn are often numpy arrays and pandas data frames. We have used pandas data frames extensively in this course, and pandas is in fact built on top of numpy, so some of the details of numpy may be abstracted from you. And it is useful to know that Seaborn also provides support for the stats model library as well as SciPy. For instance, if you'd like to perform some kind of statistical analysis on your data while visualizing it, then you could use the stats model library. The next task was to plot multiple bivariate distributions for various combination of pairs in a data frame. The simple way to do that in Seaborn is to make use of the pair plot. The way to generate the pair plot is to make use of the pair plot function and then pass in a data frame along with a list of columns from which all the combination of pairs of columns will be created. If you pass in a list of n columns, then an n by n grid will be generated along with the corresponding bivariate distributions. You may recollect that the diagonals of this pair plot contain the corresponding univariate distributions. The next task was with regard to setting the style for your plots. If you'd like to set a particular style and make it the default for all the subsequent plots in your notebook, then you can simply call the Seaborn library's set_style function. So this particular line of code will set the dark style for all the plots which follow this line in the notebook, unless the style is explicitly set to something else. And if you'd like to break from the default and then set a particular style for just one plot or maybe a couple of plots, and certainly not for all the remaining plots in your notebook, then you can simply make use of the with block. You will then make use of the Seaborn axis underscore style function in order to set your style, and this particular style will only apply to the plots within that with block. And finally, in order to generate multiple regression plots based on a particular categorical value, we need to make use of the Seaborn LM plot. So the LM plot is essentially a combination of a regression plot and a facet grid. And code, such as the one which you see on your screen, will generate a grid containing as many rows as there are unique values of z, and will plot a y versus x regression plot for each of them. LM plots are particularly useful when you'd like to divide your data into specific categories and then perform a regression plot within each of those categories. In this demo, we will be plotting a number of bivariate distributions in order to understand the relationship between various pairs of variables in our dataset. We begin by importing all the libraries which we need, starting with the Seaborn library. We will also make use of the numpy, pandas, and matplotlib libraries. And then we disable warnings, which are often thrown by some of the dependencies of Seaborn. Those warnings should disappear once Seaborn has updated its code, but for the purposes of this demo, I'm disabling them so that they don't prove to be a distraction. We begin now by importing a dataset which contains records for absenteeism at a courier company in Brazil between 2007 and 2010. So once this data has been loaded into a Pandas data frame, we can quickly preview it to see what it contains. So it contains a numeric value for the reason for absence, and this in fact is set by the International Code for Diseases, which has assigned a number for various diseases, and then there are a few additional ones which are used in this data set. Aside from the reason for absence, you can see that there is a lot of other information as well, which pertain to the employee as well as the time of absence. We can then make use of the describe function of a pandas data frame in order to get a summary for all the numeric columns in the data set. So here we get information such as the mean, standard deviation, and the values at each of the quartiles for the numeric columns. Out of these, the column we are most interested in is the one for the reason of absence. So let us plot a distribution plot using the Seaborn library, and this will generate a histogram to show the distribution of values for the reason of absence. Since our dataset contains 29 unique values for the reason for absence, this is the number of bins which we will create in our histogram plot. We'll also disable the KDE curve, but include a ruck plot by setting the corresponding arguments to the distplot function. Note that this distribution plot is rendered within a matplotlib figure whose size we have configured in the first line of the cell. Once this plot has been rendered, we get a few interesting insights. The most commonly cited reason for an absence from work in this company was for medical consultation. The last bar, which is the second highest, corresponds to a dental consultation. So intuitively, we can say that this is kind of normal and there is no unusual information which we can glean from this plot. So now let us plot one more histogram, and this time to represent the distribution for the month of absence. And this time the data is a little more interesting. There are almost no absences in the month of January, but people seem to be missing work quite often in the month of December. Once again, this plot only includes a histogram and there is no KDE curve. So the plots we have generated so far have represented univariate distributions. Let us move along now and plot a bivariate distribution, and for that we will be making use of a Seaborn joint plot. Here, we wish to analyze whether there is any relationship between the day of the week and the reason for an employee missing work. So in our dataset, there is no information about absenteeism on Sundays, presumably because it's a holiday for the courier company. and the day of the week column contains numerical values with day 2 representing Monday, day 3 representing Tuesday, and so on. So when we generate this plot, the reasons for absence are pretty widely distributed across the days of the week. In fact, the only thing we can gather is that the variety of reasons seems to be a little lower on Thursday, that is day 5 in this dataset. So we move along now and plot one more joint plot, and this is to see if there is any relationship between the reason for absence and the season. And from the resultant plot, we can once more see that there doesn't appear to be any strong relationship. The reasons for absence are very widely distributed across the seasons. So we have plotted a few bivariate distributions so far, and we have done these individually. Now, in order to look for patterns, we may want to take in multiple columns and then come up with various combination of pairs and visualize whether any of those pairs of columns has a strong relationship. So one way to do that is to manually compute all the combination of pairs which we can get and then generate a joint plot for each of those combinations. Or we could simply make use of a Seaborn pair plot. Here, we can simply define a number of x variables and then y variables, and the pair plot will come up with all combinations of x and y and generate a plot for those and display them in a grid. So here, we can check whether each of those x variables are related to each of the y variables. So this will generate a grid containing 3 columns corresponding to the number of x variables and 2 rows which represent the number of y variables. Note that to this pair plot function, we have passed in our employee data frame. We have defined the height for each of the individual plots and set their aspect ratios to 1. And in addition to the x vars and y vars, we say that the kind of plot for each of these subplots should be a regression plot. This will produce a scatter plot which includes a best fit regression line. We also make use of the hue argument so that the individual markers in the scatter plot actually represent something. In this case, the color of the markers will indicate whether the employee had a recorded incident of disciplinary failure or not. And since this pair plot will include a number of subplots, we introduce some spacing between them in order to aid visibility. So when we render this pair plot, we end up with a grid of regression plots, and there is a legend which indicates what the color of the markers implies. There is also the spacing between each of the plots which we had defined. And finally, we can examine the data over here. So along the y-axis, we have for how many hours the employee was absent and also the employee's average workload each day. Along the x-axis, we have the distance from home to work for the employees along with their body mass index and their age. In each case, we wish to analyze whether any of these factors along the x-axis have any relation with the absentee rate and their workload. And strangely enough, there are no clear conclusions which we can make from this data. The plot in the top right seems to suggest that absenteeism is higher among the younger employees. One other thing we can note is that employees who have a recorded incident of disciplinary failure seem to be absent less and seem to have a higher workload than all of the other employees. So Seaborn is a data visualization library which is built on top of Matplotlib and provides a high-level abstraction over Matplotlib. With Matplotlib, it is possible to configure even the most minute elements of your plot. However, such fine-grained control is not possible in Seaborn. On the other hand, there are plenty of plot elements which we can configure, and this is what we shall explore in this demo. So once we have imported all the necessary libraries and disabled warnings, we will load in the UFO pollutants dataset into a data frame and limit ourselves to its first 1000 rows. Next, let us take a look at all the parameters which are available for us to configure with regard to the axes in a Seaborn plot. So for that, we call the axes_style function. And this gives us a dictionary, and the keys represent all the configurable parameters in the axes, while the values represent their current values. At the top, you can see that the face color of the axes is white, and the edge color is black. Note that W and K are the shorthand representations for white and black respectively. We can also see that the color map for images, that is the image.cmap, is viridis. So let us now use this default configuration and then plot a distribution plot. The data we will be using here is the nitrogen dioxide air quality index levels from our data frame. And we can make a few observations from the generated data. So the histogram and the KDE curve are both blue in color, and they are in a plain white background. The axes themselves and the ticks and all the labels are black in color. So now we set our own configuration for the aesthetics, and for that we make use of the set style command. So the basic style is going to be a white grid, but in addition we pass along a dictionary which contains all of the parameters which we wish to explicitly configure. In addition, we also configure our distribution plot where the color of our histogram and KDE curve has been set to maroon. So once our plot has been rendered, let us analyze some of the factors which we have configured. For one, by setting the style to be a white grid, this means that we have a white background and black grid lines. By setting the grid.line style to be dash and dot, the grid lines do indeed have a dash dot style. We also set the color of the histogram and the KDE curve to maroon, which has taken effect. And we also set the text labels for the axes to be green in color. Now, we make use of the Seaborn set function in order for the standard Seaborn aesthetic parameters to take effect. Calling this will affect all the subsequent plots in this notebook unless we explicitly set other style configurations. So very often when we generate a plot, we need to present it to someone else. This could be in the form of a presentation which is given during a meeting, or we might print out our plots and display it on a poster. So there are different contexts in which we'll need to present our plot, and for that, Seaborn has provided us with the setContext function. This allows us to specify 4 different modes or contexts for our plot, and Seaborn will automatically adjust details such as the labels, lines, grids, and other plot elements so that it is best suited for the context in which you are presenting your plot. We can take a look at what that means by first setting the context of our plot to talk. So this means that our plot will be shared during a presentation or a talk, and you can see that compared to the default, this plot contains fewer grid lines and the text is just a little bit larger. So Seaborn has optimized for visibility over detail in this case. If we set the context to poster, then visibility becomes even more important. And when we render this plot, we see that there are even fewer grid lines than in the talk context, and the text is just that little bit larger. If you'd like to display this graph in a research or technical paper, then you simply set the context to paper. The rendered graph this time has a lot more detail, there are more grid lines, and the text is a little smaller. And finally, if we simply wish to share our Jupyter notebook itself with all the plots, then we set the context to notebook. And this time, the rendered plot contains a lot more detail, which is in fact similar to the paper context. Also note that the notebook context is the default one. So even though we can use some of these built-in contexts provided by Seaborn, we can still configure some of the plot elements. So we once again make a call to the setContext function, and in addition to passing in the value of notebook, we set a value for the font scale argument so that it's 1.8 times its normal size. We can also pass in a dictionary of configuration options by making use of the RC argument. Here, we set the line width for all the lines in our plot to be 2, which is higher than the default 1. So when we render our plot this time, we can see that even with the same context of notebook, our plot does look a little different. I have included an image of the previous plot in order for us to do a quick comparison. So you can see here that the font is much larger in our new plot, and the width of the KDE curve is greater than it was previously. We now try to understand the concept of outliers in a distribution, and for that, let us consider an example of people being rated by their singing abilities. So towards the left, we'll have terrible singers, and towards the right, we have those whose abilities enable them to become professionals. So there will always be a few people who have terrible singing skills, but there will be several people whose abilities cluster around the average. On the other hand, there will be a handful of professional singers, but at the extreme end of the scale will be these once in a generation singers such as Adele or Aretha Franklin, whose abilities greatly surpass even that of other professional singers. These are the folks who are the outliers. One important thing to note is that outliers are very rare, and they can occur at either end of the distribution. So if we were to plot the frequency distribution of all the people in the world by their singing ability, then we would arrive at a plot which looks something like this, where most of the people will be clustered around the middle, representing an average skill level. At the extreme end on the right, you have both the professional singers and the once in a generation singers. Such a frequency distribution is called the normal probability distribution and is also known as the bell curve, since its shape resembles that of a bell. In fact, given a very large number of samples, most frequency distributions will resemble a bell curve. This is because being average is very common, while values which are too high or too low are very unusual. So while bell curves are common everywhere, this is especially true in the case of nature, where when you measure some aspect across a whole population, then its frequency distribution will resemble a normal probability distribution. So far in this course, we have plotted the relationship between two variables when the values of both of those variables were continuous in nature. In this demo, we will cover the situation when at least one of those variables is discrete. In such a situation, the data is said to be categorical because its value falls into specific categories. We begin this demo as usual by importing all the libraries which we require. Following that, we disable warnings again. And then we load our data set into a Pandas data frame. And the data we are using for this demo is the auto MPG dataset. So this dataset contains information about a lot of cars, including the number of cylinders in its engine, the total engine displacement, the horsepower generated, and so on. And it also contains the MPG or miles per gallon given by that vehicle. Note that these vehicles are rather old, mostly from the 1970s. So the first plot which we will generate from this data will be a box plot. But first, we set the size of our figure using plt.subplots, and this will be 12 units wide and 6 units high. And then we make use of the boxplot function in Seaborn in order to render a box plot. Its arguments state that the data for the box plot should be sourced from our car data frame, and that the x-axis will represent the number of cylinders of the vehicle, while the y-axis will represent the distribution of the values of horsepower for each value of x, that is, for each unique number of cylinders. In our dataset, there are only 5 unique values for the number of cylinders, so this will end up generating 5 different box plots. So let us go and see what that looks like. So you can see here that there are 5 different values for the number of cylinders, and for each of them, we have plotted the distribution of horsepower values. Now, just a few high-level observations from this. we can clearly see that the horsepower values are higher for vehicles which contain 8 cylinders than for any of the other vehicles. And not only is the horsepower value higher, but it's also more widely distributed for these 8-cylinder cars. Now, a box plot contains many different elements which we will examine in detail, starting with the whiskers, which are these vertical lines and generally represent the range of distribution of data. The boxes themselves represent the interquartile range of the data distribution. So the data from the 25th percentile right up to the 75th percentile. That is from the first quartile to the third quartile. And the median value is represented by the horizontal line within the box. Just a note here is that the length of the whiskers is either 1.5 times the interquartile range or extends until the highest or lowest element in the distribution. One more component of the box plot are the outliers. These outliers are so far away from the other data points in the distribution that they don't fall within the range of the whiskers. Now that we understand these details, we can interpret the box plot with greater clarity. So we fully understand now that the range of horsepower for the 8-cylinder vehicles is really vast, whereas that is certainly not the case for the 3-cylinder vehicles, and that there is a single 6-cylinder vehicle which generates about 170 horsepower, which stands apart from all the other cars which have 6 cylinders. Moving along now to a violin plot, which is essentially a combination of a box plot and a KDE curve. So while our box plot allowed us to view the distribution of the horsepower values, we had no real clarity about the density of the values in the distribution. And for that, a violin plot comes in handy. So when we render this, we certainly get more information about the distribution of horsepower. For example, among 4-cylinder vehicles, there seem to be more vehicles with a horsepower of around 70 or 90 than around 80. Even among the 8-cylinder vehicles, most of the vehicles seem to be crowded around the 150 horsepower mark. And another point to note is that the quartile range, the whiskers, and even the outlier seem to be part of the violin. We now move along to customizing our violin plot, and this time we will set a bandwidth for the KDE curve, and we set it to 3. And then we make use of the scale argument in order to scale the width of each of these violins to represent the number of observations in the corresponding bin. That is, the width of the violin will represent the count of values in the bin. So this time when the violins are rendered, we see that the curves are a little more smooth, which means that the bandwidth of 3 is higher than the default bandwidth which was used previously. And on top of that, a few more interesting things come to light. For one, there appears to be a large number of vehicles which contain 4 cylinders in our dataset, but there are very few which contain either 3 or 5 cylinders. This is the effect of scaling the width of the violin according to the count of vehicles. Moving along, we add further customizations to our violin plot. For one, we specify the inner argument to be equal to stick so that this effectively plots a ruck plot within the violin. We also set a lower bandwidth for the violins, and then we also specify a color palette to be used in this particular violin plot. You can think of a color palette as a set or range of colors which Seaborn will pick from when setting a shade for a particular object. So when we plot this violin plot, we see that there is in fact a ruck plot within the violins, and the colors of each of these violins is different from what we saw previously, because this time we're using the rainbow color palette rather than the default one. We move along now and combine our violin plot with another plot called the swarm plot. So this will plot a single marker for each data point in our dataset. We configure the markers to be black in color and specify a size of 3, which is smaller than the default of 6. The markers of the swarm plot will appear within the violins of the violin plot, which is why we set the inner argument of the violin plot to none, so that none of the lines within the violin plot will appear and interfere with the swarm plot. And when we render this violin plot, we can make a couple of observations. For one, there are no lines within the violins themselves, but with the swarm plot, we can clearly see that there are a very large number of 4-cylinder vehicles in our dataset, and the KDE curve very accurately traces the distribution of the horsepower values. Now that we have covered box plots and violin plots, we will cover some of the other plots which can be used to represent categorical data. But first, let us set a style for all the subsequent plots in this particular demo. And for that, we make use of Seaborn's set function, and we set the style of the subsequent plots to be a white grid. This will render grid lines on a white background. We also set the color codes argument to true so that we can use shorthand values for various colors. Moving along, the first plot which we will render is a strip plot. You can think of this as being similar to a scatter plot, except in this case, one of our variables is categorical in nature. Since this will plot a lot of markers, we set the size of the markers to 6. And when this plot is rendered, we can see that this is kind of similar to a swarm plot, but the markers are of different colors, and there appears to be a lot of overlap, which is not the case with a swarm plot. So when at least one of the variables we are plotting is either discrete or categorical, and there is a lot of crowding of points on our plot, then the solution is to add some jitter, that is to introduce some noise. So we call the strip plot function once again and set the value of the jitter argument to true. And on this occasion, the markers are just a little more spaced out than they were previously. Moving along, we create just a single swarm plot, that is without a violin plot this time. And when we render this, we see that there are markers for each data point in our dataset, and the color of these markers corresponds to the number of cylinders in the vehicle. Let us go ahead and change that, and we render the swarm plot once again, but this time the hue or the color of the markers will correspond to the origin of the vehicles. That value can be obtained from the origin column of our data frame. So when we render the plot, our swarm plot now contains different colors representing the origin of each vehicle, and there is also this legend in the top left to indicate which color corresponds to which country of origin. A few interesting details pop up in this plot, where all the 3-cylinder vehicles seem to come from Japan and all the 5-cylinder ones are from Europe. In addition, most of the 6-cylinder vehicles and nearly all of the 8-cylinder ones were made in the United States. Now, let us plot the exact same information, but instead of a swarm plot, we make use of a bar plot. So the graph that is rendered creates one bar for each combination of number of cylinders and origin. The height of the bar corresponds to the average value of horsepower for that particular combination. There is also a vertical line which represents the overall distribution of data. At this point, we take a look at one more plot which renders a bar for different categories, and this is a count plot. You can think of this as being similar to a histogram in that it shows the number of data points for each category. The category for our count plot is going to be the origin of the vehicles, while the colors for each of the bars will be picked from the accent color palette. The result shows us that there are nearly 250 vehicles in our dataset which originate in the United States, and there are far fewer from Japan and Europe. We now explore the point plot, for which we once again map the horsepower versus the number of cylinders. And this ends up rendering a line which connects a number of points. Each of these points represents the mean value for each category, that is, the mean horsepower for each number of cylinders, while the vertical lines represent the central tendency. We now move along to rendering a number of different categorical plots in a grid. For that, we make use of the catplot function, and here we specify using the kind argument that the specific type of categorical plot we wish to render is a box plot. By setting the value of the row argument to origin, we are saying that we would like a different box plot to be rendered for each value of origin, and these will appear on different rows in a grid. So when we plot this, we see that our cat plot is indeed a box plot, and the top row in this cat plot contains a box plot for all vehicles which originated in the United States. Moving further down, we see that there is a separate row for vehicles from Japan, and then right at the bottom is the box plot for vehicles from Europe. When our dataset contains discrete or categorical data, it is possible that we may need to plot a separate graph for each different category. For example, if your dataset contains information about automobiles and there is a categorical column about the type of car, whether it's a sedan, hatchback, or SUV, then you may want to generate the same graph for each type of vehicle. In such a case, rather than you having to divide your dataset depending on the type of vehicle and then generating a separate plot for each, Seaborn provides us with something called a facet grid. This allows you to create a separate plot for each category present in a column, and they will all be laid out in a grid structure. Let us see exactly what that looks like. And for that, we once again begin by importing all the required libraries into our Jupyter notebook and then disabling warnings. The dataset we will use for this demo is the Zomato dataset. So Zomato is a restaurant searching service which is popular in India, Turkey, Portugal, and a few other countries, and it is similar to Yelp in the United States. So we will load the dataset from our datasets directory into our data frame, and then we can take a look at our data. So you can see here there is information about a restaurant ID, its name, its location, and so on. But we are only interested in some of these columns, such as the price range, the aggregate rating, and the currency, which we will soon see later in this demo. We then make use of the data frame's describe function in order to get a summary of all the numeric columns in the data frame. So the price range column in this dataset is numerical. However, it also takes the discrete values of 1, 2, 3, and 4, which makes it categorical. 1 represents the more economical restaurants, while 4 represents the more expensive ones. The aggregate rating for a restaurant can take any value between 0 and 5. Here we see that the maximum value is 4.9. So we now move ahead and plot our first facet grid. So as mentioned earlier, a facet grid allows us to plot a different graph for each category present in a range of data. Here, when we initialize our facet grid with the Zomato data, we specify a column of price range. This means that the facet grid will contain a different column for each different value of price range in the dataset. And when we plot this empty facet grid, we see that this contains 4 columns, one for each value of price range which is available in the price range column. Just as a reminder, the values of price range in this dataset are either 1, 2, 3, or 4. So one obvious thing about this facet grid is that it represents no data at all. Well, we need to map some data onto a facet grid, which is exactly what we shall do now. So we recreate the same facet grid as we did before, but this time we use the map function of a facet grid, where we specify the type of graph we would like the facet grid to generate, along with the data which needs to be represented in the graph. So on our facet grid, for each unique value of price range, we would like there to be a separate graph which shows the distribution of data for the aggregate rating in the form of a histogram. And once our facet grid has been generated, So clearly there are a lot of restaurants with no ratings in the price range of 1, and most of the ratings seem to fall between 3 and 4. The heights of the bars also indicate that there are more restaurants in the lower price ranges than in the higher ones. So now that we have plotted a univariate distribution on our facet grid, let's move along to some bivariate analysis. So this time we regenerate the same facet grid with a different column for each price range, but we use the map function in order to generate a scatter plot, and this will plot the number of votes cast for a restaurant against its aggregate rating. The markers of our scatter plot will be a shade of gray since we are representing a grayscale value between 0 and 1. And once our scatter plots have been rendered, we get the relationship between votes and aggregate rating. And we can see here that there seem to be a lot of votes in the price range of 3 for the more highly rated restaurants. So while our previous plot did convey some useful information, we can convey even more data in our plots by making intelligent use of the colors of the markers. That is exactly what we're going to do here, where we regenerate essentially the same facet grid, but this time when initializing the facet grid itself, we specify a value for the hue argument, which says that for every subplot in this grid, use a different color for every unique value of currency. So our data set only has a country code and not the name of a country. So here we are going to use the currency column as a proxy for the country where the restaurant is located. Within our scatter plots, we set an alpha value of 0.5 so that our markers are translucent. And this time, when our facet grid has been rendered, we see that there is a different color for each different value of currency, and the mapping of color to currency is available in this legend on the right. Now, most of the restaurants in our dataset are from India, but there are also a fair number of Turkish restaurants. So the facet grids we have plotted so far have contained a different column for each unique value of the price range. That is, we're using just a single column from our data set for the different categories. We will now use two different columns in our data set in order to get a matrix of categories. So there will be a new row in our facet grid for each type of value has online delivery column. The values there are simply yes or no, so it has two unique values. And when combined with the price range column, which has four distinct values, our facet grid will end up having 2 rows and 4 columns. We also specify the margin titles argument so that the row categories are displayed. And this time on our facet grid, we will plot a regression plot or reg plot rather than a scatter plot. However, we will set the fitreg argument to false so that a regression line is not displayed. This will in effect create a scatter plot. So when we plot this facet grid, which contains both rows and columns, you can see that there are 2 rows here, one for restaurants which do have online delivery and another for restaurants which don't. And by enabling margin titles, we can also see the labels along each row. So by using 2 different columns containing categorical data, we have obtained a grid which has 8 different categories. Some of the insights which we can make over here is that while there are several Turkish restaurants which do not offer online delivery, there are almost none in our dataset which do. So by using a facet grid in order to get these 8 different categories, and then by using colored markers, we are able to perform a rather detailed analysis. Our graphs are able to convey a lot of information than just a single plot would be able to. And we're able to do all this with just a few lines of code. So when we have multiple plots displayed on a facet grid, it is likely that not all of the graphs are of equal importance. There may be specific graphs which you wish to highlight and maybe make larger than all of the other plots on your grid. One way to do that is by specifying the grid spec underscore KWS argument on your facet grid, to which you pass along a dictionary containing a list of width ratios. So over here, we specify ratios of 2, 3, 5, and 3 so that The third column, that is restaurants with a price range of 3, will appear larger than the others, and the restaurants in the price range of 1 appear smaller. And on plotting our facet grid this time, we do see that the width ratios have taken effect. So this will draw more attention to the restaurants with the price range of 3, while still conveying information about the other restaurants. We now move along to a different kind of plot, where we will be plotting the average cost for 2 against the aggregate rating for a restaurant using a bar plot. And in the facet grid, we will have a different column for each value of the currency. This is because the average cost for 2 is expressed in the local currency for the restaurant, which is why it is good to separate the restaurants by currency when we wish to measure the cost. So this time when we plot our facet grid, we see that since there are a number of different currencies represented in our dataset, the number of columns is also very large, and the result is that each of the individual plots are too small for us to make sense of it. Zooming in on our screen is one option in order to view the plots, but this is far from ideal. Or we could have a plot for each currency along the rows of our facet grid. But in this case, we will just have a single plot per row, and we won't be making optimal use of the space available to us. Well, to account for this, Seaborn provides a column wrap or call wrap argument for the facet grid. So when we set this to 3 and then render the plot, our columns have now effectively wrapped around such that there are just 3 plots per row. So all of our 11 columns have now been extended across 4 different rows. At this point, it becomes easier for us to analyze each of these plots and glean some information out of them. So you can see on the right that among Turkish restaurants, there are a number of low-rated restaurants which have a rather high aggregate cost for 2. However, the highest rated restaurants also seem to have a higher average price. Facet grids allow a few customizations. So in this case, we will set the aspect ratio for each of the individual plots to be 1.5. So this is done at the level of the facet grid. And then within our individual bar plots, we set the colors of the bars to some hexadecimal value. So this is going to be some kind of purple color. And on plotting the facet grid, we see that these changes have taken effect. We will now explore some more aesthetic configurations. So we recreate the same facet grid, but we set a lower value for the column wrap. And this is because we're going to introduce some spacing between each of the plots. So here we set some width and height space between each of the plots. And then we also define the axis labels to use. So with these changes, let us replot the facet grid. And we see here that our width space and height spaces have taken effect. And you will observe that our custom labels have also taken effect along the axes. Seaborn provides a number of options in which to configure the aesthetics of your plot. One of the key factors which affect a plot's appearance are the colors of the individual elements. When Seaborn has multiple elements to color within one plot, it picks the colors from something called a color palette or color map. The colors within a color palette have a particular sequence, and Seaborn will cycle through each of these colors. There are multiple color palettes which are already built into Matplotlib and are therefore available in Seaborn, and we will take a look at some of those, as well as explore some of the other options around color palettes in this demo. We begin once more by loading all the libraries which we need, and then we import the UFO pollutants dataset. This dataset contains records of the levels of various pollutants recorded in specific cities in the United States over a few years. Once we load this data from the CSV file into a Pandas data frame, we restrict ourselves to just the first 1000 rows of it, since this is a really large dataset. We then quickly preview it using the data frame head function, and we observe that the pollutants which this dataset has records for include nitrogen dioxide, ozone, sulfur dioxide, as well as carbon monoxide. So now we wish to examine the distribution of data in two of the columns in our data frame, specifically the so2.first.maxr and the co.first.maxr, which represent the hour of the day in which the highest levels of SO2 and carbon monoxide were recorded. But first, we will set the color palette to be used in this distribution plot. Since there will be two histograms which will be drawn, there will be two different colors which this plot will contain. Those colors will be picked from one of the built-in matplotlib color palettes called set1. Do keep in mind that once we call the setPalette function this way, it will set the color palette to be used for all the subsequent plots within this Jupyter notebook, unless it is explicitly changed to something else. We also make use of matplotlib's pyplot library in order to set the size for the figure. So once this plot has been rendered, we can make a few observations. The first color in the set1 palette is a shade of red, which is why the first distribution plot here, which represents the SO2 max R, has both its histogram as well as the KDE curve, which the distribution plot generates, shaded in red, while the corresponding carbon monoxide plot is in blue. This is because blue is the second color in the set1 palette. Notice here that the two tallest bars in this graph are both blue in color, representing the R of highest recorded carbon monoxide levels. Next, we redraw the same plots, except this time we flip the order of the two. That is, we draw the carbon monoxide plot first, followed by the SO2 plot. And we don't need to call the setPalette function once more, because the set1 palette is now the default for all the subsequent plots within this notebook. So let us now replot these distribution plots. And we see here that the colors of both the bars and the KDE curves have now flipped, simply because we switched the order of the two distribution plots. So the way Seaborn and also matplotlib work is that when there are multiple objects which need to be colored, it will cycle through each of the colors in the color palette in a particular order. So previously, when we made a call to the setPalette function in order to set the color palette to set1, that meant that the default color palette for all the subsequent plots within the notebook would be set1. So that is a good way to set the default color palette for a notebook. However, there may be cases where you'd like to make an exception from the default. The way to do that is to make use of the with keyword, and any color palette set with that will only apply to all the plots which are defined within the with block. So here we set the accent color palette, and this should apply to the two distribution plots defined within the with block. In fact, that is exactly the case. But now outside that with block, if we were to redraw those two distribution plots, then the set1 palette is in effect once more. To the right is an image of the previous plot generated using the accent color palette, just for comparison. We now make use of the Seaborn set function in order to set the Seaborn standard aesthetic configurations. This includes the color palette as well as the style elements for all the plots. Our focus here is on the color palette though, so we make use of the Seaborn color_palette function in order to retrieve the current color palette. We then make use of the palette plot or palplot function in order to display the color palette in our Jupyter notebook. So we see here that this color palette contains exactly 10 colors and is in fact the tab 10 color palette. Since this color palette contains 10 discrete colors, it is very useful to plot categorical data. Such color palettes are known as qualitative color palettes. Also note the order of the colors here, where we begin with blue and then go into orange, green, red, purple, and so on. Now, we will generate multiple plots over here and then see what the colors are for each of these individual plots. So once we have defined some of the parameters for our plot, including the font scale and the line width, we define a number of KDE plots, that is 5 plots in total. And each of these will generate the kernel density estimation curve for the nitrogen dioxide air quality index data in our data frame. Though all of these are KDE curves representing the same data, they will all appear different because of the different bandwidth values we have set for them. So just to summarize, the bandwidth will define how smooth or jagged the curve is. Since there are 5 different KDE plots here, we expect their colors to be the first 5 colors in our color palette. So once this plot has been rendered, we see that that is in fact the case. From the labels of these plots, which we see in the legend, we can see that the color has been picked in the same order as they appear within our color palette. One thing to note that matplotlib and hence Seaborn will cycle through the colors in a color palette. So in our previous plot, the 5 plots which were rendered used the first 5 colors from our color palette, which consisted of a total of 10 colors. However, if we had generated 11 plots, then the 11th plot would have taken the same color as the first one. So you can imagine that it's important that we don't really run out of colors, which is why there are certain color palettes which we can use where we can specify the number of colors it needs to generate. One of these is the HLS color palettes, and HLS stands for hue, lightness, and saturation. So here we create an HLS palette which contains exactly 8 colors, and then when we render it using PAL plot, we see that we get 8 colors in our color palette. We create one more HLS palette, but this time with 12 colors, and this time we have the larger HLS palette created for us. So these palettes are very useful when you would like to set the number of colors. There are other configuration options possible when we create an HLS palette, but this time we define an HLS palette rather than a regular color palette. The arguments we pass to it include the number of colors for our HLS palette, along with the lightness and saturation levels. So when we render this HLS palette, you will observe that it contains the exact same shades as the 8 color HLS palette at the top of the screen, except that everything is just a bit darker. We move along now to sequential color palettes. So we have seen that qualitative color palettes are very useful for plotting discrete data. This is because there is often a large variation in shade between 2 colors in the palette which are right next to each other. For example, in the tab 10 color map, which is the default, the first 2 colors are blue and orange. However, if you are plotting continuous data, then it is good to have the colors in a color palette laid out in a sequence such that the adjacent colors are not that different from each other. This is where sequential color palettes fit in, and let us take a look at one over here called Viridis. And you will observe that there appears a very close resemblance between the adjacent colors. One thing to keep in mind is that even though the palette plot function has shown a number of discrete colors over here, this Viridis color palette is in fact a range or spectrum of colors. We will show that now by generating a heat map. So a heat map is a very good way to show the correlation between various variables in a dataset. This correlation will be a continuous value in the range of -1 to +1. It makes a good variable to illustrate the power of using sequential color palettes. So the columns in our data frame which we wish to include in our heat map are the mean values for NO2, CO, SO2, and O3. So we get a reduced data frame containing only those columns. Then we make use of the core or correlation function of the data frame object. And this will generate a correlation matrix. Since our data frame has 4 columns, the correlation matrix will be a 4 by 4 matrix containing the correlation values for the corresponding pairs of variables. We then make use of the Seaborn heat map function, to which we pass along our correlation matrix, and we supply a lot of configuration options for this heat map. Right at the bottom is the Viridis color map which will be used for it. We also say that this correlation matrix must be a square, and that we need to include the annotations, that is the numerical values for the correlations. Once we generate this plot, we can view our heat map. So one thing to note here is that all the high positive values are a shade of yellow or green, and all the low values are a shade of blue. The entire spectrum of colors in the Viridis color map is visible along the right of this plot. It should be clear now that a sequential color map is very useful when you are plotting a continuous range of data. So far, we have only made use of the built-in color maps of Matplotlib in our demo. So is it possible to define our own color maps or color palettes? The short answer is yes. So here, we call the Seaborn color palette function and we pass in a list of 5 different colors represented in the hexadecimal numbers. And then when we plot this, we see that our 5-color color map has been created. In this exercise, you will recall how earlier in this course, we divided our data into specific categories based on a particular categorical value x, and then used a couple of different methods in order to visualize a summary of the distribution of a value y based on the value of x. In less abstract terms, if you had data concerning 3 different types of vehicles, sedans, SUVs, and hatchbacks, and you wanted to plot the distribution of the values of their price for each of those types of cars rather than all the cars collectively, what would you use in Seaborn? Next, if you needed to generate multiple plots for different combinations of 2 categorical variables A and B, what exactly could you use in Seaborn? Think of a grid structure which you could use in order to plot this. For the next task, imagine that you need to share all your plots with a number of different people using different media. Some of your audience is focused on the overall visibility and readability of your plots and less focused on the details, whereas the reverse is true for some of the other audience members. Rather than individually configure the components of your plot, what Seaborn feature could you use to generate shareable plots based on a particular context? And finally, you will recollect the instances when it is best to use qualitative color palettes, and then other cases where you will need to use sequential color maps. The aim of this exercise is not to generate code which compiles and executes correctly, but to understand the various objects and functions which you may be able to use in order to perform these operations. So do try to perform these tasks on your own. The first task was to come up with a way in which to summarize the distribution of a variable y within different categories based on a value x. One of the Seaborn plots which we used in order to plot such a distribution was a box plot, where you will recall that the box represented the interquartile range for the distribution. The box plot also included whiskers which extended from the box and went up to 1.5 times the interquartile range beyond the box. There were certain data points which did not fit within the range of the whiskers, and these were marked as outliers. We also covered violin plots, which are in many ways similar to box plots, but the rectangular boxes were in fact replaced by a KDE curve. This KDE curve allowed us to visualize the distribution of data within the box itself. The next task in the exercise concerned generating multiple plots depending on various combination of values for 2 variables A and B. The way to do that is to make use of the Facet grid, which will essentially generate a grid or matrix of plots for all possible combinations of A and B. Once we have defined our Facet grid, we can then go on to define the individual plots which will be included within the Facet grid by making use of the facet.map function. The code which you see on your screen will generate multiple regression plots in a Facet grid. The next task involved using some of the built-in Seaborn styles in order to render plots which make it easy to share depending on a particular context. So if we make use of the set underscore context function, there are 4 different contexts which Seaborn currently supports. One of these is if you'd like to share your plot within a technical paper. Another is when you'd like to share your plot within a Jupyter notebook. There is a Seaborn style which makes it easy for you to present your plot during a presentation or a talk. And when compared to the previous context, the talk context has larger text but will be missing some of the finer details of the plot. And finally, there is also a poster context, which in fact makes your text even larger and eliminates even more of the details of your plot so that it is best suited to be presented on a poster. And finally, we wanted to compare qualitative palettes with sequential ones. And qualitative palettes, as we had seen during the demos, are better suited when used to represent categorical data. This is because Seaborn picks the colors out of the palette in a sequence, and the adjacent colors in qualitative palettes vary a lot. So different categories will be represented in sharply contrasting colors. On the other hand, if you're using colors in order to represent continuous data, then sequential palettes are the best suited for this task. The use of sequential palettes allows somewhat similar values to have somewhat similar shades, and then vastly different values will have very contrasting shades. This allows you to visualize very quickly whether two values are very similar to each other or very different.
An important component in analyzing data is visualizations. Visualizations is what allows us to explore relationships that exist in data. In the Python ecosystem, there are a vast number of libraries that allow you to visualize your data. Some of these are Matplotlib, Seaborn, Plotly, Bokeh, and so on. Pandas visualizations are built on top of Matplotlib, which is the most popular visualization library. Pandas offers the data frame data structure which you can use to store and manipulate data. You already have the data stored in the format that is easy to work with. It makes sense to integrate visualizations into the Pandas library itself. Let's get started. The name of this IPython notebook where we'll be doing this demo is called Visualizations. Because you're working with Pandas, I assume that you already have Pandas installed on your machine. We're working on Jupyter IPython notebooks and on Python 3. If you don't have the Pandas library installed, you can get it with a simple pip install. If you run the pip install command within your Jupyter notebook, make sure you precede it with an exclamation point. Exclamation point pip install pandas dash dash upgrade. Once Pandas is installed on your machine, simply import the Pandas libraries and alias it as PD. It's common to alias Pandas as PD for ease of use. In addition to Pandas for visualization, we'll also work directly with the Matplotlib library to visualize our data. Import the pyplot module from within Matplotlib as plot or PLT. If you do not have Matplotlib installed, you can get that with a simple pip install as well. Pip install matplotlib dash dash upgrade. We'll work with the countries dataset that we've seen in an earlier course. The only columns that we are interested in from this dataset are country, region, population, coastline, GDP, literacy, and birth rate. Specify these as a list assigned to the required calls variable. The data is in the form of a CSV file under the datasets folder in the current working directory. We'll use the pd.read underscore CSV function in order to read in this data. The input arguments to this function are the relative path to this dataset, datasets / countries of the world.csv. The columns that we want to read in are the required columns that we specified earlier, and we want to convert the decimal point notation from commas as it exists in the dataset to periods. As we've seen earlier, there are a number of columns here whose names are a little hard to work with. Let's rename these columns so that they have easier names. These are the GDP, coastline, and literacy columns. We are going to rename them to per capita GDP, coastline area ratio, and literacy rate. We want the result to apply to the country's data frame itself, which is why the argument in place is equal to true. From our earlier explorations in the previous course, we know that there are missing values in this dataset. Let's go ahead and drop any rows which have field values missing. This we do by calling the countries.dropNA function. The resulting data frame with no missing fields is assigned to the countries variable. Countries is equal to countries.dropNA. Let's explore the records in countries right now by calling countries.head. This displays the first 5 records in this dataset. And here on screen, you can see the country name, region, population, coastline area ratio, per capita GDP, literacy rate, and birth rate for Afghanistan, Albania, Algeria, American Samoa, and Andorra. If you want to get all of the unique regions represented in this dataset, you can simply access the region column by calling countries.region and call the unique function. This will list out unique regions, which is Asia, Eastern Europe, Northern Africa, Oceania, Western Europe, Sub-Saharan Africa, Latin America and Caribbean, and so on. You can see that the regions here don't really correspond exactly to continents, but they are close. We've already performed some basic statistical exploration of this dataset. Let's now find some aggregates of the data that we hold. Pandas allows you to group your dataset just like you can do with, say, SQL queries. You can call group by on your data frame and specify the column you want your data to be grouped by. Here we are grouping by the region column. We want to group our data by region and perform a mean operation. So we group by region and we'll calculate the mean of all other columns so that we get regional data. The resulting average by region data frame contains one row or one record for each region. You can see the regions at the very left. That is the first column. The remaining columns are average measures for that particular region. You can see that the average population of Asia, all the countries in Asia, is roughly 131 million. The average per capita GDP for Asia is roughly $8,000. The average literacy rate is around 80%, and so on. Let's take a look at the same statistics for Western Europe. You can see that the average population of a country in Western Europe is 17.2 million. That's much lower than in Asia. The average per capita GDP is $28,350. So that's a huge difference as well. And the average literacy rate is 98%. Without knowing anything about the world as a whole, this simple grouping operation and the finding of averages allows us to see that Western Europe is probably far more developed than Asia. This is, of course, only on average. Individual countries might differ. And to keep things interesting, you can quickly take a look at the same average measures for Northern America. Average population 82.9 million, per capita GDP 27,625. So you can see that Northern America is kind of like Western Europe. Exploring data in a tabular format is great when we have just a few records, but if we have a huge number of records, it's really helpful for us to plot graphs. Here, we are going to plot a bar chart for the birth rate by region. Average by region is the grouped data frame that we had created before. We access the birth rate column and call the plot function on it, and we specify the kind of chart that we want to plot. Kind is equal to bar. The plot.show function in matplotlib will display this plot to screen. When you execute this cell using Shift Enter, you'll find a bar graph is drawn. Our data was stored in Pandas and we plotted a bar graph of the birth rate series column, and it has automatically picked up the region as the x-axis values. And the actual bar represents the birth rate for each region. And there are some interesting findings here. You can observe that the birth rate is the highest in Sub-Saharan Africa. The birth rate here is around 35. And you can see that the birth rate for more advanced or more developed countries, which are mostly in the Baltics or maybe Western Europe, are far lower. Both Western Europe and the Baltic region have a birth rate of under 10. When you visualize data using Pandas, specifying customizations is also easy. Once again, we want a bar plot to represent birth rate, but this time we want it to be a horizontal bar, not a vertical bar. In addition, we also want a customized title for this matplotlib plot. Average birth rate by region is our title. Bar H is the kind you specify when you want to plot horizontal bars using Pandas. The chart below displays the same data that we've seen before, birth rate by region. This time it has a title and the bars are displayed horizontally and the regions are specified on the left-hand side. Pandas makes it very easy for you to slice and dice your data and extract only those columns that you're interested in. We're working with the original country's data frame and we specified the list of columns that we want to extract from this data frame. This is the region and population column. This gives us a resultant data frame with just two columns, one for region, one for population. And we group this data frame by region and perform the sum aggregation. This will give us the total population for each region. Display the results stored in the population by region variable, and you can see that we have the region as the first column and the total population for each region is the second column. We've selected only those columns from the original data frame that we were interested in to perform the aggregation operation. Once we have the population data on a per region basis, let's plot it as a pie chart. We call pop by region, that's the data frame, dot plot dot pie. We pass in the name of the column that we want to visualize as a part of this pie, that is the population column. In addition, the fig size is the matplotlib parameter to specify the size of the resulting plot. The fig size here is 8 inches by 8 inches. And here displayed on screen is the resulting pie chart along with the legend for this pie chart. The plot.pie function is what displays this pie chart. It's pretty obvious from this pie chart here, not that we didn't know it before, but over 50% of the world's population lives in Asia. And the smaller portions of the pie represent the other regions, Western Europe, Sub-Saharan Africa, Latin America, and so on. The matplotlib library supports many customizations, and you can access these customizations from within Pandas as well. Here is the same pie chart that we've seen before. In addition to plotting the population and using the fixed size of 8 inches by 8 inches, we do not want to display the legend. We pass in legend equal to false to the pie function, and in addition, we pass in cmap is equal to set3. Cmap stands for color map and is used to customize the colors in which the pie sections are displayed. Set3 is the name of a color palette that matplotlib supports. And here is the resulting pie chart. The data that it visualizes is the same population data. However, the colors are all different and the legend has disappeared. We've already studied the describe function that we can invoke on Pandas objects. We've seen describe used with data frames. You can call describe on a Pandas series object as well to get basic statistical measures for a particular column. Here are the statistical measures for the birth rate column. There are 207 rows with birth rate information. The mean birth rate is 22, the standard deviation is 11, min is 7, and the max is 50. There is actually a very interesting plot that is typically used to visualize the mean, median, and quantile information. This is a box plot. We can use Pandas to visualize the statistical information as a box plot by simply calling the plot function on a Pandas series and specifying kind is equal to box. And here is the box plot, which gives us all of the statistical information about birth rate at a single glance. You can see that there is a box at the very center and there are whiskers extending from the box. The horizontal line drawn at the center of the box is the median of our data. So you can see that the median birth rate across all countries is a tad under 20. The edges of the box typically correspond to the 25th percentile and the 75th percentile of our data. You can see that the 25th percentile is a little above 10 and the 75th percentile for the birth rate is a little under 30. And finally, we have the whiskers. The upper whisker gives us the upper range of our data and the lower whisker represents the lower range of the data. The maximum birth rate across all countries is at 50 and the minimum birth rate is around 7. Pandas has support for other common visualizations as well, such as histograms. Histograms are what you use when you want to divide your data into buckets and plot a frequency for each bucket. Here we want to plot a histogram on the birth rate column, and if you see the resulting visualization, On the x-axis, we have birth rates ranging from 0 to a little over 50. This range is then converted to buckets, and on the y-axis, we have the number of countries that fall into each bucket. The first histogram bar should tell you that in the birth rate range 7 to 15, there are roughly 40 countries. Let's explore a few other customizations that you can set up when you visualize your data. Here we're going to plot a histogram, but this time we set the parameter grid is equal to true. Grid is equal to true will overlay a grid on top of our chart, which will allow us to view the values easily. There are two ways to plot a particular visualization in Pandas. You can call the plot function and specify a kind of chart as a parameter value, or you can call the function directly. Here we access the birth rate column in the countries data frame, country square brackets birth rate, and call the .hist function to display a histogram of this data. This is the same histogram that we plotted just a minute or so ago by calling the plot function and passing in kind is equal to hist. You can customize your histogram by changing how you bucket your data on the x-axis. You can specify the number of bins for each histogram. Here we plot the same histogram with 20 bins. By default, the histogram is plotted with 10 bins, and here is the same histogram this time with 20 bins, and you can contrast it with the earlier histogram that is off to your right. Increasing the number of bins that you display in your histogram will give you a more granular representation for your data. Let's see one last plot before we complete our exploration of visualizations that Pandas supports. This is a scatter plot. On the x-axis, we have the per capita GDP, and on the y-axis, we have the literacy rate. In an earlier analysis, we'd seen a high correlation between literacy rate and the per capita GDP, and we can see whether the scatter plot represents this high correlation. Take a look at the resulting scatter plot. On the x-axis is the per capita GDP, and on the y-axis is the literacy rate ranging from 0 to 100. And the per capita GDP ranges from 0 to above 50,000. You can see that this plot shows a strong correlation. However, there are definitely countries with a high literacy rate but with a low per capita GDP, as you can see from the cluster on the top left of this graph. Let's plot another scatter plot of the same information, but this time we'll make two changes. The first is an obvious change. We change the color of our dots to be purple in color, and we also move the x-axis to be the per capita GDP, and the y-axis is the birth rate. This is the visualization that we'll use in order to see whether there is indeed a relationship between birth rate and the per capita GDP. Most of the countries are clustered at the bottom left of this graph, low birth rate and low per capita GDP. But if you notice the countries which have a high per capita GDP, they typically tend to have a birth rate of under 20. If you're working with this data set in the real world, there is some correlation here that bears further exploration. Pandas offers extremely useful functions to deal with time series data, and that's what we'll work with in this demo. We're going to write all of our code in the time series Jupyter notebook. Time series data is data that is associated with a certain point in time. This can be a second, a day, a minute, any point in time. A common example of time series data is stock market prices. I'm first going to import the libraries that I need for this demo. I'm going to use the Pandas library. That's what this course is about. We'll use the pyplot module from the matplotlib library. We'll also use numpy. The numpy Python library is the standard library used to work with multi-dimensional data in Python. If you don't have numpy installed on your machine, you can get it using a simple pip install. Simply type in !pip install numpy -- upgrade to install the latest version of numpy on your local machine. The time series data that we'll work with is stock market prices. This is for Amazon's stock over the past several years. This data is present as a CSV file under the datasets folder. Use the pd.read_csv function and specify the path to this file to retrieve this data in the form of a data frame. That is the Amazon data frame called the head function in order to explore this data. This dataset contains the prices of Amazon stock starting from 2008. These are prices from the NASDAQ index. For each day markets were open in the US, we have the open price of the stock, high price, low price, close, adjusted close, and the volume of the stock traded. There is an integer index value associated with each row. In addition, we have a column for date. You can see that the date starts on 8th December 2008. And for each of these days, here is the stock price information that we have available as a part of this data set. When you read in a data frame from a CSV file, by default, Pandas assigns integer index values to each row. You can see that the index is a range index starting at 0 and going up to 2517. Here we access the date column using square brackets, Amazon data square brackets date, and call the head function, which will display the first 5 records with the date information. When we read in data from a CSV file, the default data type for all of our columns is object. Even though this column is clearly a date, the D type here is object. Let's change that. Pandas offers a very helpful function to convert an object to be of type date time. pd.toDateTime is what we use, and we pass in the values of the date column. This will convert all of the dates which are currently of type object to be of type date time. And once this conversion has been performed, we can perform manipulations on date time values. Observe that we set the index of our data frame, Amazon data.index, to be the dates of the individual rows. We don't want our indexes to be the default integers. Instead, we want the dates associated with each record to be the index value. If you display the index, you'll now see that we have a date time index with date values starting on 8th December 2008 and going up to 6th December 2018. We've changed the index of the Amazon data frame. Let's take a look at the data now and observe that the index column at the very left is of type date. The index column is always the first column and it's always displayed slightly in bold, which makes it easier for you to identify. In addition, the original date column continues to be part of this data frame. You can see that the first column here after the index column is the original date column. The original date column is no longer needed now that we have a date time index. Let's go ahead and get rid of that column by using the del keyword. So del Amazon data, and within square brackets specify the column that you want to delete. If you now take a look at your data frame, you'll find that that date column has disappeared. The data frame that we are going to work with now has a date time index, that is the leftmost column displayed, and the other columns are open, high, low, close, adjusted close, and volume. Amazon underscore data dot tail invokes the tail end and displays the tail end of the records present within this data frame. You can see that we have records all the way up to 6th December 2018. Let's see the trend of this time series data. Let's plot a line graph. So we access the adjusted close column. That is the data that we want to plot in this line graph, and call plot and specify kind is equal to line. We specify labels for the X and Y axis. The X label is year and the Y label is the closing price for Amazon stock. The index automatically becomes the X axis data. Well, if you've held Amazon stock, it's good news for you. You can see that Amazon stock price has been slowly rising till at the middle of 2018, it touched $2,000. Notice that the index values, that is our date time index for individual days on which we have the adjusted close price, automatically become the X axis, and on the Y axis, we have the adjusted close price. Just like with the regular range index, you can use the date time index to access specific records. So we want the adjusted close on 12/12/2008, and on this day, Amazon stock price closed at $51.25. Let's see the adjusted close price on 29th November 2018 to see what the difference is. And you can see on this day, the stock price closed at almost $1,700. Once you have your index as date time values, there are some interesting aggregations that you can perform. Here we use the resample function to sample our data month-wise, and after we resample by month specified by capital M, we want to calculate the mean adjusted close for each month. And here is the average monthly adjusted close price for Amazon stock starting with December 2008. Observe the index values of this resampled data. Each index value represents a particular day in a particular month. The date here is the last day of each month: 31st December, 31st January, 28th Feb, and so on. You can perform a month-wise aggregation using resample and specifying capital M for month, and you can calculate other aggregations such as median as well. And this result here is the monthly median of Amazon's stock price starting from December 2008. Once again, you can see that the index for the resulting data frame is one value for each month, the last trading day in each month. Now that we have the median closing price for Amazon stock per month, let's plot this as a simple line graph. Monthly median dot plot by default will plot a line graph if you don't specify a graph type. And here is the line graph showing how Amazon stock price has moved. Let's perform a little bit of customization here. Let's say instead of a simple line graph, you want an area chart. Simply specify kind is equal to area on the same data set. And here is the area chart showing the monthly median of Amazon's closing price starting from 2008 onwards. When you have time series data, the data has a natural order, starting from the beginning of time to the end of time as specified by your data set. You can calculate the difference between individual records by calling the diff function. We call the Pandas diff function on the adjusted close price to find the difference or a delta between the stock price from one day to another. Let's store this in the Amazon deltas variable and explore the first 10 records. Observe that the record for the diff value for the very first day is not a number, which makes sense because there is no previous day which you can use to calculate the delta for this particular day. All other records will have logical values. In this result, you can see in dollar terms how Amazon's stock price moved from one day to another. Finding deltas in terms of absolute dollar values is interesting but not really very useful when you're dealing with stock market prices. What you're really interested in is the percentage change from one day to another. A change of $1 when the stock price is 50 is more significant than a change of $1 when the stock price is at say 2000, which is why the percentage change is more important. This is what is referred to as returns. Pandas offers a built-in function for you to calculate the returns for a particular series, PCT underscore change. Let's take a look at the Amazon returns series in order to see the percentage change in Amazon stock from one day to another. As usual, the first record will have nan because there is no previous record to compare it with. Another interesting operation that Pandas allows you to perform with time series data is the calculation of moving averages. You might want to select a window of records from your time series data and perform some kind of aggregation such as mean. Let's see a moving average over every 5 trading days of Amazon stock. So we specify a rolling window of 5 records. This window will include 5 records at a time. A rolling window basically means that it will first select records 1 through 5, 2 through 6, then 3 through 7, and so on. And for each of these windows with 5 records in our returns data, we'll calculate the average. And here is the result of our rolling or moving average. You can see that the first 5 records are all nans. The first row here is a nan because it includes the first row from our returns data frame, which is a nan. So anytime you include a nan in your computation, the result will also be a nan. The second record is a nan because the window size will increase up to 5. So long as there is a nan in the input calculation, the result will also be a nan. Finally, after the first 5 records, our rolling window will include 5 records from the original data frame where none of the input values are nan. It will calculate the average as expected. Here are the 5 records that are part of our rolling window. The rolling window then moves or rolls over and includes the next 5 records. and so on till we get all of the resultant values. When you use rolling windows, you can perform any aggregation or any statistical operation. For example, here we calculate the standard deviation on a rolling window with 5 records. We perform this operation on the Amazon returns data frame. The first 5 records are all nans. The fifth record is a nan because it includes the first record. The sixth record does not include the first record, and it's a valid value for standard deviation. Hopefully, the highlights that you see on the input data on which we are performing the standard deviation aggregation allow you to understand how the rolling window works. Let's visualize some of our calculations using a more complex plot. We'll use matplotlib to instantiate a figure which is 13 inches by 6 inches. The original line plots the returns that we calculated directly. These are the percentage change returns in the color purple. It also has the label original. We also then plot the rolling mean that we calculated over 5 records. We want this plot to have a legend so that we understand the data, and also a title, absolute value and 5-day rolling mean of Amazon returns. And here is the resulting plot with both these bits of information. The purple line you see is the original returns, the percentage change in returns, and the blue line is a rolling mean. You can see that returns are very spiky, but the rolling mean gives you a better idea of how Amazon stock prices changed over the course of time. Let's work with datetime objects in Pandas in a little more detail so that you can understand the various operations that we can perform on dates and times. pd.timestamp allows you to convert any object to a timestamp format. Here we've passed in a string for 1st of January, the year 2000. And the result is a timestamp object representing this instance in time. We can call pd.timestamp and pass in an integer value as well, and specify that we want this interpreted as seconds. Pandas will interpret this as seconds from the beginning of the epoch, that is the 1st of January 1970, and the timestamp object says that this is some instance in the year 1987. The date range function in Pandas is what you can use to specify a range of dates or times. Observe the date range that we've specified here, 9 to 1400, 9 a.m. to 2 p.m. and the frequency is 30 minutes, and we extract the time information. And the result here is a number of datetime.time objects at 30-minute intervals starting at 9 a.m. in the morning. So the first object is for 9 a.m., the second object represents 9:30 a.m. and so on. The second to last object represents 13:30 and then 1400, 1:30 p.m. and 2 p.m. You can generate datetime objects in hourly frequencies as well. We use the same pd.dateRange function from 9 to 2 p.m., 9 a.m. to 2 p.m. at a frequency of 1 hour. And here are the resulting datetime.time objects where the range is from 9 a.m. to 2 p.m. with a frequency of 1 hour. So we have 9 a.m., 10 a.m., 11 a.m. and so on. Now that we know how to use pd.dateRange, we can use this function to set up Pandas series objects. Here we have instantiated a series of dates starting with the date 1st of January 2012. The periods is equal to 3 and the frequency is capital D, which stands for days. If you take a look at the result of this operation, you'll understand what it means. We start our date range on 1st of January 2012 and on a daily frequency, that is, we want the resulting objects to represent 1 day and we want this for 3 periods. So we get 3 days of information. The resulting Pandas series contains the 1st, 2nd and 3rd of January as its date time information. The Pandas time delta object can be used to represent differences in time. Let's say the difference in time or the time interval between two datetime objects are 1 day, 1 hour, 1 minute, and 1 second. So we can instantiate a time delta for this. Time delta can be added to timestamp objects in Pandas, as you see here on screen, in order to get a new timestamp. So we added a time delta of 1 day, 1 hour, 1 minute, and 1 second to the 1st of January 2000, and we got the 2nd of January 2000 at an instance of 1 hour, 1 minute, and 1 second on the 2nd of January. You can pass in specific input arguments to a time delta object. Here we pass in the arguments for days and hours. Days is equal to 0, hours is equal to 11. This is a time delta that represents 11 hours. Here is another time delta representing 1 day and 15 hours, so a little over 1.5 days. This is a separate time delta object. It's also possible to add two time delta objects together, and Pandas will perform the right calculations. Time deltas of 11 hours and 1 day 15 hours gives you 2 days and 2 hours. You can instantiate series objects using Python list comprehension as well. Here is a list comprehension to generate time delta objects. Days is equal to I for I in range 3. So for 3 days and hours equal to 9, we want to generate the result. This code will become clearer when you take a look at the result. We have 3 time deltas in the series: 0 days 9 hours, 1 day 9 hours, and 2 days 9 hours. Let's now create a new data frame by combining the two series that we instantiated, a series of days and a series of time deltas. Here is the dictionary that we pass into the pd.dataframe constructor, where the key is days with a capital D and the value is the day series that we had instantiated earlier. You can see the day series to the right side of your screen. The second column is the second series that we just instantiated. This is the time delta series. And here is the resulting data frame df with two columns. The first column contains the days from the day series and the second contains time deltas. You can see the individual records highlighted and you can see the values that it has received from the individual Pandas series that we had set up. The date range is typically used to generate date time indexes for time series data. Here we've assigned this to an indices variable pd.daterange. Starting from 1st of January 2000, periods is equal to 8, meaning we'll have 8 date objects in the result, and frequency is 30t. That is, each period will be 30 minutes apart from the previous object. Here is the resulting date time index. We have 8 values specified by periods equal to 8 in this date time index, and you can see that the frequency difference between each consecutive value is 30 minutes. We've instantiated a date time index. Let's now create a new data frame. This data frame has two columns, column named A and a column named B. The column A contains A, B, C, D, E, F, G, H. These are characters. And the column B contains some random integers, 50, 100, 150, and so on. The index for this data frame we initialize to the date time index that we had generated earlier. This time, the data frame that we create will not use the default integer values for the index. Instead, it will use the date time index. And here is the result, a data frame with two columns A and B, and the index values are the date time index that we had set up. With a date time index, you can perform interesting time series specific operations. For example, if you want to know what record is present at time 1:30, you can use the @time function on this data frame. Let's instantiate another date time index with index values that are 15 minutes apart. They start on the 1st of January 2000. It's for 8 periods, but the indices are 15 minutes apart as opposed to 30. Let's instantiate another data frame. df underscore 15 is equal to pd.dataframe. This data frame has two columns, A and B, exactly like the data frame that we have created before. A contains a list of characters, B a list of integers. The index values for this data frame is this new datetime index. This is the new index that we generated where consecutive index values are 15 minutes apart. Let's take a look at this data frame. It has two columns, and the index values are the datetime index that we had used. Let's now perform some mathematical operations on the two data frames that we created, df plus df underscore 15. I'm going to display the original data frame values on the right side of the screen. Here is df and df underscore 15 highlighted. If you notice the index values for the very first record in these two data frames, the index values are exactly the same. So when you sum up the two data frames, the string or character values get appended together. So for column A, which has characters, A plus I is equal to AI in the result. For column B, which is made up of integers, 50 plus 450 is equal to 500. For the next record here, both of the fields A and B are nans. That's because this record contains valid values in only one of the data frames. Both data frames do not contain valid values for this particular index. When you sum up two data frames, it tries to add the values corresponding to the same index. If valid values are present in both data frames, we get a meaningful result. When valid values are present in only one of the data frames, the resulting fields are just nans. Let's play with this a little more and see some more operations. Let's instantiate two more series objects. df1 contains a pandas series with 5 elements, 0 through 5. The index for this series is a date range starting on the 3rd of January 2000 for 5 periods. For a date range, the default time interval is 1 day. Similarly, we set up another pandas series and assign it to df2. This contains the numbers 0 through 9. np.arange10 will give us numbers 0 through 9, and the index is a date range starting on the 1st of January 2000 and for 10 periods. Let's instantiate a new data frame using the two series objects that we just created, df1 and df2. Observe that df1 has just 5 rows and df2 has 10 rows of data. Some of the index values overlap. And let's take a look at the resulting data frame that we generated from the two series objects. You can see that nans have been used to fill in values that were not available. df1 had just 5 elements. Any elements that were not present were filled with nans. The right values corresponding to these indexes were picked up from the df2 series. You can see that there are 5 nan values corresponding to the 5 missing rows in df1. You can use some specific pandas functions to fill up these missing values with some logical data. For example, df.ffill. ffill will fill the nan values in our data frame using some kind of interpolation behind the scenes. ffill will fill in the last valid observation to the remaining cells. So the last valid observation was 4 and the remaining cells are also filled with 4. ffill also allows you to specify how many records you want filled in. So how many nan values you want filled in. If you say limit is equal to 2, only 2 nan values starting from the last observed value will be filled in. Just like ffill, bfill will fill nan values at the beginning of the data frame. Observe that the nan values were filled in using the first observed valid value, which was 0. And just like with ffill, you can use bfill with a limit. Limit is equal to 1 will fill in just the first nan value that it observes starting from the first valid value and moving backwards. If the data that you store in your data frame is made up of strings, pandas offer some special functions and operations to work with string data, and that's what we'll study in this demo. We'll be writing our code in the string data Jupyter notebook. Let's import the libraries that we need for this demos. We'll import pandas as pd and numpy as np. We'll instantiate a simple pandas series object to the string data variable, which contains a list of strings: ant, bull, cat, dog, and elephant. Assign this pandas series to string underscore data. Let's take a look at the contents of this string data series. You can see that it's a series of strings. The data type is object. This is when pandas hasn't assigned the data type explicitly. And the indexes are the default indexes starting from 0. Now, when you have string data, you can access the strings by calling the .str member variable. String underscore data .str.lower will convert all of the strings to lowercase. So we have the same strings: ant, bull, cat, dog, and elephant, but notice that they are all in lowercase. If you can convert strings to lowercase, it should be possible to convert them to uppercase as well, and that's possible by calling the upper function on string data.str. This returns a new series with all of the strings in string data, but the strings are now in all uppercase. There are other interesting operations that you can perform with strings as well. For example, you could swap the original casing of the string. Here we have string data.str, and when we call the swap case function, notice that all of the characters that were originally in lowercase are now in uppercase and vice versa. For example, in the string ant, the first character A was originally uppercase, it's now lowercase. N and T were originally lowercase, they are now uppercase. Here are the elements in the original string data series: ant, bull, cat, dog, and elephant, with the first characters capitalized. Let's now lowercase all of the strings in this series by calling string data.str.lower and assign it to string data lower. String data lower is a Pandas series with all of the strings in lowercase, as you see here on screen. These are the same strings with all lowercase. In case you want only the first letter of each string to be in uppercase and all of the other letters in lowercase, you can use the capitalize function. String data lower.str.capitalize will give us ant, bull, cat, dog, and elephant. Notice that the first characters are all in uppercase. The len function available on string data.str will give us the lengths of every string that is present in the series. The original series of strings had 5 elements. The resulting series also has 5 elements which correspond to the lengths of the strings in the original series. Ant has 3 characters, its length is 3. Let's now instantiate another Pandas series comprised of strings. Observe that this contains different kinds of strings with different cases, with different special characters, and sometimes with leading and trailing white space. Here are the first 3 strings, string 1, 2, and 3. They contain the special characters hyphen and colon, and notice that string 2 and 3 contain leading and trailing white space. This series also contains an np.nan. This stands for not a number. The special nan value is not a string. You can see the 2 other strings here, one that starts with the special character hash and one which says number %57. Here is our string data series printed out to screen containing a number of different kinds of objects. Let's now convert all of these strings to uppercase by calling string data.str.upper. Notice that every string value has been converted to uppercase. Anything that is a letter or a character and has an uppercase has been converted to uppercase. Nan, or not a number, is not really a string, so string operations do not apply to it. And the number hash 4, 5, 3, and 57 are numbers, not letters or alphabets. They do not have a corresponding uppercase, so they can't be converted. Let's now perform a chained operation in Pandas. We access all of the strings in the string data series, convert them to uppercase, access the string in the resulting series by calling str, and then call capitalize. This will give us a resulting series where all of the strings have their first character capitalized. String 1 has its first character S capitalized, as does number %57. String 2 and string 3 have leading white space characters, which is why their first character is not capitalized, because the first character is a white space. Let's find the lengths of all the strings in this series. As we've seen before, we call string data.str.len. Len is the function that will give us the lengths of the individual strings. Here is the result of all of the lengths of the strings in our series. Notice that the nan value does not have a corresponding length. The length is nan as well. If you want to clean up the string data that you have stored within a column in a data frame, you can simply call the strip function. So string data.str.strip will strip the trailing and leading white spaces of all strings. The resulting data frame contains the same strings, but leading and trailing white spaces have been stripped. If it's not clear, specifically observe string 2 and string 3, which have trailing white spaces. They are not present in the result after we call the strip function. You can confirm that leading and trailing white spaces have been stripped by calling strip data.str.len. Notice that the lengths of string 2 and string 3 are now smaller than before. All of the other strings did not contain leading and trailing white spaces. Their lengths remain the same. Pandas also gives you a quick way to check whether a particular string contains a number. Call string data.str is numeric to check whether a string is a number. This will return a series of booleans. None of the strings that we have in the original series are numbers, which is why you see all false values. Nan, it's not an actual numeric value. Let's now instantiate a new pandas series and assign it to the data variable. This series contains a number of different kinds of elements which are numbers, strings, and characters. Here is the resulting series. Because the series contains mixed values, the data type is object. This particular series contains a mix of numeric and non-numeric values. Let's call data.str.isNumeric, and this time you'll see true whenever a particular string has a numeric value. Observe that the first element in this series is a number 1. It's not a string, which is why when you try to call isNumeric on it, it says nan. It doesn't know how to interpret it. This is a little confusing, but isNumeric is a function that is called on strings within your series. One is not a string, so when you call the function on it, it's not able to return a value. The strings in this series that can't be converted to numbers, such as #2 and will have a isNumeric value of false. These are clearly not numbers. But 3 and 4 are string values that are numeric, which is why you see true when you call isNumeric. Using pandas, it's possible for you to concatenate all of the strings in a particular series. String data.str.cat will concatenate using the pipe as a separator. The result is a single concatenated string with all of the string elements from our original series. And you can see that every string element is separated using the pipe as a separator. You can also concatenate the strings in a particular series with a list. So string data is our original series. Access the strings called the cat function and specify A, B, C, D, E, and F as a list. The NA_rep parameter is what you pass in when you want to represent unavailable or missing data using some kind of special character. Here we've used the _special character to represent missing data or nans. Take a look at the strings in the resulting series. Notice that every element of the list A, B, C, D, E, F has been appended with the corresponding element in the series. And the fourth element, where we have the nan, is represented using an underscore. What if we try to concatenate a list of characters with elements in a pandas series, but the list did not have the same number of elements as the series? This is an error. Observe here that pandas throws an exception and does not perform the operation. All arrays must be the same length. Most of the operations that you can perform on individual strings in Python are also supported for all of the strings that live within a pandas series. If you want to check whether any of the strings in a series contains a particular pattern, you can access string data.str and call the contains function and pass in the pattern that you're looking for. Here we're looking for the hash. The result is a series of Boolean values. The value will be true if the corresponding string element in the series does indeed contain a hash. The Boolean value will be false in all other cases. The result will be a nan if you're operating on a nan. The contains operation on string values stored in a series supports regular expressions as well. Here we want to check whether a string contains a hash, a percentage sign, or :thr. This is a regular expression where the result will be true if any of these patterns match. Here is the Boolean result of this operation. Notice that the result is true when the patterns match or are found in the original string. Let's take a look at some of these cat patterns. The :thr is present in the string 3. The hash special character is found in the string #453. That is why the corresponding result is true. And finally, the percent is found in the string number %57. Let's change this regular expression just a little bit. So we'll check for hash and percent as before, but instead of :thr, we'll change it to :thy. Now, :thy does not match any of the strings in our original series. You'll find that the result is true where we find the hash and where we find the percent sign in the original series. However, :thy does not match the string because that is :thr, which is why the corresponding result is false. The pattern was not found. The contains operation just returns true or false. If we want to find the index position within a string where a particular character occurs, we'll use the find function. So for all of the strings in our Pandas series, we want to find the position of the character E. The result will return the index position of the first occurrence of E in each of the strings. If the character E is not found, the find function will simply return -1. So where E is not found, you'll see a -1 in the result. So for the first string in our series, we have an E at the 9th index position. For the third string, we have it at the 12th index position. And for the last string, we have it at index position 4. And for those strings where the character E was not found, we have the -1. The find function is not just for characters. It can be used to search for substrings as well. Here we are looking for the substring ring. And here in the result, you'll see that if the string ring is found as a substring in any of the original series elements, the index is returned, as in the case of the first 3 strings. The substring ring is present starting at index positions 2, 3, and 4. And when the substring is not found, a -1 is returned, as in the case of the strings #453 and number %57. You can also use the findAll function to find all instances of a particular string within your series. FindAll E will show you where all E exists within your series. You can see that in certain cases, E appears twice, and in other cases, it appears just once. Notice that every element in the resultant series here is a list. FindAll does not return index positions. Instead, it returns an actual occurrence of the match. You can also use regular expressions with findAll. Here we want to find all occurrences of the uppercase characters A through Z, at least one occurrence of them. Here is the resulting list. This is a series where every element of the series is a list, and the list contains all of the occurrences where a match was found for the regular expression. In string 2, we found 2 uppercase characters S and T. In string 3, there was exactly 1 uppercase character S. You can also use pattern matching to apply transformations to your string data. For example, replace will replace all occurrences of the string E with the asterisk. In the resulting series, observe that every occurrence of the character E has been replaced by the asterisk. You can specify any arbitrarily complex regular expression as the pattern that you want to match. Here is a pattern that matches all occurrences of lowercase letters A through Z. You can call stringdata.str.replace and find matches for this pattern and replace all of those matches with 3 hashes. And that's exactly what you see here in the result. Observe the very first string that's made up of 2 words, string and 1. The first word, that is string, is replaced by 3 hashes. The second word, 1, is also replaced by 3 hashes. For string 2, notice that we only match the lowercase letters A through Z. The uppercase S and T are left as is. The remaining letters are replaced by 3 hashes. Let's define a lambda function which will extract the matched string and convert it to uppercase. So that is the replacement. Call the replace function on all of the strings in our Pandas series. We find all matches for the pattern. Remember, we are looking for lowercase letters A through Z, and we apply the replacement lambda function, which will convert all of the lowercase letters to uppercase. And that's exactly what you see here in the result. All pattern matches for lowercase letters or alphabets have now been converted to uppercase. You can also apply the count operation on all strings to count specific characters or substrings. Here we want to count all of the white spaces present in our strings. This white space can be a leading white space, trailing white space. It can occur anywhere within the string. You can see that the first string, string 1, has exactly 1 white space character between the 2 words. String :3, on the other hand, has 4 white space characters. Some of these are leading white spaces, others are trailing white spaces. You can also apply string operations on series to do fun things like repeat each string a certain number of times. Here we want each string to be repeated 3 times. And here is the resulting series. Notice that every string in the original series has been repeated thrice. For example, here you see string 1, string 1, string 1. None of these string operations, no matter what the operation is, apply to nans. The operation on a nan is always a nan. When you work with data in the real world, a very common operation that you have to perform is to transform the data in the format that you want it to be. You want to perform analysis, and you know the kind of analysis that you want to perform. You have something in your head. But how do you get your data to be in exactly the right format for that analysis? That's what we'll study in this demo. We'll see how we can apply functions on series data in order to transform the data to a different format. We'll write code for this demo in a new Jupyter notebook, and this is the apply functions on series notebook. The first step, of course, when you're working with data manipulation and exploration using Pandas is to import the libraries that you need. For this particular demo, we'll go ahead and import Pandas as PD, also import the numpy library as NP. NumPy, remember, is a Python library that you use to work with multidimensional arrays. NumPy and Pandas are both part of the PyData stack. They're closely integrated and work very well together. In fact, Pandas often uses NumPy behind the scenes to perform some of its manipulations. For this particular demo, we'll work with an interesting dataset. This is a dataset of cars sold on the Zoom Tanzania site. This cars data is located in the datasets folder under the current working directory. Zoomcars.csv is the name of the file. We'll read the contents of this CSV file into our pandas data frame in order to perform exploration and analysis called pd.read_csv and specify datasets /zoomcars.csv as your path. Once the cars dataset has been loaded, call carsdata.head and pass in 5 as an input parameter in order to view the first 5 records in this dataset. If you call head without the input parameter, that also by default displays just 5 records. If you take a look at the car listings on Zoom Tanzania is a site in Tanzania used to connect buyers and sellers. You'll see that there is a bunch of different information in here. One of the columns at the very beginning is the URI. This URI is the listing page for this particular car at zoomtanzania.com, and this listing is under sedans, hatchbacks, pickups, and so on. I'll briefly go over some of the other interesting columns here and leave you to explore the dataset in more detail as you need to. There is also a priority for each listing. It can be gold or silver, as you can see on screen. There are probably other categories here which are not present among the first 5 records. There is also a column which lists the price for this particular car. The seller wants to sell the car at this price. This is, of course, in the Tanzanian currency. At the very right of the screen, there are a number of columns about the ad listing itself. When it was posted, what weekday it was, the time it was posted, the year the ad was posted, and so on. There are many more columns in this dataset. I'm going to scroll over to the right so you can view some more. You can see the model of the car. You can see the make of the car. You can see whether the car is currently in Tanzania or has to be imported. If the car has to be imported, there is a column for whether import duty has been paid. Then there are a number of other features which car buyers might want to know, such as the mileage, the kind of transmission, the description, and where exactly the car is located. Whenever you're working on data analysis with data from the real world, it's good practice to first explore the data and then get rid of the columns that you're not planning to use. This will reduce the size of your data frame, and your operations will be more performant. This is one of the most common operations that you'll perform in Pandas, and Pandas offers an easy function for you to do this. CarsData.drop allows you to specify the columns that you want dropped from the original data frame. We've specified an input parameter to this function, that is the columns parameter, and it takes in a list, and we pass in a list of columns that we are no longer interested in analyzing. We're interested in the other columns. We want to drop these columns: ID, URL, page, price, currency, location, description, and so on. We assign the resultant data frame to cars data, which means cars data is now a smaller data set, much easier and more performant to work with. Now let's go ahead and drop all of the rows which have missing values. So if there are any fields within a row which are not available, that is data is missing, we want to drop that record as a whole. This we do using drop NA. Every row in a Pandas data frame has an index that Pandas automatically assigns. Now, when you drop rows, certain rows will be missing and index values will contain non-contiguous values. So there'll be certain index values which are missing from cars data. If you want contiguous index values, you'll need to reset the index so that the indices for your rows start from 0 and are continuous values once again. We've seen this operation before. Simply call carsData.resetIndex so that we reset the index to start from 0 going all the way to the number of records. Now let's quickly call the head function in order to explore the dataset as it now stands. Observe that we have all of the features that we were interested in. The columns that we dropped are no longer available. In addition to index values which start with 0, this is because we called reset index, we also have an additional column called index. This additional index column are the original index values that existed before we called reset index. This additional index column is actually of no use to us. Now that we've reset the index, we'll just make do with the new indices. Let's scroll over to the right in order to see all the columns that we're going to work with. Now let's go ahead and drop the index column. This is the column with the original indices. We are no longer interested in those. Simply call the carsData.drop function and specify within square brackets the columns that you want to drop. Right now, it's just the index column. You can also specify additional information. Axis is equal to 1 basically says that it's a column that you want to drop. The column axis is axis 1. And if you take a look at this resulting data frame, you'll find that the index column, which we no longer need, does not exist in the data frame. We have reset the indices and dropped the original indices. With basic data cleaning out of the way, we are now ready to apply some transformations on our data. The first transformation we'll define as a lambda function. This is a change case function which takes as its input a string represented by x and converts it to uppercase. Lambda functions are anonymous functions in Python and are very useful to perform quick operations. So change case is our lambda function. Let's now apply the change case function to the make field. While exploring the data frame, you might have noticed that there was a column of data which contained the make of the car that was sold on the Zoom Tanzania site. This make column had the car name in all case, mostly in sentence case, but it could be lowercase. In order to standardize this, let's change all of the car makes to be uppercase. We access the make column or the make series by calling cars data square brackets make and call the dot apply function. The dot apply function is what allows us to transform the data in that column. And in our case, the transformation that we want to perform is to change the case of the string which represents the make of the car. We want to convert it all to uppercase. So simply specify apply and pass in the change case lambda function. This will apply to every row of data. And take a look at the series that is the result of this operation. All of the makes of the car, BMW, Toyota, Volkswagen, Audi, and so on, are now all in uppercase. Now, some of these columns have categorical or discrete values, such as current location. In order to quickly get a sense of the various locations where our cars are located from this dataset specifically, you can call the unique function on any series. So access cars data, the current location column and call unique, and this will list out the unique locations. The current location is a categorical field with just two values. It tells you whether the car is available in Tanzania or has to be imported. So in Tanzania and available for import are the two unique values in the current location field. Let's say that we want to transform this data so that this information is expressed more clearly or more succinctly. Instead of current location in Tanzania or available for import, we want a single column import. This import column will tell us whether the car needs to be imported before it can be sold to a buyer. Adding a new column with transform data to a data frame is very straightforward. Specify the name of the new column in brackets. In our case, it's cars data, import, and then specify how you want the data for this new column to be generated. In this case, we want to apply a transformation on existing data in the data frame in order to generate the values for this new import column. And what's the transformation we plan to apply? We'll check the current location of the car and check to see whether it's in Tanzania or available for import. We'll perform a map operation on the current location column, and if the value of the field for any particular row is in Tanzania, we'll map it to the value no, indicating the car does not have to be imported. And if it's available for import, we'll map it to yes, indicating it has to be imported. Once you've executed this mapping transformation on current location, and executed this cell, let's take a look at the dataset as it stands now, called carsData.head in order to view the records. You'll find that a new import column has been added to your data frame. Because the data in this column has been generated by applying a transformation to the current location column, a mapping operation, you'll see that import is no whenever the current location is in Tanzania, and if the current location says available for import, import will be yes. Let's explore the import column and see the number of unique values that it contains, called carsData import.unique, and you'll see that it's an array with just the values no and yes. Those are the unique values. Just a little bit earlier, we saw how we can perform a transformation using a lambda function. This time, let's define a named function which contains a transformation. This is the drop comma. The drop comma takes in a single field value as its input, converts it to a string format, and replaces the occurrence of any comma within that string with an empty string. So any string which had commas, the commas will simply be removed. Observe that we are explicitly casting the input field as a string before we perform the replace operation. We are going to apply this drop comma transformation function to the price value field. Let's first explore this field to see the kind of data that it contains by calling the head function. If you take a close look at the price value field, you'll find that the price is expressed using commas, so that it's easier to know whether it's 1 million, 100,000, or so on. But also the data type of the price value field is of type object. Because of the presence of commas, price value is not considered to be numeric data. So the data type is not int64 or float64. Instead, it's an object, which means you can't perform numerical aggregations on the price value field as it stands. There are a number of functions that we need to apply in order to convert this price value field to a numeric form. The first step here is to drop the commas that exist. And this we'll do by applying the drop comma function to the price value field. What we're going to do is access the price value column, call apply, and pass in the drop comma function and assign the result back to the price value column. This is a common technique used in Pandas in order to make in-place changes to the data stored in a particular column. So the old values of price underscore value will disappear and we'll get new values without commas. Now let's quickly explore this price value field to check whether the drop comma transformation function has been successfully applied, and you can see that it has. Observe though that the data type for this column is still of type object. That means Pandas does not interpret this as numeric data even though the commas have disappeared. For this, we'll need to perform another function transformation. Pandas offers a very handy built-in function to convert the object or some other data type to numeric form, and that is the pd.to underscore numeric. The pd.toNumeric function can be applied to a column of values, which is essentially a Pandas series. This will convert every element in the series to a number, to numeric form, and we're going to assign the result back to the price underscore value column. Now it's time to make sure that the function that we applied produced the right results. Let's explore the price value column, and you can see that we have numeric information and the data type for this particular column is now int64. That is the most significant. Panda will now treat this column of data as numbers, which means we can now apply numerical transformations or numerical aggregations to this data. Now that we have the price information in numeric form, we can apply a different transformation to extract some information which might be useful for car buyers. This is the category function, which takes as its input argument the price of a car. We'll then categorize all of the cars in our dataset based on its price as cheap, mid-range, expensive, or a luxury car. As you can see, the functions that we apply to series in order to perform transformations can be arbitrarily complicated. You can perform a whole bunch of processing within these functions. This particular function is a little more involved than the lambdas and other functions that we've seen so far. Our price data is already in numeric form. However, just to be safe, we convert the price to an integer form. We cast it as an int. We then perform a number of checks on the price in order to categorize the car as cheap, mid-range, expensive, and luxury. If the price is less than 10 million Tanzanian shillings, we consider that car cheap. This is, of course, just a category that we've defined. The category can be anything that you choose it to be. Let's say the price is between 10 million and 30 million shillings. We consider it to be a mid-range car. And if it's greater than 30 million but under 70 million Tanzanian shillings, we consider that an expensive car. Above 70 million, that's a luxury car. Let's go ahead and apply this category function to the price value column in our cars data frame. Cars data.price value.apply category. And let's explore the first 10 records. And these 10 records show us that cars have been categorized. Let's check to see whether the categories make sense. Okay, we have this particular car here, which costs 5.6 million Tanzanian shillings. That's definitely a cheap car based on our categorization, and you can see that it has been categorized correctly. And here is a car which costs 97 million Tanzanian shillings. And that definitely, based on the categories that we generated, is a luxury car. So you can see that categories have been applied correctly based on the price of the car. Now that we know that this categorization works, let's generate a new column in our data frame. This is the price underscore range column, and this will contain the categories of the car based on price. So we'll apply the category function to the price value column and generate the price range column. And here is the resulting data frame with the new column added in. And at the very right, you'll see the new column that we added, price underscore range, which specifies the category that the car belongs to. The functions that you apply to columns in data frames, which are Pandas series objects, need not be functions that you have defined. You can apply standard built-in Python functions as well. Here in this example, I've chosen two columns, price value and mileage, and I apply the built-in max function in Python. This will give me the maximum value in my data set for the price of a car and the mileage of a car. Let's see some more interesting functions that we can apply on series data, and this time we'll work with a new data set, nationalparkvisitors.csv, that is available in the datasets folder in the current working directory. We'll read this dataset in as a pandas data frame using pd.read_csv. The index that we want to use for this dataset is the year. There is a year column within the dataset which specifies the number of visitors for each year. That year column is what we want to be the index of the resulting data frame. This is a fairly small data set. It comprises of data for the years 2008 to 2017, and it gives us the number of visitors for each of these national parks: the Acadia National Park, Badlands, Sequoia, and Yellowstone. Observe that when we read in the data, Pandas did not generate its own index values. Instead, it used the year column from the underlying dataset as its index values. Let's say you want to find the minimum number of visitors for any of these national parks. You can use a function for this, the built-in min function. Because we want to apply this function to all columns, apply this to the data frame as a whole. So apply the min function and specify axis is equal to 0. Axis is equal to 0 will calculate the min value across all of the rows in our data frame, which means we'll get a minimum value for each column. And the result will show you the minimum number of visitors for each of these national parks. It doesn't tell you what year the minimum number of visitors visited these parks, but it gives you the min. Let's say you wanted to apply the min function on a per row basis. So you want to find the min number of visitors across all national parks for each year. So you'll apply the same min function to the data frame as a whole, but you'll say axis is equal to 1. This will compute the min value across all columns for one record and give you a minimum value for each year, as you can see here on screen. We've seen earlier when working with time series data that Pandas makes it very easy to calculate moving averages on your data. We can use np.data.rolling to define a rolling window over our data set and perform any kind of aggregation. Here we've specified a rolling window of 3 records and we're calculating the mean for each window. Here is the result seen on the left side of the screen. Because the window size is 3, you can see that the first 2 records of the result are nans because there are not enough records to go into the computation of the mean. Let's visually take a look at how the rolling window works. The result for the year 2010 will calculate the average number of visitors, that is the mean value, for each of the national parks across the years 2008, 9, and 2010. The rolling window of size 3 will then roll over so that the record for 2011 will calculate the average number of visitors in each national park for the year 2009, 2010, and 2011. The rolling window is not the only kind of window that Pandas support. You can also have an expanding window. An expanding window is what you'll use when you want to calculate cumulative sums. Here we are calculating average values using an expanding window, and the minimum number of periods within this window should be equal to 3. Let's take a look at a result and understand how this expanding window works. The first 2 records in the results are nans because the min periods equal to 3 is not satisfied. Let's move on and take a look at the record in the result for the year 2010. This includes the years 2008, 2009, and 2010. The result gives us the average number of park visitors across these 3 years. The expanding window will then expand to include the year 2011. The result for the year 2011 will contain the average number of park visitors all the way from the year 2008 to the year 2011 and so on. The window will then expand further till all of the result is populated. In this exercise, you will plot a horizontal and vertical bar graph using data in your data frame. You'll also assign a title for your graph. Next, you will recall all of the statistical information available in a box plot. You will then invoke the write pandas function to convert your column values to be of type date time. And finally, you will apply a function to convert a column with string values such that the string values are in lowercase. I now invite you to pause this video here and try these exercises out on your own before moving on to viewing some sample solutions. Let's now see a sample solution for how you would plot the data in a data frame in the form of a bar graph. Your solution might be a little different, and that's totally fine. Assume that you have a data frame called df and you have a population column within that data frame. In order to plot a bar graph of population, you'll simply call df.population.plot. Plot is the function that you invoke for visualization, and into that you'll pass in the input argument kind is equal to bar to plot a bar graph that is oriented vertically. The title for this plot will be population by country, which you specify as a separate title input argument. In order to orient your bar graph horizontally, you can invoke the same function, df.population.plot. The kind of the bar graph will change though. It will be bar h, not bar. The title field is set as before. The title of this bar graph is population by country. A box plot offers you a rich set of statistical information that you can view at a glance. This is what a box plot looks like. It has a box in the center with a horizontal line. Then there are two vertical lines that extend outwards and terminate with two more horizontal lines called whiskers. Now, this horizontal line that you see at the center of the box represents the median of your data set. So, one of the bits of statistical information that you get from a box plot is the median of your column. By default, the edges of the box that is drawn represents the quartiles. The 25th percentile is the lower edge and the 75th percentile is the upper edge. So the box as a whole represents the interquartile range. And finally, the whiskers at the very outer edge of the box represent the range of data, the minimum at the lower end and the maximum at the upper end. These are all the bits of statistical information that you can derive from a box plot. Let's now see a sample example for how you can convert column values to datetime objects. Now, when you read in a data frame from a CSV file, all of the data types are of type object. In order to convert these objects to datetime formats, you use the pd.to_datetime function. This is a built-in function available in Pandas. Here we are accessing the date column, applying the pd.toDateTime function to it, and storing the result in the date column itself. Now, all of these values will be in the datetime format. Let's now see a sample example of how you can convert the string values present in a column to lowercase. Now, your example might be a little different, and that's totally fine. Here, I've specified a simple change case lambda function. It's possible for you to do this using a named function as well. This lambda simply applies a x.lower operation on the input argument x. Once we've specified change case, you can simply apply this change case function to a particular column. Access a column. Here we are accessing the name column in our df data frame. Call .apply and pass in change case. This will change all of your string values to be lowercase, and this lowercase string values will be assigned back to your name column. When you're working with data, a very common operation that you perform is to group the data and perform some kind of aggregation on it. Pandas supports multiple levels of grouping and many different aggregations. Let's take a look at some of these. We're going to write our code in the groupings and aggregations Jupyter notebook. We'll first import the libraries that we'll need, pandas as pd and numpy as np. These are libraries we've used before. Let's read in some data from the objects.csv file. This is a file which contains certain everyday objects and its shape. This is the information within the CSV file, and it's present under the datasets folder. We'll read this file in as a data frame using pd.read_csv. This is a pretty small data set with just 9 records. Let's take a look at what it has. It has an object, an everyday object such as mirror, wheel, lemon, box, and so on. The shape of the object, which can be circle, square, or rectangle. The color of this object, such as yellow, brown, silver, white, black. And the number of items of this object that are available, that is the quantity. Let's perform the first grouping operation on this data set. We want to group this object's data by the shape column. Remember, the object can be a circle, a square, or a rectangle. Shape data is a special kind of data frame with a grouped field. You can see it's of type data frame group by. Now let's take a look at the contents of the shape data by calling .first. First is a function that is offered by grouped data frames. This will return every group present in that data frame along with the first record in that group. It won't return every record. Observe that the groups here form the index of this grouped data frame. So we have the shapes circle, rectangle, and square. This is what we group by. There are multiple records with these shapes, but for each shape, the first function has returned just the first record, which happens to be mirror in the case of circle, towel in the case of rectangle, and box in the case of square. Once you have this grouped data frame, let's say you want all of the records associated with a particular group. You can access shapedata.getGroup and specify the name of the group that you're interested in, which in this case happens to be square. This will return a data frame with all of the records that belong to the square group. There are 2 records in our data set, The object box and bread both belong to the square group. Once you have a grouped data frame in Pandas, all of the aggregations that you perform on this data frame are applied to a particular group. They are not applied to the data frame as a whole, which is useful if you want group-wise information. So here we call shapedata.quantity.sum to perform the sum aggregation on the quantity column, and we get the sum of the quantity for each group. So circle has a total quantity of 9 and so on. Let's perform another different grouping operation on the original object. So we have objects underscore data group by, and this time we want to group the objects by the color column. And the resulting grouped data frame we assign to the color data variable. Now that we have the objects grouped by color, let's perform a different aggregation. Once again, the aggregation is on the quantity column, color data.quantity.mean. We want to find the average quantity across objects for each color and observe from the result that we have a value associated with each color group. Remember, when you're using a group data frame, all aggregations that you apply will be applied on a per group basis. If you take a look at the color groups here, you'll find that by default, they happen to be sorted. For example, black, blue, those are the colors that appear first. White and yellow appear at the very end. They're sorted in the alphabetical order. Let's say you don't care about sorting. It's possible for you to specify this as an input argument when you perform your grouping. Here once again, we group our original objects data by the color column, but we explicitly pass in an input parameter to the group by function saying sort is equal to false. We are indicating to group by that we don't care to sort our groups in any order. Let's perform the same aggregation on the grouped data frame and see how the results are displayed. You'll find that the results are no longer sorted. The groups are basically created as the records are encountered in the original dataset. Silver appears first and red appears at the very end, and you can compare this with the default specification for group by, which sorts the groups in ascending order. You can have your group by operations run a little faster if you say sort is equal to false. Now, behind the scenes, a Pandas data frame basically stores its data in the form of numpy arrays. Tabular data is easy and more intuitive to work with, which is why the Pandas library is so popular. You can always access the array form of any Pandas object, whether it's a series or a data frame, by calling the values member variable. Objects data.values will give you the contents of the data frame as a numpy array. What we are doing here is accessing the array representation of our data frame and calling the t member variable, which transposes that array. So values is the array representation, t is the transpose of that array, and we are converting that to a list. And here is what the resulting array looks like. Now, a data frame comprises of rows and columns. So obviously, the array representation of a data frame is two-dimensional. The records in the original array would have corresponded to one row in the data frame, but because of the transpose operation that we applied, a single column forms a sub-array within the outer array. So here is the nested array, which contains all of the object information. There is a nested array that contains shape information, a nested array that contains the color information, and so on. And here at the very end is the nested array that contains the quantity information. The sub-arrays are column-wise because of the transpose operation that we applied. When you're cleaning and wrangling data using Python, you'll often want to convert from a Pandas data frame to a multi-dimensional numpy array. And the values member variable is what you'll use for this. Once you have the data represented in the form of a multi-dimensional array, that is a numpy array, all of the normal array slicing operations and other operations can be applied to your data. Here I want to access rows 1 up to 3, not including 3, from the original array. And here are the two rows. The row at index 1 contains the shape information. The row at index 2 contains color information. We now have an array called array underscore index, which contains the shape as well as the color of the individual objects. We'll use this to generate a pandas multi-index. We worked a lot with index values in pandas, and you should be very comfortable with the idea of indices. A multi-index is the hierarchical analog of the normal index that we've used so far. A multi-index is an advanced indexing concept that makes it easier for you to perform analysis where you have data with a large number of dimensions. Here we generate a pandas multi-index from the arrays that we set up earlier. Remember, the array contains shape information as well as color information, and these two columns are going to be part of our index. The array index contains two rows of data, one for shape and one for color. So we assign names to those rows, shape and color. Let's now create a new data frame holding the same data that was in our original objects.csv file. But this time, this data frame will have a multi-index. The data columns of this data frame are object and quantity, that is the kind of object, mirror, towel, and so on, and the quantity of each object. And the index is a multi-index of shape and color. Now, it's quite possible that the concept of a multi-index wasn't really clear to you. The hierarchical nature is not clear without an example, and this is the example that should clarify stuff a great deal. Here is the new data frame that we just created with multiple indices. The first index is the shape of the object, the second index is the color of the object. This shape and color is the multi-index that we had set up. We had created this multi-index from the array index, which comprised of two rows, one for shape and one for color. The data columns of this multi-index data frame comprise of two bits of information, the object itself and the quantity. This is what we had passed in when we had initialized the new data frame with the same object's data, but a multi-index data frame. And here is the hierarchical multi-index. Two columns form index values. The outer index at the root of the hierarchy is the shape. The inner index at the leaf of the hierarchy is color. Now that we have a data frame with multiple indices set up, let's see what kind of analysis we can perform on this multi-level data. The first thing is grouping. Because we have multiple hierarchical levels of indices, when you specify a group by operation on a data frame with multiple indices, make sure you specify the level at which you want the grouping to occur. Here we call multidata.groupBy, level is equal to shape, and then we perform the sum aggregation. Pandas interprets that the sum aggregation makes sense only on the quantity column. So notice the group is the shape, and then we have the sum of the quantity associated with each group. You can perform a grouping operation using any of the indices in the multi-index. Here we group by level is equal to color and perform the sum aggregation. The sum aggregation is applied on the quantity column, and for each color, we get a total value for quantity. Now for multi-index data frame, the interesting thing is the ability to group by multiple columns. So you can perform a group by operation and specify both levels, shape as well as color. And once this grouping is done, we perform a sum operation, and this is what the result looks like. Notice how this gives us information for every shape color combination. This ability to group by multiple levels allows us to answer questions like, how many silver colored circular objects do you have? We know it's 5 based on our grouping and aggregation. How many yellow colored circular objects do we have? Well, 4. How many square brown objects do you have? 3. Once you have a multi-index data frame, you can also switch the order in which you want grouping to be performed. You can group first by the color level and then by the shape level. Simply specify the levels in the order in which you want the grouping to be performed. And as for the aggregation, we perform the same sum aggregation as before. And here is what the result looks like. Notice that the very first column is the color column because that is the column that we grouped on first. And then we have the shape column. This grouping helps us answer the same questions as before, but here you think color is more important. How many black rectangular objects do you have? 1. White rectangular objects? 2. Once you group by 2 levels, here it's color and shape, you can call the getGroup function, but you have to specify a tuple. You have to specify the color and the shape because that is what comprises a group. So we are grouping by color and shape. Color is the first level, shape is the second. When we call get group, specify the color first and then the shape. So we want to get the group white rectangle. Here is the result of this get group call. There is exactly one white rectangle object in our data set. Observe, we have the color, shape, and we call get group with a tuple. Pandas offers a special object called grouper, which is essentially just syntactic sugar over the group by operation that we've seen earlier. Here, we are performing a group by operation, but instead of the columns directly, we specify a pd.grouper object. Observe something here. We are performing a group by operation on two columns. The first of these columns is one of the indices, and the second column is object, which is just a regular column. That is possible as well. Instead of using the column name directly for the index column, we use a pd.grouper object. We use the object column name directly. So we group first by shape and then by object. And this is the result as you see here on screen. pd.grouper is just syntactic sugar for specifying the column name directly. This is something you need to remember. So we have a grouping by shape and then by object, and we perform an aggregation sum which sums up the quantity. When you have a data frame with multiple indices, you can refer to the index values. By the name of the column, you can also use an index position. Here we are performing the same group by operation as before, but to pd.grouper, we pass in level is equal to 0. If you take a look at the result, it's exactly the same as before. We first group by shape and then by object. However, the way we've specified the shape that we want to group by, the shape index, is by specifying level is equal to 0. The shape index is at the 0th index position. Once you have a grouped data frame, you can also use a for loop to iterate over the data present in that data frame. Notice here that we have grouped our original objects data. This does not have the multi-index, it just has the regular index. So for name, comma, group. So when we perform the group by operation, the first parameter is basically the group itself. The second parameter is all the contents of that group. And if you take a look at the result, you'll see exactly what I mean. The name variable holds the group, that is the name of the group, which can be black, blue, brown, any of the colors. Remember, we've grouped only by the color column. And the second variable, the group variable, holds the entire object that belongs to that particular group. You can see here that the black group and the blue group has just one record, but the brown group has two records. After this little segue using our objects data frame, let's go back to using our multi-indexed data frame, that is multi-underscore data, and group by both color and shape and call the size function. The size function is a quick way for you to see the number of records associated with each group. Here you can see that a silver circle has two records, all other groups have just one record. You can quickly explore basic statistical information for each of your groups as well in a group data frame. So we group by color and shape and call the describe function. The describe function, if you remember, is what gives you a quick glance at the stats associated. And here in the result, for every group, we have the count, mean, standard deviation, min, max, and the quartiles. Some of these groups have just one record. The count is equal to 1. So the mean is the value of the single record itself, that is the quantity. The standard deviation is nan because there is no standard deviation for a single data point. We've seen examples of using built-in Python functions for aggregations. You can also use numpy functions to perform your aggregations as well. Here we've grouped by the shape index, level is equal to shape. And instead of calling the sum aggregation directly that's available in Pandas, we call the general purpose aggregate function and pass in a function into here, which will actually perform the aggregation. So we pass in the np.sum function to aggregate. This essentially performs the same operation as calling sum directly. So for each shape, we sum up the quantity. Let's see one more example of using the aggregate function. This time we group by two levels, shape and then color, then call the aggregate function and pass in np.sum to the aggregate function. The resulting data frame will be grouped by both our indices, first by shape, then by color, and the quantity will be summed up. And that's exactly what you see here in the result. For all of the group by operations that we've been performing, the resultant data frame is actually useful because it gives you the value that you've grouped by and the aggregation result. If you are interested only in the aggregated result, but not the value that you're grouped by, you can pass in as index is equal to false. The result of as index is equal to false, it is true by default, is clearer when you see the result. Notice that we get the aggregated value of quantity, that is the sum of all quantity for each shape group, but we don't get the shape itself. So we only get the aggregated result, not what we group by. Let's try this once again. This time we'll group by shape as well as color on our multi-index data frame. As index is false, so we get the aggregated result, but not the shape color tuple that makes up the group. When you use the dot aggregate or the dot ag function, which is simply dot aggregate, you can perform multiple aggregations as well. Here we've grouped by shape and we want to perform the aggregations sum, mean, min, as well as max. Because we've specified 4 aggregations, there are 4 columns in the result. So we have the shape, circle, rectangle, and square, that is our grouping. And notice we have the sum, mean, min, and max for each shape. Pandas is highly customizable and you can explore data in exactly the way you want to. Let's say you want to apply different aggregations on different columns, that's possible as well. Here we use the multi-indexed data frame and perform a group by operation on the shape index, and then we want to apply 2 different aggregations. On quantity, we want to apply the sum aggregation. On object, we want to find np.max. Notice how we specify the aggregation for each of the columns within curly braces. And here is the result with individual aggregations applied on each column. On the quantity column, we've applied the np.sum aggregation to find the sum of all objects of a particular shape. On the object column, we've applied the np.max aggregation. np.max for objects simply finds the last object in lexicographical order. This is within a particular shape group. There are many ways to perform aggregations on group data, and you should choose one that works for you and is intuitive. Here we group by shape and we apply a transform operation which takes in a lambda function that performs an aggregation. Typically, when you use the transform function, you want to perform a more general purpose transformation on the data, but it can be used for aggregations as well. The transform takes in a lambda function which calculates the mean. Let's see exactly what this transform does by taking a look at this result here. For every shape group, we calculate the average quantity. Now, what if we want the results of this aggregation to be stored in our data frame? That's possible by simply assigning it to a particular column and giving that column a name. So within the multi-data data frame, we add a new column called average. This average column will hold the average quantity of items of each shape. And here is the resulting data frame with the new average column. Because average values are calculated on a per shape basis, within each shape group, the average values should be the same. If you're cleaning data, an important operation that you might want to perform is filter your data to contain only those records that you're interested in. And that's what we'll study in this demo. We're going to be writing our code in the filtering Jupyter notebook. Let's start off by importing the libraries that we need. Import pandas as PD and numpy as NP. The dataset that we're going to work with for this demo contains students' performance, and it's available in the datasets folder under the current working directory in the students performance.csv file. Use pd.read_csv to read in this file as a data frame. Call perfdata.head and pass in 10 as an input argument to view the first 10 rows in this data frame. You can see that this contains general information about students, the gender, race and ethnicity, parental level of education, whether they take standard or reduced lunch, and whether they've taken a test preparation course, whether they've completed it or taken none. In addition, we also have their scores in math, reading, as well as writing. Let's say you wanted to explore this data set, but you were specifically interested only in the performance of female students. In such situations, you would apply a gender filter to your data frame and view only the female students. And here is one way in which you can apply a gender filter. Remember, gender is a categorical column with two discrete values, male or female. Here is our filter, perf data gender column, that's what we are interested in, is in, and you can specify a list. The only value in this list is female, so we are only looking for the female students. And this is the result of the gender filter. Any filter returns true or false, and you can then use this filter to select records from the original data frame. You can see that the value is true if the student is a female and it's false if the student is a male. So the isIn function returned a pandas series of Boolean values where we have true and false values. We can now use this gender filter with true and false values in order to filter only the records for the female students in our original data frame. So we call perf data, and within square brackets, we simply specify the gender filter. And with the resultant data set, let's call the head function to see what this results in. The gender filter has extracted only the female records from our original data frame. You can see that gender is equal to female for all of these records. Once you have a filter, you can flip the values as well using the tilde notation. So tilde gender filter will convert all true values in the series to false and false values to true. And once we apply the reverse of the gender filter to our original data frame, this will extract all of the records of the male students. You can see in the resulting data frame that the gender is always equal to male. What we saw right now was an example of a simple filter condition. However, filter conditions can be made arbitrarily complex and can include logical operations such as and, or, and not. For example, here we have a condition where we want gender to be female, that is, the gender column should be female, isIn female. And the second criteria that we want our records to satisfy is that the reading score for a particular record should be greater than the writing score. So this is a condition which has a logical and it's basically a combination of two conditions. And this is how you specify the logical and. The condition is simply a series of true and false values when applied to our data frame. Once we have the condition, we can use this to filter the original data frame. So call perf data, and within square brackets, you can specify your filter condition. And when you explore the result using head, you'll find that we only get records which match both of the criteria that we had specified because we've used the logical and. Gender is equal to female, and the student's reading score is greater than the student's writing score. Let's see another example of applying multiple filter conditions. Let's go back to our original gender filter where gender is in female. We want to select just the female records. This is what the gender filter looks like, a series of true-false values. A value is true if the record is for a female student, false otherwise. Let's set up another filter called course filter. This is a filter on the test preparation course column. We want to know whether the student has completed his or her test preparation course. So if the value of the test preparation course is in the completed list, we have just one element in that list, then this condition will be true. The course filter, just like the gender filter, is a Boolean series of true-false values. If a student has completed his or her test preparation, the value will be true. It will be false otherwise. Now let's apply a more complex filter using a logical and. We'll apply both of these filters to perf data and extract those records where the student is a female, that is, the gender filter is satisfied, and the student has completed her test preparation course. The ampersand that we specified between the two conditions indicates that both conditions need to be satisfied, and here is the result. All of the records in the resulting data frame are for female students and they've all completed their test preparation course. A quick glance through the result should show you that the filter conditions have both been satisfied. Let's get some more experience working with filters. Here we've initialized a variable called education levels, which is a list And the two kinds of education levels that we are interested in are associate's degree and bachelor's degree. Make sure you specify the elements of this list exactly as they appear in the Pandas data frame. The strings have to be an exact match. Let's create a new parent filter where we filter the students based on their parental level of education. So the filter is applied to the parental level of education column, and we want to access the data for only those students where the parents have either an associate's degree or a bachelor's degree. Perf data parental level of education is in education levels. That is the variable that we had initialized. Let's now apply this parent filter to our perf data frame, and in the result, you will have the records only for those students whose parental level of education is either bachelor's degree or associate's degree. So far, all of the filters that we applied to rows. We performed row level filtering where we included only those rows that matched our filter condition. It's also possible to perform column level filtering. Here we've invoked the filter function on the perf data frame, and within that we've passed in items. All of these items refer to columns. The only columns that we want to include in our filtered results are gender, test preparation score, and the math reading and writing scores. And this is a way by which we can filter on data frame columns. You can see that the resultant data frame has only those columns that we were interested in. You can filter on columns with more complex operations. For example, you can apply a regular expression to column names and extract only those columns which match your regular expression. Now, this filter could apply to rows as well as columns, which is why when we call perfdata.filter, our regex is score. So we want to extract all of the columns which have score in its name, and we specify axis is equal to 1, indicating that it's a column level filter. There are 3 score columns in our data frame: math, reading, and writing scores, and that is what is available here in the result. The filter function on your data frame applies to rows as well as columns. You can also pass in a like parameter to your filter. Here we want to extract any records where the field values are like 14, that is 1 for the string. And axis equal to 0 tells Pandas that we want to perform row level filtering. Here is the resulting data frame, and if you're not able to understand why these records are present here, observe the index values. All of the records that contain indices with 1, 4 in them have been included in the result. There are other ways to perform filtering on data frames as well. For example, let's say you want to extract all of the records where race ethnicity is equal to group A. You can access the values in the column by specifying the column name in square brackets using the double equal to sign and specifying the group that you're interested in. This is the filter condition. Apply this to the perf data frame and you'll get all students whose race or ethnicity is group A. In this demo, we'll see how we can apply conditional masks on our data frame in order to use only the data that we need. And we'll also see how we can work with duplicates. Dealing with duplicate data is an important part of data wrangling and cleaning. We're going to be writing all of our code in the masks and duplicates Jupyter notebook. Let's go ahead and get started by importing the libraries that we need. We'll need pandas and numpy. Import pandas as pd and numpy as np. We'll first instantiate a simple pandas series object which contains integers in the range 0 through 10, 10 not included. This will be our sample list where we'll demonstrate masks and filters. The sample list is a pandas series object where the elements in this series are the integers from 0 through 9. Now let's see how we can perform a simple conditional filtering or masking of this data frame. This is a filter on the sample list where we want to extract only those elements that satisfy the filter condition. Sample list is less than 3, only those elements whose values are less than 3. This filter condition will be applied on the sample list, which is why we specify the filter within square brackets. And here is the result. All elements of the sample list that satisfy the condition less than 3. Instead of a filter, we can apply a masking operation on a data frame, which means we are only interested in those elements where our condition is satisfied. We want to mask all of the other elements. In order to do this, we call the where function on the series and apply the condition sample list is less than 3. Observe that the resulting series is the same shape and size as the original series, except that all of the elements which do not match the condition have been masked. They are nans. When you use the where function, the elements which did not match the condition were masked. When you use the mask function, the elements which do match the condition will be masked. That means all elements where the values are less than 3 will be masked, as you can see here in the result. When you call the mask function on a Pandas series object, the mask is applied to all elements which match this condition. The mask operation masks those elements which match the condition. The where operation masks those elements which do not satisfy the condition. Here is the Pandas series object, the sample list that we are working with, containing elements from 0 through 9. Now let's apply a where operation on the sample list. When we use the where operation, we find those elements of the sample list that are greater than 3. The elements which do not satisfy this condition will be masked. They will be nans, as you see in the result. Elements that do satisfy this condition, sample list is greater than 3, will remain as is in the result. By default, the mask that is applied when we use the where function on a particular series is the nan. We can also specify a slightly different mask. Here in this particular operation, all of the elements in the list that do not match the filter that we've specified, we want to mask with the X character. There are 4 elements here that do not match the filter condition. That is elements 0, 1, 2, and 3. They are not greater than 3 and they've all been masked using X. They've been replaced by X in the resulting series object. And as usual, those elements that match the filter condition remain as is in the result. Let's take a look at a simple series instantiation. We want to instantiate a series with elements in the range 0 through 10, 10 not included. These are the numbers, the integers 0 through 9. Let's see an operation which masks data and then compares one series with another. We first apply a where condition on the sample list. This where condition produces a series where all elements which do not match the condition will be replaced by X. And we want to compare this with the original series. We instantiate a new series object which has the elements 0 through 9. The result of this is a series which contains Boolean data. The Boolean value will be false where the corresponding elements in the two series that we are comparing do not match. It will be true otherwise. Let's take a look. You can see that the first 4 elements are false. This is because in the masking operation, we mask the first 4 elements. They do not satisfy the condition. However, the remaining elements in the Boolean result are true because they match the original series object, which contains the elements from 0 through 9. We've seen some examples of masking here. Let's move on to working with duplicates. For this, we'll instantiate a new data frame. This data frame comprises of 2 columns of data, color and vehicle. Observe that we instantiate this data frame using a dictionary. The color is the key, which is the first column name, and the corresponding value is a list of colors. The second key is vehicle that corresponds to the second column of the data frame, and its value is a list of vehicles, truck, bus, van, truck, and so on. Let's take a look at the data frame that we just instantiated. You can see that there are a total of 7 rows of data. The first column is color, the second column is vehicle. In both of these columns, you can see that the data contains some duplicates. Certain colors are duplicated, certain vehicles are duplicated. You can check to see whether the value in a particular column is a duplicate, that is, it has been seen before in that column by calling df.duplicated and specifying the column that you're interested in. In this case, we want to see what values are duplicates in the color column. The result here is a series of Boolean values, and you can see that some of these values are false and others are true. Let's analyze these. The first value is false because when we encounter the color red, you can see that there's exactly one occurrence of red in the color column, which means it's not a duplicate. So the entry corresponding to red says false for duplicate. But let's say you encounter a value more than once. In that case, duplicated will return true. For example, the color green occurs 3 times in the color column, and for all 3 occurrences of the color green, duplicated returns true. Let's invoke the same function df.duplicated, but this time we'll pass in a different column, the vehicle column, and we get a Boolean result as before. You can see here that there are 3 entries here that are duplicates. The second entry is for truck, bus, and van, and that's what returns true. Let's say you want to clean your data set and you want to drop duplicates. So let's say you want to discover the duplicates based on a certain column and you want to drop duplicated records. You can do that by calling the drop duplicates function, and you can pass in a column to check for duplicates. The resulting data frame will be a subset of the original data frame, and the color column will hold no duplicated data. The color green occurred 3 times in the color column, but in the resulting data frame, you can see that it occurs just once. Pandas pick the rows to drop at random. Any of the rows that contain duplicated color information were chosen at random and dropped. You can exercise some control over which of the duplicated record you want to preserve in the resulting data frame. When you call drop duplicates, you want to drop duplicates based on color, you can specify a keep argument. You can say keep is equal to first, and Pandas will preserve the first record that it observes. Pandas will scan the rows from the first row to the last, and it will keep the first record that it finds for any color, and it will drop the remaining records. You can see that keep is equal to first is the default value when you drop duplicates. If you compare the two results, keep is equal to first and a simple drop duplicates, you'll see that they're exactly the same. Instead of preserving the first record in the resulting data frame, let's say you wanted to preserve the last record in the data frame. You can simply specify the keep argument to be last, and this will change the result. If there are multiple records for a single color, instead of preserving the first record, keep last will preserve the last record that Pandas encounters. Another option is to say that you want to drop all records which have duplicates. You don't want to keep any of the records with duplicated values in the color field. So you'll simply say keep is equal to false. The only colors that were not duplicated in our original data frame were red and blue, which is why only those records have been preserved. Green and yellow were duplicated, those records have been dropped completely. You can check for duplicates across multiple columns as well. One row is considered to be a duplicate of another only if all field values of the two rows match. When we consider both color and vehicle, you can see that there is just one duplicated record. Green van occurs twice. So we get true only for the second occurrence of green van. This allows you to be more granular about the duplicate records that you want dropped. Let's say you want to drop duplicates only when both the color and vehicle match for 2 records. You can see from the result that green van now occurs just once. That was the only record where both the color and the vehicle were duplicates. If you have duplicates in your data frame, but you want to get rid of all duplicated records, you don't want to preserve just one of them, you can say keep is equal to false. Notice that there is no occurrence of the green van in the result when you say keep is equal to false. If you want a quick way to explore the data that you have stored in your data frame along 2 specific dimensions, the cross tab in Pandas is a very useful function. The cross tab takes in the 2 dimensions that you're interested in. Here, this is just color and vehicle. The result of a cross tab is something that in machine learning is called a confusion matrix. It's actually a matrix representation. Notice that color is along the rows, those form the rows of your data, and the vehicles form the columns of the resulting matrix. The cells of the matrix give you a frequency count of the records that match these 2 conditions. For example, take a look at the green row, and you can see that we have 1 green car and 2 green trucks in the original data frame. The frequency count for green car is equal to 1 and for green van is equal to 2. Let's take a look at another row here. You can see that we have 1 yellow bus, 1 yellow truck in our original data frame. The kind of data that you work with can be divided into two broad categories. The first is continuous data, which comprise of a continuous range of values. Another common type of data that you might work with is categorical data. Categorical data is data which has discrete specific values. Continuous data implies an infinite set of values. Categorical data is a finite set of discrete values. Let's see how we can work with categorical data in Pandas. We'll write our code in the Jupyter notebook called categorical data. Let's import the libraries that we need. Import pandas as PD and numpy as NP. Let's create a series with categorical values and we'll name this categorical series. We instantiate a pd.series object and it contains three discrete values: cotton, polyester, and wool. Pandas supports a special data type for categorical data. Notice that the D type that we have specified here is equal to category. With this data type, Pandas understands that this series is made up of discrete values that may or may not be ordered. Let's print out the categorical series. You can see that we have cotton, polyester, and wool. D type is category. And you can see that Pandas has determined that the category contains three objects. Let's instantiate another Pandas series object which contains categorical data, but this time we'll specify a duplicate in the category: cotton, polyester, wool, and cotton once again, and the D type is equal to category. Because we've specified the data type of this series to be category, Pandas is smart enough to know that these are discrete values, and you can see in its specification of the categories that it knows about that it has not considered the duplicate cotton. So the series contains the cotton element twice. However, the categories still say that there are just three objects in the category. Let's now instantiate a pandas data frame with three separate columns: material, garment, and size. And all three columns are made up of categorical data. You can see that the material is cotton, polyester, wool, and silk. The garment can be t-shirt, jacket, socks, and scarf, and the size can be medium, large, or small. Here is the resulting data frame with the three columns of data. There are a total of 4 records and 3 columns. Now, if you take a look at the data types for this particular data frame, by default, Pandas assumes that the data type is object. It does not identify categorical data by default. However, if you want Pandas to treat these column values as categorical data, you can cast or change the data type of each column to be category. Here we'll create a new column where we cast our material column as type category and assign it to the new column. The new column is called material underscore cat. Here is the data frame as it stands right now with a new 4th column material underscore cat added. The 4th column contains the same data as the first material column, but if you take a look at the data types, you'll find that the data type associated with the 4th column is different. It's of type category. When you instantiate a data frame, instead of accepting the default data type of object, you can explicitly specify a data type for the data that you set up. Here we've explicitly specified a data type or a D type input parameter to our data frame constructor to indicate that this contains categorical data. Here is the data frame with the same 3 columns, no change here. But if you take a look at D types, you can see that every column has category as its data type. We'll now take a look at the individual columns here, starting with the garment column. So index into the data frame, display the garments, and you can see that its data type is of type category, and there are 4 categories here. Each value in the column is a category: jacket, scarf, socks, and t-shirt. We take a look at the size column. There are 4 values here: medium, large, and small. But because its data type is category, it has identified just 3 categories. Pandas has correctly identified that the 3 categories are large, medium, and small. Now, if you're working with categorical data, often the categories have a certain innate order. And when you want to specify order for your categorical data type, you should use the categorical dtype class. From pandas.api.types, we'll import categorical dtype and we'll instantiate a categorical dtype. Here, materials is a categorical data type with the categories cotton, polyester, wool, and silk. These categories do not have any innate order, which is why we say ordered is equal to false. If you take a look at what is in materials, you can see it's of type categorical D type. The categories are the 4 categories and it's not ordered. Let's set up another categorical D type, this time of sizes. Intuitively, you know that garment sizes have an innate order. So we instantiate a categorical D type with categories small, medium, large, and we indicate that they are ordered in the order that we've specified. Small comes first, large comes last. When we list out the sizes categorical data type, you can see that it's ordered. Now that we have categorical data types defined, we can use them when we set up our series objects. Here we have a new series called list series. We instantiate it using pd.series and specify the values medium, small, x, large, and small. And we cast this series to be of type sizes. Sizes was a categorical D type that we had instantiated earlier. But if you remember when we set up sizes earlier, we'd only specified the sizes small, medium, and large. But this particular series has this value extra large, and you can see that the values medium and small have been preserved after we cast the series to be of data type sizes. However, the one value that was not identified, extra large, is now a nan. Let's set up the same data frame that we did before with the 3 columns, material, garment, and size, and the same values as well. Let's cast the material column to be the categorical data type materials. This is a categorical D type that we had instantiated earlier. And we'll now cast the size column to be of categorical data type sizes. This is the ordered sizes categorical D type we had instantiated earlier. Here is the data frame that we just instantiated with 4 records and 3 columns. If you take a look at the material column, things are as expected. The materials are cotton, polyester, wool, and silk. The D type is category, and all of the values in the series map to the categories that we had set up for materials. Let's take a look at the values in the size column. The sizes are medium, large, and small. You can see that the D type is category, and observe that this is an ordered categorical data type. Pandas now knows that small is less than medium, which is less than large. We hadn't made garment a categorical data type, and if you take a look at the values in the garment column, you can see that the D type continues to be object. Let's perform some operations on categorical data. We want all of those rows which satisfy the condition material is equal to cotton. This is a filtering operation that we could perform even if material wasn't of categorical type. Here we see one record where material is cotton. Here is another filtering operation. We want to extract all rows from the data frame where the size column is equal to large. Once again, this is something that can be performed even if the size column wasn't a categorical data type. But here is something interesting that we can do now that we know that the size column is an ordered categorical D type. We can apply inequality operations on the size column. Here we want to access all of those records where size is greater than small. Now, this is possible only when the size column is a categorical data type that is ordered. And the result here shows you all garments which have size medium or size large, because those are the ones that are greater than small. Inequality operations cannot be applied to unordered categorical types. For example, if you want all rows where material is greater than cotton, that is meaningless, which is why Pandas will throw an error. The error is pretty obvious here. Unordered categoricals can only compare equality or inequality. Other logical operations do not apply. Interestingly enough, when the data type for a particular column is of type object, you can still apply inequality filters. Pandas automatically assumes lexicographical ordering of your data. For example, if you're looking for those records where garment is greater than scarf, you'll find that the result is t-shirt and socks. T-shirt and socks both occur after scarf in the lexicographical order. Well, this is okay, but it doesn't really make much sense because lexicographical order may not make sense for values such as for garments. it makes much more sense to define garment as a categorical data type. So let's cast the garment column as type category. Now, if you take a look at the garment column, you can see that its D type is category. And it supports the 4 categorical values that were present in the column: jacket, scarf, socks, and t-shirt. Now that this is a categorical column, you can specify equality filters. For example, you can retrieve all records where garment is equal to scarf. Well, this happens to be exactly one record in our current data set, that is the silk scarf in the small size. But now, if you try to apply an inequality filter for garment greater than scarf, you'll get an error. And if you set up your data in this way, it makes much more sense. Pandas is now able to tell you that a greater than or a logical inequality filter does not make sense for this categorical data. If you have categorical data that is ordered in nature, additional pandas operations can be supported. For example, we can sort values by the size column because size is an ordered category. Here is the resulting data frame with all of the rows sorted by size. We start with size small and go up to size large. The categories for any series is held in the cat field. So you can access df.size, that will give you a series object, .cat.categories, and this will show you that the size column supports the categories small, medium, and large. The cat member variable for a particular series holds its categorical data type. Once you have access to the categorical data type, you can use it to add categories. Here I'm accessing the categorical data type for the size column, df size.cat. I then invoke the add categories function on this categorical data type, and I've added 2 new categories here, X large and XX large. Now, if you take a look at the size column, you'll see that the data type is category, and you can see all 5 categories here. The categorical data type is still ordered, and the 2 new categories that we added were added to the very end. So we have the right order for size here. Small is smaller than medium, which is smaller than large, which is smaller than extra large, which is smaller than extra extra large. You can add categories to unordered categorical data types as well. Here we are accessing the categorical data type for the materials series, and we've added the category bamboo. Here is the column of values for the column material. And if you take a look at the categories that it supports, you can see that bamboo has been added to the very end. The categories are unordered. The categorical data type supports the add categories function. It also supports the remove categories function. If a category is no longer valid, let's say the extra extra large category is no longer valid, you can go ahead and call remove categories to remove it. And if you examine the size column now, you can see that its data type categories does not contain extra extra large anymore. Now it's possible that you've defined a bunch of categories in your categorical data type, but your actual data frame doesn't contain many of those categories. If you want to get rid of those categories that are not used, you can do so by calling cat.remove unused categories. Let's take a look at the size column after unused categories have been removed from our categorical data type. If you take a look at the categories, you'll see that we are once more down to 3. Small, medium, and large occur in our data set. Those are the only categories that have been preserved in the categorical data type. Another function available on your categorical data type is set categories. Let's say you want to set a whole new bunch of categories in a different order. You'll call set categories. Notice that now our categories start from extra small and go all the way up to extra large. These are the brand new categories that we want set. And if you take a look at the size column, you'll see that we now have the new categories in our categorical data type. The categorical data type is still ordered. Here is the data frame with our data. In the size column, we have medium, large, and small. Let's say we set our categories to just extra small, small, and medium. In the new categories that our categorical data type supports, large is no longer included. We've eliminated large. Now, if you take a look at the size column, you'll find that the values that corresponded to large are now not a number. With the new updated categories in our categorical data type, large is not considered a valid category, which is why those values have been replaced by nans. When we work with data frames, we know that Pandas automatically generates indexes for each of our data frame rows. However, you have a lot more control over indices as well. In this demo, we'll study the different kinds of reindexing operations that we can perform on our data frame. We'll write all of our code in the Jupyter notebook called reindexing. Go ahead and import the libraries that you need. Import pandas as pd and numpy as np. Let's instantiate a data frame with some manually generated data. This contains information about candy bars, and there are 3 columns of information in this data frame: the name, the company, and the cover. The name column contains the names of the candy bars, such as Snickers, Dairy Milk, Kit Kat, Ferrero Rocher, and so on, and the company that produces these candy bars. That information is contained in the company column, and the cover column specifies the color of the cover of the candy bar. Let's take a look at the data frame that we just created. It has 3 columns and 5 rows, 5 records. Let's use the reindex operation on the candy bars data frame to generate a new data frame we call candybars.reindex. The indices that we are interested in for this resultant data frame are the index values 0, 1, and 3 from the original data frame. And the columns that we are interested in are just name and company. If you take a look at candy underscore reindexed, you can see that from the original data frame, we have indexes 0, 1, and 3, and we have values for the name and company column. The reindex function allowed us to select specific rows and columns of data to create our new data frame. Let's invoke the reindex function once again. This time we call candybars.reindex, but the index values that we specify are 0, 1, 3, 5, and 6. If you remember, our original data frame has just 5 rows and index values 0 through 4. And the columns that we want in the result are name, company, and rating. The rating column doesn't exist in the original data frame. Let's take a look at the result. Notice that the result has rows that correspond to every index value that we specified, except that the index values 5 and 6 are just filled with nans because there were no records in the original data frame for these index values. Similarly, the columns in the resultant data frame are the columns that we specified using the reindex operation: name, company, and rating. However, the rating column had no data in the original data frame, which is why the rating column is now completely filled with nans. The reindex operation can also take in another data frame. Let's instantiate a brand new data frame with 2 columns, name and company. The name is just name 1, name 2, name 3, and name 4, and the company is just A, B, C, and D. We're not really interested in the values of this data frame. We're interested in the columns and the indexes. Let's use this data frame that we just created as an input to the reindex operation. This time we'll call reindex_like. We want candy bars to be reindexed to be like the df data frame that we just set up. Reindex_like basically looks at the index values and the columns in the df data frame and extracts only those index values and columns from the original candy bars data frame. Here is what the result looks like. Notice that the index values 0, 1, 2, and 3 have been extracted from candy bars, and the columns name and company have been extracted. We've seen this before. When you instantiate a new data frame like we are doing right now, you can specify your own index values. This data frame contains 2 columns, name and company, and there are a total of 8 records. For the name column, we simply have name 1 through name 8. For company, we just have A, B, C, D, E, F, G, and H. Notice the index values that we've specified. They range from -2 to 5. If you take a look at the resulting data frame, you'll see that you can customize the index values to be how you want them to be. Our index values range from -2 to 5. These are the indices and columns of the df data frame. Make sure you remember this because we are going to use this df data frame in our reindex operation. So we call candybars.reindex like df. df has index values which are not present in the original candy bars data frame. Those index values are present in the result, but the fields of those rows are filled with nans. The indices -2, -1, and 5 are not present in the original candy bars data frame, which is why the fields in those rows are all nans. The fields which do exist in the original candy bars data frame have the right values. Let's call the ffill function on our data frame. Ffill, if you remember, is a way where Pandas uses interpolation behind the scenes to fill in values for missing fields. Ffill stands for forward fill, and it interpolates the last valid record to fill in values for rows which come after the last valid record. It fills in the missing fields by performing some kind of interpolation. Here it simply copied the last valid record and filled in the record at index 5. Just like ffill, you can perform the bfill operation to fill in missing data. Bfill is backfill. This is where Pandas finds the first valid record in the Pandas data frame, and it uses that to interpolate backwards to fill in earlier records with missing fields. Both forward fill and backfill can be specified with a limit. Let's say we pass in limit is equal to 1 into our bfill operation. Only one record before the first valid record will be filled. So you can see that only one record has been filled in using interpolation. The very first record is still nan, contains missing values. In this exercise, you will filter the records in a data frame to keep only students of the male gender. Assume you have a data frame called students and you have records of both males and females. You will then perform a check for duplicate values in your data frame. You'll check to see whether a particular column or columns have duplicate values. You will then write code to drop duplicate values from a data frame. These duplicate values can be for a single column or multiple columns. And finally, you'll define categorical values and state how they differ from continuous values. I now invite you to pause this video and try and answer these questions and perform these exercises on your own before you move on and view a sample solution. Let's take a look at a sample solution to filter records in a data frame. I assume that I have a student's data frame and within that I have a gender column. If I want to filter out those records which belong to male students, I can simply specify students in square brackets, students' gender is equal to male. This particular operation will retrieve all of the rows in the student's data frame where the gender is equal to male. Now, there are other ways of doing this filtering as well, and it's possible that this is the type of your solution. You can use the is_in function on a Pandas series to check whether the student's gender is in male. The is_in function returns a series of Boolean values, and these Boolean values can be used to filter the original student's data frame. This filter will also give you the records for all male students. Now, your solution might be a little different and might have made different assumptions, and that's totally fine. Now, let's move on to see a sample solution to check for duplicate values in a Pandas data frame. If you're looking for duplicate values in a particular column, you can use df.duplicated. df is my data frame here, and I'm looking for duplicate values in the name column. This will return a Pandas series object with Boolean values, where the Boolean value is true if that value is a duplicate. You can check to see whether your data frame contains duplicate across multiple column values as well. Here, I've specified the column's name as well as age in a list, and I'm checking to see whether there are rows which have the same value for name and the same value for age. Only then does Pandas consider that a duplicate. Let's move on and see one sample solution to drop duplicate values. The df.drop_duplicates function is what you'll invoke to drop duplicate records. Now, there are different input arguments that you can specify to customize how drop duplicates work. Here, I drop those records which have duplicates in the name column. Keep is equal to first will preserve the first record for each duplicated value. So one record for a duplicated value will be present in the resulting data frame. Let's say you want to drop duplicates and you want to get rid of all duplicated records. You don't want to preserve even one. You can specify keep is equal to false. All duplicated records will be dropped. Only those records which do not have duplicates will be present in the resulting data frame. You can also check for and drop duplicates based on values in multiple columns. Here we are checking for duplicates based on the name and the age column. And when we drop duplicates, we'll preserve one duplicate record. We'll keep the last record, keep is equal to last, that Pandas encounters. And finally, let's move on and understand the differences between categorical data and continuous data. Categorical data is made up of a finite set of discrete values, garment sizes of large, small, medium. These are examples of categorical values. Images of cat, dog, or rabbit. That is an example of a categorical value. Categorical data may be ordered or unordered, both are possible. Continuous data is typically numeric and it is an infinite set. For example, all of the decimal numbers in the range 1 to 10. That is an infinite set and an example of continuous data. Continuous data is not made up of discrete finite values.